Hey, welcome back, genius. So today we are going to learn periodic table and periodic trends. So this is going to be the first lecture of this series. Let me take the laser pointer. So in this first lecture, we are going to learn what is periodic table in chemistry, what is the need of learning periodic table, what type of questions are asked in interviews, and then I will show various forms of periodic table. So this is going to be the basic introductory lecture. So if you're already aware of these things, you can skip this lecture and you can go to the lecture number 2. So in this lecture, I'm just going to deliver what is the purpose of learning this periodic table, why you need to learn this, and then to increase the curiosity in yourself, I will show various forms of periodic table. So without wasting any time, let's start. So the first thing we have to know is what is meaning of periodic. So something that is recurring at regular intervals that we call as periodic. Now definition of periodicity in context of periodic table. So the recurrence of properties of the elements after a certain regular intervals when they are arranged in the increasing order of their atomic numbers is called periodicity. So in your exam, if the examiners ask what is the definition of periodicity, you can write this. Now, what is the periodic table in chemistry? So the periodic table, also known as periodic table of elements, is a tabular display of the chemical elements which are arranged by atomic number, electronic configuration, and recurring chemical properties. So these things we will learn in details in the later lectures. The 7 rows of the table called periods. So in the periodic table, we have 7 rows, generally have metals on the left and non-metals on the right. The columns are called groups. It contains elements with similar chemical behaviors. The elements from atomic numbers 1 to 118 have all been discovered or synthesized, completing 7 full rows of the periodic table. The first 94 elements, hydrogen to plutonium, all occur naturally, though some are found only in trace amounts. Elements 95 to 118 have only been synthesized in laboratories, nuclear reactors, or nuclear explosions. So these elements do not occur naturally, do not form naturally. So these are synthesized. So this slide is just for you to take notes. You can take these small notes, which will be helpful for you in later. Now this is the basic structure of a periodic table. So this we call a periodic table, complete periodic table. Now you can see this is the first hydrogen and this one is the last atom. So here I will show you later what are the names of these elements. Now let's see the color coding. You can see some are yellow, some are gray, some are green. So if you see these yellow ones are the alkali metals. You can see these group 1 elements, these are the alkali metals. Next this grayish one is the alkaline earth metals. So these are the alkaline earth metals. Next here we have lanthanides. So these are the lanthanides. After that, we have actinides, transition metals, some other metalloids, non-metals, halogens. All these things we will learn in the later lectures. Now, one thing that is important is to know that how to represent the element or how to read the element from a periodic table. If you see a periodic table, you can see this is called atomic number. So that many protons it has in its shell. So for sodium, the atomic number is 11. Now here it is the elemental symbol. Here we have element name, and at the bottom we have atomic weight. So you can see this atomic number, element symbol, element name, atomic weight, or 4 details or 4 parameters in each box here. Now I'll tell you what is the need of learning periodic table. So as every language has its own alphabets, periodic table is the base of chemistry. To learn chemistry, if you want to grow in chemistry, you have to learn periodic table. Now in any kind of interview, if you are a chemistry major, then you need direct or indirect application of periodic table or its properties. And of course, I have to mention that in all kind of competitive exams, especially in inorganic branch, you need to know or you need to learn this periodic table. And one of the most interesting thing is that even during this PhD presentations or PhD comprehensive exams or PhD entrance exams or even after that for postdocs, sometimes these examiners will ask you direct or indirect questions from periodic table. And I have personally seen this that examiners ask direct questions, even from the halogens they will ask questions. So normal basic questions also they ask. Now next we are going to say that what type of questions are asked in interviews, what type of questions you can expect. For direct questions, you need to know all extreme and exceptional cases. For example, heaviest metal, lightest metal, or the metal which has most number of isotopes, these kind of things. See highest, lowest, longest, hardest of any property and exceptions of those properties. So we will discuss this later in the later lectures. Now, yeah, questions related to isotopes, especially isotopes of hydrogen and carbon. And you also remember or take a note that tin has most number of isotopes, that is 10. Questions related to qualitative values of periodic trends. For example, trend of oxidation potential of chromium, molybdenum, and tungsten. These things they can ask. Maybe you don't have to say the specific number in this case, but you have to say that what will be the trend, which will have the highest and which will have the lowest value. Okay. So next we are going to show various different forms of periodic table. I'm sure you all have seen one periodic table, that is the modern version, the most accurate one. I'm going to show you the other different versions. Just out of curiosity, I'm showing these things. I hope you guys will enjoy these things. So let's see what are the other types of periodic table present there. So first we are going to show Corvino's right state periodic table, which came in 1928. So this is the Corvino's right state periodic table. It was published in the same year as Janet's left state formulation. Corbino saw if blocks shifted by corresponding value of quantum number L, then the rows represent electronic shells. So you can see, so there S means L is equal to 0, then P block comes means L is equal to 1, then D and F. So like that, from S, P, D, F, they have, Corbino has arranged these elements. Now next, this one is the racetrack periodic table. Chemist and sci-fi author John Clark created this racetrack periodic table in 1933. Now you can see, here we have hydrogen, then helium, then lithium, beryllium, boron, carbon, nitrogen, oxygen. Again, we have fluorine here, then neon. Like that, it goes round and round, round and round. That's why it is called racetrack periodic table, like a racetrack, Formula 1. Next, we have Akimov's system. So Akimov's system took the form of a cross-section of pyramid, and he based his system on the principle that the lengths of the periods and analogies in properties between the elements of these periods must be clearly demonstrated. So you can see, here we have hydrogen, and this side we have helium. Then lithium comes this side, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And you can see this one is going like this: hydrogen, then lithium and sodium, then here potassium and rubidium, and then here cesium. So this one is going like a cross-sectional pyramid. Next one is the spiral periodic table. So one of the Bentley's publications in chemistry was a model of an extended periodic table, sometimes referred to as periodic snail. So this is referred as periodic snail. So this is same, just extended version of this racetrack periodic table. You can see hydrogen here, then helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, and it goes like this, and after that it comes here in the D block elements, and again it goes here, the S and P block elements, and after this D block elements, you can see it will go to the F block elements, and these F block elements are here, lanthanides and actinides. This is also referred as periodic snail. Next one is the curl-driven periodic table. So it was created by James Franklin Hyde in 1975. So this is also another extended version of that racetrack periodic table, and you can see it starts from here and all the way it goes there, and here we have the D block elements this side, and after that going here, these F block elements comes this side. So these are the different versions of a racetrack periodic table. Next we have Mayan periodic table. So the Mayan periodic table of elements named for its similarity to the ancient Mesoamerican calendar. It shows electron shells as concentric circles. Each row in the tabular form is shown as a ring. So you can see here we have hydrogen, then helium, and then lithium, beryllium as a ring. And again, if you take from sodium to argon as another ring, you can see another ring. So it goes as a ring and ring. Again, you have to start from potassium, and you will get another ring, pale potassium to krypton, and again from rubidium to xenon, you will get another ring like this. So it goes like ring wise. Next, we have the Adoma periodic table, so which came in 2006. So it was proposed by Worley Shimmerman. It is based on the Janet or left state periodic table. It consists of 4 blocks S, P, D, and F corresponding to quantum numbers L is equal to 0, 1, 2, and 3. So if you can see the S block elements are here. So you have to start from here. You can see hydrogen and helium. Then you have to come to the P block elements. So it will be like hydrogen, helium, lithium, beryllium. Then you will come here boron, carbon, nitrogen, oxygen, fluorine, neon. Similarly, when you have S, P, and D, so first you will come here sodium, magnesium. Then you will come here aluminum, silicon, phosphorus, sulfur, chlorine, argon, and then you will come here for the D block element, scandium, titanium, all these things. So first you have to fill this S block, then you will fill this P block, then you will fill this D block, and after that you will go here and you will fill this F block. So like that, it is that consisted of 4 blocks. Next we have this nucleosynthesis periodic. So a version of the periodic table indicating the origins, including Big Bang nucleosynthesis of the elements. All elements above 103 are also man-made and are not included. So this periodic table tells how these atoms got originated. So you can see this hydrogen and helium mostly from Big Bang fusion. So if you see this color, that tells it is coming from Big Bang fusion. And this one is cosmic ray fission. And this color, if you see this strontium, yttrium, these are having most greenish. They are coming from dying low mass stars. Again, this color, if you see, it is coming from merging neutron stars. So all these different colors, or this ratio of the colors, they say how much percentage of this atom is coming from merging neutrons and how much percentage of this atom is coming from dying low mass stars. So this is a different type of periodic table. Now next we have Wies's tetrahedron. So Dimitri Wies shows how it is possible to go from the Janet periodic table formulation to a tetrahedral formulation. So this is just another type of block periodic table, but he arranged it as a tetrahedron. So you can see these are the S block elements, then we have the P block, then we have D block here, and at the end we have F block. So all these blocks can be arranged as a tetrahedron. So where we have S blocks on the top, then the bottom layer comes the P block, after that the layer comes the D block, and the last layer comes as a F block. Next, another interesting one is the Pizza-Lunker's circular periodic table. So you can see this periodic table is made like a pizza. So this one is hydrogen and helium, and then we have lithium, beryllium here, and boron, carbon, nitrogen, oxygen, fluorine, neon this side. So first you fill the S blocks this way, and then you fill the P blocks like this way, and then you fill the D blocks like this way, from here to here, here to here. But inside the D block, we have F block elements. So that's why we have to fill the F blocks this way. Next one is the Adoma periodic table class Q. So you can see the periodic table is has been fitted inside this glass cube. The Worldly Schimmermann of the Adoma periodic table and the Adoma tetrahedron has now used these ideas to produce a beautiful glass cube. Next one is Janet Rajuni. So this is also another kind of periodic table where this is also kind of that block periodic table, and you have S blocks here, then we have P blocks here, then we have D blocks, and then we have F blocks. Next one is the Adoma periodic table and normal. So the Adoma from here resembles the normal distribution or bell curve. So you can see like this bell curve, bell shape. So how to fill? So you have to fill it here, hydrogen and helium, then lithium, beryllium. Then you have to go here for the P block, boron, carbon, nitrogen, oxygen, fluorine, neon. Again, after, so you have to fill this S block here, then you have to fill the P block. After that, you will fill the D block like this, and then you will fill the F block like this, and you will stack on top of each other. Next one is Nauma's Boyobu Janet periodic table. So a Japanese school teacher, I'll show him, and he has made a lot of periodic tables. I'll show some more later. So he designed this Janet form of periodic table in the traditional Japanese Boyobu style. So this is the Japanese Boyobu style, and you can see that S block and P block elements are here, this side, and then we have D block elements, then we have F block elements. So this one is called Boyobu style. Next we have clock phase periodic table. So this is Professor Martin Polyakov. He's a very famous professor as well as a YouTuber. So he had made this clock phase periodic table. So in 2014, Professor Martin Polyakov showed us a working periodic table clock. The designer of the clock is Nagayasu Nama, a Japanese school teacher. So here you start from here, hydrogen, helium, lithium, and you will all the way you go from one end to other end. And then you get the F block elements, and you will go again like this. So it's a kind of clock periodic table. Next one is the Sensu or fan periodic table. So Nagayasu Nama, as I was mentioning, that Japanese school teacher, he made various kinds of periodic tables, and one of them are this Sensu or fan periodic table. You can see it starts from here, hydrogen, helium, lithium, beryllium, then it goes all the way here, and after that it goes here for the D block. It starts here and it goes all the way, and then you start the F blocks from here and you go all the way. So it's kind of fan periodic table. Next one is the clock prism periodic table, and this one is the Braille version. So for those who cannot see, they can touch this and they can feel the periodic elements. That's why it's a Braille version of clock prism periodic table. So Nagayasu Nama, that Japanese school teacher, he has made a lot of periodic tables, and he has a homepage where he showed all his inventions and innovation regarding these periodic tables. You can go and visit. You can type Nagayasu Nama, you will find his homepage, and you go and check all these periodic tables. He is the man, Nagayasu Nama. Next one is Moran's periodic spiral. So Jeff Moran has updated his 1999 periodic spiral, and it looks like this. Now how to interpret it? You see hydrogen is here, then helium, then lithium. So hydrogen, helium, lithium, beryllium. Then you have to find the boron, and you can see boron is here. Boron, carbon, nitrogen, oxygen, fluorine. Again, neon is here. So this is kind of complicated, but if you really see it carefully, you can find that it's a spiral kind of thing. So you have to start from here, or you can see this line. Start from here and go like this, this, and again you come here and go like this, then you will get neon, then again come here, the sodium, magnesium, and then you come all the way down, go like this, and you will get aluminium, silicon, phosphorus, sulfur, chlorine, then you go to argon, and then again you come to potassium, calcium. So it is kind of spiral. It's a very different kind of arrangement. You just take a proper look, and you can understand this one. Next we have Stewart's periodic table. So P.J. Stewart has mapped a periodic table onto a sphere. So on the surface of the sphere, he mapped this periodic table as blockwise SPDF block, and then it looks something like this. If you see, these one are the S block elements. Here we have P block elements. On the side of that, we will have D block elements, and then we will have F block elements. Next, we have another kind of periodic table, that is Simpson's 4-dimensional version of the Adoma periodic table. So this is also kind of same block kind of thing. But how they are doing? You can see these S block elements are here, and then in this first layer is the S block elements, and then we have P block elements on the back of this S block layer. Then we have D block elements back of this P block layers, and then we have F block elements back of the D block layer. This is kind of 4D version. Next one is Nama's 3D octagonal pillar. So this is kind of same thing. You can see hydrogen, helium, lithium, beryllium, boron. Just like a pillar, he just so kind of go around this pillar, lithium, beryllium, boron, then go in the back. You can see the back, carbon, nitrogen, oxygen, fluorine. Again, you will go here. So this is kind of 3D octagonal pillar, means on top of a pillar, you are writing these elements in a swirl motion. Next one is Nama's VET periodic table and hourglass. So this is a very interesting periodic table, and I will show you in the next slide how the electronic filling is happening there. So this is the same thing we see. This is also blockwise, S block elements, and then P block elements, and then D block elements, and then F block elements. But I will show you how this electron filling is happening. He has shown in this hourglass periodic table. So watch it out carefully. So hydrogen, helium, I'll go back. I will start again. You see the electron filling. So for hydrogen, there is half filled, then helium, two filled, 1s2, then 2s1, 2s2, then 2p1, 2p2, 2p3, then 2p4, 2p5, 2p6. So all these elements, you can see the filling, how this is happening. Then again 3s, 3p3, 3p4, 3p5, 3p6. Just see the filling of electrons here. You can see all these electrons, how it is filling one by one. And now we are filling this F, 4f, now 5d. So you can go back and you can try to realize how this electron filling is happening. You can just tap in the video and go back and see it again. So this, they have also at the end showed how in the future that other elements are possible to come. Now next one, we have the periodic table of element scarcity. So in this table, they have mapped what is the abundance of the elements. So for example, if you see this green one, this means that is plentiful supply, that has plentiful supply. Hydrogen, sodium, potassium, calcium, it's the abundance is more in nature. Now if you see the yellow ones, that has limited availability, future risk to supply. If you see vanadium, scandium, manganese, nickel, copper, these are the yellow ones. These white ones are the synthetic ones. There are some more, and you can see this technetium that is in white color. This gray one, that from conflict minerals, you can see here, tantalum, gold, and this mobile sign. These are the elements that are used in the smartphones. So you can see gold, tantalum, tungsten, tin. These are used in the mobiles, as well as these ones F block elements, D block elements. Some of the D block elements also you can see cobalt, nickel, copper, gallium, all these things. Even these P block elements, carbon, silicon, oxygen. These are used in the mobile phones. Now let's come to the availability. And if you see this orange color, that means rising threat from increased use. So if you use more and more, so that will become threat to human being. So you can see these ones: europium, osmium, ruthenium, palladium, platinum. And this red one is that serious threat in the next 100 years. So these red ones are very, the scarcity is more. So if you take strontium, yttrium, these are very less in amount, and it can be finished within next 100 years if you use more and more, right? Now next we have Stewart's quantahedron formulation. So this is also another kind of 4D periodic table, and you can see this S blocks, P blocks, D blocks, and F blocks. These are arranged as a quantahedron. So this is kind of also 4D arrangement, same as that. Now next is the periodic table of chemical bonds. So this one we owe to mathematicians at the Max Planck Institute, who investigated almost 5,000 substances containing two elements in different proportions. Each circle in this hypergraph represents the bonding an element establishes with an organic residue. The bonds are then ordered by their polarizability, where more polarized bonds place the element higher in the graph. Here, two elements can be compared either through a direct arrow. Example, the bonds of hydrogen, for example, are more polarized than those of boron. So you can see these are the bonds. These are the bonding between the hydrogens, and this hydrogen is on top. That means it is more uh, polarizable, and then or by the chain of arrows between them. For example, the oxygen bonds are more polarized than those of bromine. So if you see bromine is here, and oxygen, so oxygen is here. So these oxygen containing bonds are more polarized. So either you can compare the position of the atoms not linked to each other, or you can see the atoms, those are linked to each other through an arrow. That means they make elements together, so binary elements. Whatever is on top, that has higher polarizability. This is also a very interesting way to show the elements. But yeah, this took a lot of efforts to analyze all those 5,000 substances. Next, we have rainbow periodic table in NOMA, and so this is kind of same as just let me see. Yeah, S block elements are on top, then P block element, then we have D block element, and the last layer we have F block element. Next one is this NAWA's rainbow periodic table, and you can see. So a lot of information is given in this rainbow periodic table. That means he has done a lot of color coding, and he has said what is the meaning of these color codings. You can see this K, L, M, N, O, P, Q, R shells. So where this last electron is going, accordingly, these color codings will be done. For example, you can see in hydrogen, the last electron is going to the 1s, that means K shell. So it is, that's why red in color. The helium is going to 1s2, K shell. So that is also red in color. Then we have orange in color, this lithium, beryllium, boron, carbon, all these are orange in color. So these are the, if you see the symbol, you can see this much of information is given here. and also the type of the elements also given here. So have a careful look and try to understand what are the informations given here. Next one is the NAVA's multi-periodic table that came in 2021. So this is actually a complete circle. I try to show it in two parts so that it is properly visible to you, but it will be actually complete circle. If you go and see his website, you can see it is a complete circle. And this arrangement is also kind of a clock. So you start from here, hydrogen, helium, lithium, beryllium, boron, carbon, and you go all the way to this one, and then you come to the F block elements, and again you come this way, and then after this you have to come this circle. Yeah. So this is a complete one full circle. So I have cut it down just to show it in better way. And yeah, you can see these color codings as well. So when it is found of discovery, according to that, these are the color codes, and these are also time. I'll zoom it in. You can see, oh shit. I'll zoom it in, and you can see according to the timing when it was found, when it was discovered, he has color coded all the elements. And here in this in this part, he has color coded all the elements according to the abundance in Earth's upper continental crust, Earth crust. So this one and this one are also different kind of periodic tables that people have come up with, and this one is kind of looks like a mobile game, right? This one is also another 3D periodic table. This one is also kind of a periodic table. There are a lot of variations available, and people came up with their own ideas, own uniqueness, and they make these different kind of periodic tables. So this much was for this first lecture. Hey genius, welcome back to the second lecture of periodic table and periodic trends. So in the previous lecture, we discussed about what is periodic table in chemistry, what is the need of learning periodic table, what type of questions are asked in interviews, and then we have seen various forms of periodic tables. In this current lecture, we are going to learn about the history of progress of periodic table. So just let me take the laser pointer. So we will start with Law of Triads, which came in 1829. Then in 1850, we got to know rule of integral multiple. Then in 1862, Law of Telluric screw came. Then in 1864 to 66, in this range, Law of Octaves came. And after that, we will discuss about the limitations of Law of Octaves. Then we will show important things on Mendeleev's periodic table. We will also compare the properties of group 1A and 1B elements. After that, we will discuss usefulness of Mendeleev's periodic table and defects in Mendeleev's periodic table. So these many things we are going to learn in this second lecture. So without wasting any time, let's start. So we are going to start with history of progress of periodic table. So in 1789, Anthony Lavoisier published a list of 33 chemical elements, grouping them into gases, metals, nonmetals, and earths. So this was the fundamental start of this periodic table, or the journey of this modern days periodic table. That was started in 1789. In 1829, we came to about Law of Triads. So Dobeiner observed that when arranged by atomic weight, the second member of each triad was roughly the average of the first and third. Now let's see by example. So if you arrange by atomic weight, the second member will be roughly the average of first and third. So if you take this lithium, sodium, and potassium, so you can see the atomic number of 7 and here 39. So if you sum those two, you will get 46, and if you take the average, it will be 23. So lithium, sodium, and potassium in this triad, you can see the second member, sodium, that has atomic weight or atomic number average of this lithium and potassium. Similarly, in case of calcium, strontium, and barium, we can see that if you sum this calcium atomic number and barium's atomic number, if you divide it by 2, you will get roughly the atomic weight of the strontium. And these are some other examples. Not exact, but close number you will get. Next, German chemist Leopold Melin worked with this triad system, and by 1843, he had identified 10 triads, 3 groups of 4 and 1 group of 5. So this grouping was done based on the elements' nature, physical and chemical natures. Because at the initial time, they did not have any clue how to arrange these elements. So they started arranging them, they started grouping them based on their physical and chemical properties. For example, sodium, lithium, and potassium, they had common properties. That's why the scientists thought they can be in one particular group. Next, in 1850, this rule of integral multiple came. So Patenkoffer pointed out that the atomic weights of the chemically similar elements differ by an integral multiple of 8. So let's see the examples. For example, if you take this triad, lithium, sodium, and potassium, you can see the atomic weights are 7, 23, and 39. If you subtract 7 from this 23, you get 16. And if you subtract 23 from this 39, you will get 16. So that is the multiple of 8. Similarly, if you take this series, oxygen, sulfur, selenium, and tellurium, then you can see, if you see the atomic weights, these are also integral multiple of 8. So that's why he pointed out these atomic weight differences are integral multiple of 8. So that was also a key finding. Next, in 1862, Law of Telluric screw came. So it stated that the elements differing by 16 units in atomic weights among the successive members form a family of similar elements. So this has similarity with the rule of integral multiple. So in the integral multiple, it was said that the difference, atomic number difference, is the multiple of 8. And now here it is saying that the atomic weight difference is by unit of 16, which is also a multiple of 8. So Jancotis placed the elements in order of increasing atomic weights on the surface of a regular cylinder, whose surface was divided into 16 equal vertical columns. Then a helix making 45-degree angle to the axis of the cylinder was drawn. The atomic weights were plotted vertically along the spiral line. In this arrangement, the chemically similar elements fall in a particular vertical column, and the successive members in the group differ by 16 units in atomic weight. The helical arrangement looks like a screw. That's why it is referred as the law of Telluric screw. Now I'll show you the structure, how it looks. And if you see, this is the helical system, and they have made this 45-degree arrangement. If you see here, 16 equal vertical columns at 45-degree angle. So all these are the vertical columns. These ones are the vertical columns, and they have placed the elements one by one. So here you can see lithium, then beryllium, boron, carbon. So if you see the chart, so this wise, so from here to here, it is 16 columns. And when there is oxygen, in the backside also you will get oxygen here, and again you will get this one. So it's kind of a screw type of arrangement. And it was observed that the elements of similar nature, for example, lithium and sodium, or if you take this boron and aluminum, carbon and silicon, they have the atomic number difference of 16. So that was a major observation. Next, in 1864 or 1866, in this range, this law of octaves came. So elements are arranged in order of increasing atomic weights. All 8 elements have similar properties. So Newland gives this law of octaves, and he said that all 8 elements have similar properties. So all those elements, whichever were known at that time, they have arranged according to the atomic weight. For example, if you see here, lithium, sodium, potassium. So if you go like this, if you arrange these atoms from top to bottom, and then next from here to here, so you will see these lines, these elements are similar in properties. Now let's talk about the limitations of law of octaves. So though the octave rule works well for the lighter elements, it is deviated for the heavier elements. So this law of octave does not work in case of higher atomic number elements or the heavier elements. And make sure to remember that this, in case of this law of octave, the elements were arranged according to the atomic weights, not atomic number. It was according to atomic weights. Now inconsistencies exist because at that time available atomic weight data were not totally correct. So because they had some limitations in taking the proper atomic weight data, that's why that some inconsistencies were there. And atomic weight is not the principal property. Two different elements, which are different atoms, they may have same atomic weight. For example, argon and calcium. So they have same atomic weight, but they have different atomic numbers. So just make sure to remember this atomic weight is not the inherent property of an atom. Atomic number is the one which is the inherent property of an atom. So next, near 1868, Mendeleev and Lothar Meyer, so these two renowned scientists, Mendeleev and Lothar Meyer, so they independently noticed the properties of elements are periodic functions of their atomic weight. And then they independently tried to come up with their periodic table. But Mendeleev got most of the credit. And in 1871, Mendeleev published his short periodic table. So this one is the original Mendeleev's periodic table. And till that time, only a few elements were known. And all these 118 elements that we know now, it was not known at that time. Now let's learn about important things on Mendeleev's periodic table. So in Mendeleev's periodic table, it was 7 periods and 9 groups. If you see here, so these rows are called periods, these rows, and these columns, they are called groups. So in Mendeleev's periodic table, there were 7 periods and 9 groups. So in first period, only 2 elements were there, and that is called very short period. So in the second and third period, 8 elements were there in each, and these were called short period. In fourth and fifth period, 18 elements were kept, and those were called long period. And in sixth and seventh period, 32 elements were kept in each period. So these are called very long period. Now each long period is divided into even and odd series. Zeroth group contains inert gases, though it was absent in the original Mendeleev's periodic table. So at that time, right now, the inert gases are in group 18, but at that time, it was called zeroth group. Now group 8 contains 3 elements of close atomic weights in one place. For example, iron, cobalt, nickel, and ruthenium, rhodium, palladium. These three elements were housed in the group 8. For example, you see here, iron, cobalt, nickel. they are kept in group 8, and ruthenium, rhodium, palladium, they are also kept in group 8. You can see osmium, iridium, platinum, they are also kept in group 8. Now correction of atomic weights were done, and so that Mendeleev became successful to determine the correct atomic weight in some cases. For example, beryllium and indium. So that time when they were doing this research, that time there was some issue with the correct measurement or precise measurement of atomic weights. So when he was putting these elements, so in his chart, so that time while when they saw that chemical nature or the physical natures are matching, so in that respect he can put beryllium in this position, and also he can put indium in the respective position, and in that way it was automatically they could assume the atomic weight of this beryllium and indium. So the correction was done by Mendeleev. Now prediction of missing elements. So at that time of Mendeleev, they had only 63 elements known. Now to maintain the order of atomic weight, he had kept some vacancies, so which inspired the discovery of new elements. For example, scandium, gallium, germanium, technetium. So all these elements were not known at that time. So he kept vacancies, and in that vacancy, people assume that yes, some other atom can be there. So that inspired to find out more and more atoms. Now this is the modern version of Mendeleev's periodic table. Next, we will do the comparison of the properties of group 1a and 1b. So for that, you can see, so this group 1 is are called alkali metals, and that time group 1b were called coinage metals. So you can see the outermost electronic configuration is ns1, and here n-1d10 and ns1. So valency, group 1a elements had valency 1, whereas this group 1b metals, they had different valencies. For example, copper had 1, 2, sometimes 3, silver had 1, sometimes 2 and 3, gold also has 1 and 3. Now if you compare the state of occurrence in nature, so these group 1 elements, they exist in compounds and never exist in free state, whereas group 1b, they exist both in chemical compounds and free state. Now if you compare the electropositive character and reactivity, so group 1 elements, they are highly electropositive in character and highly reactive, whereas group 1b elements, they are less electropositive in character and the decreased activity makes them noble metals. If you see the bonding nature, so group 1 elements used to form ionic bonding, whereas group 1b elements, due to the higher polarizing power, they introduce more covalency in their bonds. Now nature of oxide and hydroxide, this group 1a elements used to form highly alkaline materials, whereas these group 1b, they form slightly alkaline compounds. Now if you see complex compound, so in case of group 1a, no marked tendency is noticed to form coordination compounds. Only some complexes with the oxygen donor are reported. And in case of 1b, a marked tendency to form coordination complexes is noticed due to the ligand field stabilization energy, except for +1 oxidation state. So these things, these electronic configurations or ligand field stabilizing energy, these things I'll discuss later in some other chapters. So for the time being, you can try to understand what are the differences between this group 1a and 1b compounds. Now if you see the color of the compounds, the group 1a elements, they generally form colorless compounds because of the absence of ligand field band, that is DD transition, and charge transfer band, metal to ligand or ligand to metal charge transfer. Now in case of group 1b, those compounds are generally form colored compounds due to the presence, sorry, those molecules, so they generally form colored compounds due to the presence of the ligand field band and charge transfer band. Now if you see that hard soft principle, from there you can see this group 1a elements, they are hard acids, whereas this group 1b elements, they form soft and borderline acids. Now if you see the structure of metallic crystals, group 1a elements, they adopt the BCC, body centered cubic structure, and possesses low cohesive energy, giving rise to low melting points and density. Whereas this group 1b elements, they adopt the FCC structure and are highly malleable with a higher cohesive energy, higher melting point, and higher density. So these things you can take a note if you need. So we have discussed about the importance of Mendeleev's periodic table. Now we are going to discuss the defects in the Mendeleev's periodic table. So each coin has its two sides, right? So for example, the reverse atomic weight order in some cases were observed in Mendeleev's periodic table. Though the elements are placed in the order of their increasing atomic weights, in some cases the trend is reversed. So there are 4 such pairs. So you see iodine and tellurium. So iodine had lower atomic weight compared to tellurium, but iodine was placed before tellurium. Similar to that, potassium and argon. Potassium had low atomic weight, but it was placed before argon. Nickel had the lower atomic weight compared to cobalt, but it was placed before cobalt. Now next defect was triads in group 8. So in group 8, there were 3 elements which were sharing that space, right? So though the different elements are separately housed in different rooms, in group 8, the 3 elements, that is iron, cobalt, nickel, and in the next period it was ruthenium, rhodium, palladium, and in the other period it was osmium, iridium, platinum. Those were placed in each of the single rooms of the period 4 to 6. The members in each triad are not similar in terms of properties, but still, because of the absence of suitable vacant rooms, they were placed in the single rooms. Now, the next one is subgroup elements lacking in similarities. So each group was subdivided into A and B subgroups. But in the long periods, similarity in the properties of the two subgroups is hardly found. For example, the alkali and coinage metals are widely different in properties, as I have shown in the previous slides. That comparison of 1A and this one, comparison of 1A and 1B elements. So they are kept close to each other, but they have completely different properties. Next one is the positions of isotopes and isobars. So according to the placement in the order of atomic weight, the isotopes should have different positions, while the isobars, so this isotope means you have, so if you see the isotope, that means you have same number of proton but different number of electron. So that means your atomic weight will be different. And isobars means you have different number of protons but same number of total atomic weight, means atoms of the different elements, but the atomic weight is same. So the both proton and neutrons might be different, but their summation, the atomic weight, will be same. Those are called isobars. So these isobars should be placed in the same row. So this was not justified in Mendeleev's periodic table. Next was group valency. So though the group number indicates the highest possible valency state, that is in case of oxygen valency, it might be 8 of the elements except ruthenium and osmium of group 8. No one in the group shows the valency 8. So if you see, so the highest possible valency was denoted from the group number, but in reality, they don't show that much of valency. Now, missing link between the group 7b and group 1a elements. So transition from the highly electronegative halogens to the highly electropositive alkali metals through the inert gases can hardly be rationalized in terms of atomic weights. Next one was the relative stabilities of oxidation states. So the relative stabilities of the different oxidation states of an element cannot be interpreted from its group position and atomic weight. Means the stability of the oxidation states you cannot predict from this Mendeleev's periodic table. Peculiarity of the lightest congener in each group. So the first member of each group is drastically different from the other members of the group. For example, if you see the periodic table, you see helium, neon, argon, krypton, or this hydrogen, lithium, sodium, potassium. So in this group, the hydrogen has drastically or dramatically different properties compared to the other elements. Similarly here, in case of beryllium or boron or carbon, so they have different properties compared to rest of the elements in this group. Next was the diagonal relationship. So the existence of diagonal relationship for the short period elements can hardly be rationalized in terms of atomic weights. So this diagonal relationship we will explain in later lectures. Position of lanthanides and actinides. The position of lanthanides or actinides in a single room cannot be properly understood in the Mendeleev's periodic table. The next one is uncertainty in the prediction of the number of missing elements. So the successive members in the periods differ in atomic weights by different extents, that is 1 to 4 units. Hence, it is difficult to predict the number of missing elements present between the elements whose atomic weights are known. Because of the fact, it was difficult to predict the exact number of lanthanides and actinides from the knowledge of atomic weights. So if you know two elements and that has higher atomic weight gaps, so you cannot predict that how many more elements will fit in between those two elements, right? The next one is the position of hydrogen. That was also arbitrary. Now the position of hydrogen creates a confusion as it has similarities in properties with both the group 1, that is alkali metals, and group 7b, that is halogen elements. Now different capacities of the periods. So the different capacities, that is in first period it was 2, in the second and third it was 8, then fourth and fifth it was 18, and then sixth and seventh it was 32. So the different capacities of the different periods to house the elements cannot be rationalized from the Mendeleev's periodic law. So these were some of the defects in the Mendeleev's periodic table. So actually they developed the formulation of periodic tables, and Mendeleev gave a huge milestone in the formulation of this periodic table. So this much for this lecture. Hey genius, welcome back to the third lecture of periodic table and periodic trends. So in the previous lecture, means in the second lecture, we have learned about history of progress of periodic table. In that second lecture, we discussed about law of triads, rule of integral multiple, law of Telluric screw, law of octaves, limitations of law of octaves, as well as we have discussed some important things on Mendeleev's periodic table, comparison of properties of group 1a and 1b in Mendeleev's periodic table, and we have also discussed some usefulness as well as defects in the Mendeleev's periodic table. So these many things we have already discussed in the lecture 2. So if you have not seen the lecture 2, please go and watch it. And in this lecture, we are going to learn about discovery of noble gases, discovery of atomic number, the modern long form of periodic table, and advantages as well as defects in the long form of periodic table. And towards the end, we will briefly discuss about Bohr's classification based on electronic configuration and the Actinide hypothesis. So without wasting any time, let's start. So the discovery of noble gases came into the picture in the time of 1894 to 1898. Using two different methods to remove all known gases from air, Ramsay and Rayleigh were able to announce in 1894 that they had found a monoatomic, chemically inert gaseous element that constituted nearly 1% of the atmosphere. They named it argon. So Ramsay discovered argon in 1894 with Rayleigh, and after that he discovered krypton, neon, xenon in 1898 with Maurice M. Travers. And another noble gas element, radon, was discovered in 1898 by Frederick Ernst Dorn. Now in 1913, discovery of atomic number was done. So in 1913, Moseley discovered that atomic number instead of atomic weight is the fundamental property or the identity of an atom. So based on this, he proposed his periodic table. So basically, he had worked on characteristic X-ray and atomic numbers. So before this time, so scientists and researchers, they were arranging the periodic table according to the increasing order of atomic weight. But atomic weight is not the sole identity or inner property of an element. Actually, the atomic number, that is the indistinguishable, or that is the main property of an atom. So that's why Moseley first said that atomic number he discovered first, and that is the fundamental property of atom. Now, in 1922, the modern long form of periodic table came into the picture. That is also known as Bohr's table, because Bohr created his own version of this table in 1922, and based on experimental measurements of electron energies, along with some guidance from the periodic law. So Bohr's table added elements discovered since 1869. Now let's see the modern periodic table. So this is a version of modern periodic table where you can see we have 7 periods. So if you see these rows, these are actually called as periods. Row wise, these are called periods. And if you see the columns, those are called groups. So in the modern table, there are 18 columns or 18 groups and 7 periods. Now we have metals on the left hand side in this periodic table and non-metals in the right hand side. So these are the non-metals. So I will say these things in details in the later lectures. But for the time being, you just know that this is the borderline. These are called metalloids, which consist some property of metals, some property of non-metals. These right hand sides, they are called non-metals, whereas left hand side portion is called metals. Now these are the group 1 and group 2. They are called S block S block elements. Whereas if you see from group 13 to 18, these are the P block elements, and this group 3 to group 12, these are the transition metal elements. Whereas inside this group 3, we have these lanthanides and actinides. So these are called post-transition metal elements. So all these things we will see, or we will see more on these things in the later lectures. Now let's see the advantages of this long form of periodic table. So earlier in the other periodic tables, scientists were arranging the elements according to the atomic weight. Now scientists have started arranging the elements according to the atomic number. So the advantage is that no reverse order for placement in terms of atomic number. So by considering the more fundamental basis, that is atomic number, the problems of reverse order of atomic weights in placing the elements in the pairs, that is iodine and tellurium, potassium and argon, nickel and cobalt, so all these were removed. Now interpretation of properties in terms of electronic configuration. The gradual change in properties along the periods and groups can be interpreted by considering the electronic configuration, that is atomic number. No concept of subgroups and odd or even series. So the A and B subgroup, so which was in the Mendeleev's periodic table, so the convention of designation by A and B is arbitrary, but presently the metals are placed in B subgroup and the non-metals in A subgroup. So the A and B subgroup elements are placed separately. So now there is no A or B subgroups in this long form of periodic table. So hence the question of odd and even series does not arise. Splitting of triad positions. So we have already seen that in the Mendeleev's periodic table, in group 8, we were keeping 3 elements there. So we were calling it as triad. So now it has been removed. So though the triads are placed in group 8b, in terms of electronic configurations, they are separately grouped according to IUPAC convention. Now group 8 to 10 constitute these triads. So earlier in the Mendeleev's periodic table, we were housing 3 elements in group 3b. Right now we have separated them and we have given them particular groups, group 8, 9 and 10, to keep these triad elements. Next one is the positions of lanthanides and actinides. So the 14 lanthanides are not forced to be placed in a single room. In terms of electronic configurations of the 4F sublevel, the 14 lanthanides have got 14 rooms. The same thing appears for the actinides based on the electronic configurations of the 5F sublevel. So I'll go back in this periodic table, and if you see, so we represent that these 14 elements, all of these 14, 14, 28 elements are here, but actually the electrons are getting filled in the F level, so F orbital. That means if you expand this, then you can find that these 14 elements are housed differently according to their atomic number. So earlier there was no proper explanation that where to put these lanthanides and actinides, but now you can give proper explanation that as the electron is going and getting filled in the F sublevel, so these will be the F block elements, and they will be housed in different rooms. So these are called rooms or house, whatever you want. Now, prediction of valences and stable oxidation states. So in predicting the stable oxidation states, not the group number, but the electronic configuration is a much better criteria. So earlier we used to think that if one element is in group 3, then it will be having stable oxidation of +3. If an element is group 5, it will be having oxidation state of +5. But there was no reason of that. So now if you see the electronic configuration, from that electronic configuration, you can say that how many electrons it will use or how many electrons it will take. So because the electronic configuration or the atom will try to occupy a particular electronic configuration that will give its half-fill or full-fill nature. So those things also we will learn later. Now, interpretation of the capacity of periods to accommodate the elements. So the maximum capacity of each period to accommodate the elements can be understood in terms of electronic configuration. So as we have seen that in first period there are only 2 elements, in second period and third period 8 elements, fourth and fifth period 18, as well as sixth and seventh period 32 elements are there. But why these different number of elements in different periods? There was no justification. Right now, if you see in terms of electronic configuration, you can justify it. So if you see in first period, there is only one s. So one orbital is there. That's in one orbital you can accommodate maximum 2 electrons. That's why the maximum 2 elements can be there in first period. Now in the second period, we have 2s and 2p. Now 2s, so it has only one orbital s, but p has 3 orbitals, px, py, and pz. So for 2x we have one orbital, and for 2p we have 3 orbitals. So in total we have 4 orbitals. Now each orbital can accommodate 2 electrons. So 4 into 2, 8. So 8 different elements can be housed in second period. Similarly, in case of third period, we can accommodate 8 elements. And if you see the fourth and fifth period, so we have D, S, and P. So this 3D, it has 5 different orbitals, which we will show in the later videos. And S has 1 orbital, and P, it has 3 different orbitals. So in total, 5 plus 1 plus 3, so 9 orbitals are there. And in each orbital, we can put 2 electrons. So 9 into 2, 18 electrons, or 18 different elements can be there in fourth and fifth period. Similarly, in the sixth and seventh period, we have F orbital, D orbital, S, and P. Now F, it has 7 orbitals. So D has 5, S has 1, and P has 3. So in total, 16 orbitals are there. So if you multiply 16 into 2, because each orbital can accommodate at max 2 electrons, so we can accommodate 32 elements in the 6th and 7th period. Now we can give a proper logic that why these different periods have different elements or capacity. Interpretation of variable valency for the transition elements and fixed valency for the lanthanides. The common oxidation state +3 for the lanthanides arises due to the availability of 3 valence electrons in the outer levels. The differentiating electrons remain in the chemically inert N-2F sublevel. So let's try to understand. So what is happening when we are going to the lanthanide elements, lanthanides or actinides, the F block elements, the last electron that is going in the N-2F sublevel. For example, if you take cerium or praseodymium, the last electron will go to the 4F. Okay. But if you see the cerium's electron configuration, you will see it is 4F1, 5D1, 6S2. So although the last electron is going to the N-2F sublevel, means 4F, but it already has 1 electron in the 5D and 2 electron in the 6S. So that's why there are 3 electrons in the N-1D and NS. So these 3 electrons can be oxidized. So that's why they have a fixed oxidation state, these F block elements. So this +3 comes from the N-1D and NS. Whereas this N-2F, which is accommodating that variable number of electrons, that is kind of inert. In the same way, the common +2 oxidation state for the D block elements arises due to the NS2 electronic configurations. For the transition series, the N-1D sublevel in which the differentiating electrons are placed is not so inert. This is why the variable valency for the transition series is a common phenomenon. So in case of F block element, what was happening? The last electron was going in the N-2F, and we have total 3 electrons in the N-1D and NS. So only those 3 electrons which are in the N-1D and NS, those can be oxidized. That's why they had a fixed oxidation state +3. But there is a little bit different, and the case is a little bit different in case of D block or transition metal elements. What is happening? There, in case of that, the last electron is going in the N-1D, and NS has 2 electrons, NS2. So they definitely have this +2 oxidation state. These 2 electrons can go and give it +2 oxidation state. But at the same time, they can lose electrons from the N-1D as well, because this N-1D is not that much inert. If you provide proper amount of energy, this electron can also go out. So that's why they have variable oxidation state, +2 for sure, and they can have more +3, +4, +5 according to the availability of this N-1D shell electrons. Okay, fine. Now next one is the distribution of metals and non-metals. The state diagonal gives an idea of the distribution of the metals and non-metals. The metals exist at the left side of the stair step, while the non-metals are placed at the right side of the stair step. What I was mentioning while showing the periodic table, and this thing also I will clear in the later videos. Still, I will go and show it. Here, if you see this boron, silicon, arsenic, these things, boron, silicon, germanium, arsenic, antimony, tellurium, these are the metalloids. And if you take the left hand sides, those are the metals. And if you see the right hand sides, these are the non-metals. So this one is called stair step. And it is coming like this. So that's why it is called stair step. Clear? Now let's see some defects in the long form of periodic table. The first one is dispute in the position of hydrogen. The problem regarding the position of hydrogen is not settled satisfactorily. In terms of electronic configuration, 1s1, so hydrogen has only one electron, which is in the 1s orbital. So it is to be placed in the alkali metal group. The formation of H plus also supports its placement in the group 1, but it can also form H minus, means so negative charge, say H minus, like the halogens. For example, F minus, Cl minus, Br minus. Similarly, it can also form H minus in some compounds by taking an electron. So thus, it shows a similarity with the halogens to get placed in group 17. But in fact, hydrogen differs significantly from both the alkali metals and halogens. Next defect is the dispute in the position of helium. Again, the position of helium is not settled. In terms of electronic configuration, as helium has only 2 electrons, it goes into 1s, so 1s2 is the electronic configuration. It should be placed in the alkaline earth metal group, that is group 2. But from the standpoint of the chemical inertness, it is placed in the family of inert gases, in the group 18, having the general electronic configuration Ns2Np6. So this Ns2Np6 is like for the this is the common configuration for the other inert gases. But in case of helium, it is a little bit exception. There is no Np6, only Ns2, 1s2. Thus, from the consideration of the properties, it is to be placed in the group of the inert gases, while from the electronic configuration, it is to be placed in group 2. But ideally, it is in the group 18. If you see the modern form of the periodic table, helium is placed in the group 18. But still, ambiguity is there. The next one is the borderline elements. The borderline elements lie in the border range of two adjacent blocks, that is S block and D block, or F block and D block, or D block and P block, are having some properties common to both the blocks. Hence, the separation by a sharp line of demarcation cannot be justified in such cases. Next one is the detachment of F block elements from the main periodic table. The inner transition series, that is the F block elements, are thrown out from the main body of the periodic table. It indicates apparently that the members of this series do not obey the trends followed by the main body elements. Next one is the position of isotopes of lighter elements. The isotopes have not got separate rooms. For the heavier elements, the properties of the isotopes of an element are more or less the same. But for the isotopes of the lighter elements, the physical, kinetic, and thermodynamic properties are drastically different. For example, the isotopes of hydrogen, that is hydrogen, deuterium, and tritium, are so different in properties that to place them in a single room is really surprising. But these isotopes, as of now, are considered to be in the same room. Now, position not always determined by electronic configuration. In the D block elements, the missing of the groups having electronic configuration N-1 D4 NS2 and N-1 D9 NS2 do not have any explanation apparently. So if you see the electronic configurations of the D block elements, you cannot find these electronic configurations. The reason actually is half-filled, full-filled concept. So if you see N-1 D4 NS2, here a D orbital can accommodate 10 electrons, but it has only 4. And if you see this one N-1 D9 NS2, D orbital can accommodate 10 electrons, it is one shot, 9. So what it will do, so it will take one electron from here and it will fill the D orbital. So it will become N-1 D10 NS1. Similarly, it will also take one electron from here, it will go here and it will become N-1 D5 NS1. So this is called D orbital is half filled, and here D orbital will become full filled. So this half filled, full filled concept also we will learn later. So these two electronic configurations do not have any explanation apparently. Chromium and molybdenum are having the configurations N-1 D5 NS1, as I was saying, half filled. Here D is half filled, while tungsten is having the configuration N-1 D4 NS2. But still tungsten is placed in the group of chromium and molybdenum. So there is some discrepancy. So for example, chromium and molybdenum, they do this half filled and full filled concept, but tungsten is comfortable in having this D4 configuration without feeling its half filled nature, half filled D. So there is some discrepancy in the same group, but still this chromium, molybdenum, and tungsten, they are in the same group. In fact, the electronic configurations for the members of 5D series, that is 6 period, differ from their respective congeners of the 3D and 4D series in many cases. But the periodic table does not care for it. This drawback is the reflection of the drawback present in the Aufbau principle. Now, what is this Aufbau principle? That will be discussed in the later videos. Maybe in lecture number 6 or 5. Yeah, it will be discussed in the lecture number 5 or 6. You can go and check. A similar situation arises in the inner transition series also. Thus, it can be safely concluded that the heavier elements are placed in order of their increasing atomic numbers, not in terms of electronic configuration. Yeah, so the take-home message is that this periodic table, or the modern form of periodic table, that has been constructed based on the increasing order of atomic number. Neither increasing order of atomic weight nor by the order of electronic configuration. It has been formulated by only the increasing atomic numbers. That you have to remember. Okay. Now let's talk about Bohr's classification based on electronic configuration. If you see the inert gas elements, for these elements, the outermost S and P sublevels are fulfilled, having the electronic configuration Ns2 and P6. Thus, the zero group or group 18 elements are the members of this family. Helium is also included here because of the full-filled shell structure. These are generally chemically inert with respect to other elements. they generally remain as monoatomic species among which the weak London dispersion force operates. So these inert gas elements, they do not tend to react. So if you mix different gas and if you put inert gas there, so these inert gas elements will not it will not react with the other gases or other elements. Now if you see the transition elements, these are characterized by the incompletely filled n-1 d sublevels. Evidently, for these elements, the two outermost shells are incompletely filled. Now next one is the representative or normal elements. So these are characterized by the incompletely filled outermost shell. That is, the nth shell is partially filled, while all the other inner shells are completely filled. So these actually consist of the S and P block elements. So S and P block elements are called representative or normal elements. Now what are the inner transition elements? So these elements are having n-2f levels incompletely or partially filled, along with the partial filling of the n-1 d level and nth shell. So thus three outermost shells remain partially vacant in case of inner transition elements. Now let's talk about the Actinide hypothesis. So for the discovery and investigation of 10 transuranium elements, Professor Seaborg has earned a share of the 1951 Nobel Prize in Chemistry. Now what is this? So at the early days, thorium, protactinium and uranium were mistakenly placed in group 4b, group 5b and group 6b respectively in D block. So in 1944, Seaborg pointed out this incorrect assignment and he proposed these elements to be the members of a new inner transition series analogues to the lanthanides. So this new inner transition series was described as actinides in his famous Actinide hypothesis. So at that time, Seaborg was strongly criticized and warned not to publish his Actinide hypothesis because it would destroy his scientific career. So see, this thing sometimes happens that if you want to publish something, if you are arguing something, so you will be criticized. The other people who are more knowledgeable or who know more in their field, they will think that you are making a mistake. The same thing happened with the Seaborg. So everyone warned him that don't say that there are something like called actinides or there are some different groups. Don't dare to publish these things. It will ruin your scientific career. So sometime later, after publishing that, so he narrated the event humorously as, I didn't have any scientific reputation, so I published it anyway. So this is the greatness of great scientists, that you believe in yourself, what you are doing, and ultimately, even in the long form of periodic table, you can see these actinides below these lanthanides. So he was right actually, but at that time, people criticized him. So he used to make a humor about that, and he used to say that I didn't have any scientific reputation, so I published it anyway. The actinide hypothesis saved the chemistry from a wrong direction. Seaborg and his group had synthesized many elements of the second inner transitional series, that is actinides. So this much was here for this lecture 3. Hey genius, welcome back to the lecture 4 of periodic table and periodic trends. So this is the part A, lecture 4. So in the previous lecture, we have discussed about discovery of noble gases, discovery of atomic number, the modern long form periodic table, advantages as well as defects in the long form of periodic table, Bohr's classification based on electronic configuration, and the actinide hypothesis. So all these things we have covered in the lecture 3. If you have not seen that video, please go and check that video. And in this current video, we are going to discuss about the mnemonics for S block and P block elements. So this lecture 4 is divided into 3 parts, 3 videos. So in part A, we will discuss in this video S block and P block elements, mnemonics. In part B, we will discuss about the mnemonics for D block elements along period. And in part C, we will discuss mnemonics for D block elements along group and mnemonics for F block elements. So all these mnemonics, I will say one for Hindi, one for English, both in both language. So whichever you are comfortable with, you can remember that one. And some of the mnemonics are prepared by some other teachers or researchers. I have included those also, as well as some of the mnemonics are made by me. So all these I will show. Then you decide which one is easier for you to remember. And one more thing, to make these mnemonics, I will take help of some arbitrary stories. So you have to believe in those stories. So these stories may be irrelevant or wrong or not even true. So still you have to believe that these stories are true so that you can easily remember those mnemonics, right? So without wasting any time, let's start. So this is the modern periodic table, which is consisted of 118 elements. I have already discussed about this periodic table in earlier videos. You can check that. And in a brief, I will say that these 7s are the periods. So these rows are the periods. There are 7 rows in the periodic table. So that's why these 7 rows are called 7 periods. And these columns, if you see these columns, so these columns are called groups. So in total, there are 18 columns. Now, if you see this column 1 and column 2, or in other words, group 1 and group 2, these are called S block elements. And now come to this side, in the right hand side, you can see from group 13 to group 18. So these groups are called P block elements. And in between, we have from group 3 to group 12, these are called D block elements. And as a part of this, here we have this 14 lanthanides and 14 actinides. So these are called F block elements because the last electron will go to the n-2 F orbital. Now we are going to learn about the mnemonics of S block elements. So these many elements we will cover. So before that, let's see the periodic table, or what are the informations hidden inside the periodic table. So this is the periodic table that I have with me. So you can see different color codings, and if you just take one element, for example, if you take this chromium, you can see a lot of numbers are written in the left side as well as right side. So what is the meaning of those numbers? So just try to understand this. So I have this periodic table. You might have some different version, maybe more informations are there or different informations are there. But what are the informations given that will be mentioned in the periodic table? So if you see in this lower corner, it has been mentioned that what are the informations given in this periodic table along with the elements. Now let's see. So if you see this one is given for the aluminium, and for aluminium we have symbol. Along with that, if you take this corner, in the corner you can see atomic number. Then the lower one is the density in gram per ml. Next one is the atomic radius. Then this one is given as the melting point temperature and boiling point temperature in degree centigrade. And at the end, it is given the electronic structure. So this neon means neon has atomic number of 10, and the closest inert gas element to this aluminum is the neon, or the previous, I should not say closest, I should say the previous inert gas element is the neon. So neon has 10 elements, 10 electrons. So that's why all those 10 electrons you can put in the short form as a neon and then bracket. So it counts 10 electrons. Then it has 3s2, 2 electrons in the s orbital, and 3p1, so 1 electron in the p orbital. So in total, it has 13 electrons. So that is the electronic structure. Now come to the right hand side. See, in the right hand side, atomic weight is given. So atomic weight is the summation of proton and neutron, which is in the nucleus. Now this one is the electronegativity. Next one is the first ionization energy, and this is the most favorable oxidation state. And here also it was given the year of discovery, in which year this element was discovered. And name already you know the full name. And this one is the crystal structure. So what kind of crystal it forms. So some more informations are given here, that solids are shown in black, gases are shown in red, liquids are shown in blue color, synthetic elements are shown in orange, and this inside the element bracket and double star that indicates most stable isotope, and radioactive elements are marked by this symbol, this yellow black symbol. So all these informations are hidden inside this periodic table, which one I have. So if you go and check your periodic table, you can also find a lot of informations are hidden inside this periodic table, and it has been given for each and every element. So now we will start the mnemonics for S block element. So we will start with discussing the S block element and group 1 element. So in group 1 we have hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. So कैसे याद रखेंगे इसको? इसको ये याद रखेंगे कि दो लड़की हैं, बहुत अच्छी फ्रेंड है, बहुत क्लोज फ्रेंड है, हलीना एंड रूबी. तो वो दोनों बहुत बचपन से दोस्त हैं और बहुत क्लोज फ्रेंड है. तो बाकी लोग उनको देख के जेलस होते हैं. तो क्या होता है, क्या बोलते हैं लोग? बोलते हैं कि अरे वो देखो दोनों साथ में जा रहे हैं, या फिर दोनों साथ में खा रहे हैं, हर एक चीज साथ में कर रहे हैं. तो क्या होता है, हलीना की रूबी से फ्रेंडशिप. तो लोगों के जलने का वजह क्या है कि हलीना की रूबी से फ्रेंडशिप. तो हलीना में आ रहा है हाइड्रोजन, लिथियम एंड सोडियम, एक साथ में हलीना. की में आ रहा है पोटेशियम, क्योंकि पोटेशियम का सिंबल के है. रूबी से आपको पता चला कि रूबीडियम है इस पोजीशन में, और ये से हम रिप्रेजेंट कर रहे हैं सीजियम से. और फ्रेंडशिप का पहले है Fr, जो कि फ्रांसियम को रिप्रेजेंट कर रहा है. तो ये याद रखना है कि हलीना और रूबी बहुत अच्छे दोस्त हैं, लोग उनसे जलते हैं, और लोगों के जलने की वजह क्या है, हलीना की रूबी से फ्रेंडशिप. या फिर ऐसे याद रख सकते हो कि हलीना एक बहुत रिलीजियस लड़की है, वो बहुत मानती है, गॉड में बिलीव करती है. तो हलीना की रब से फरियाद, क्या हुआ, हलीना का कुछ प्रॉब्लम हुआ, तो उसने रब से जाके बात किया, मन्नत मांगी. तो रिलीजियस, एज अ रिलीजियस पर्सन गॉड से बात कर रही है वो. तो क्या है, तो हलीना की रब से फरियाद. तो हलीना में कवर हो रहा है हमारा हाइड्रोजन, लिथियम एंड सोडियम. की से आ रहा है पोटेशियम, रब से आरबी रूबिडियम, और से आ रहा है सीजियम, और फरियाद Fr, तो Fr से फ्रांसियम. ओके, नाउ लेट्स मूव टू द इंग्लिश वन. सो अभी क्या बोला था हमने, हलीना एंड रूबी आर वेरी क्लोज फ्रेंड्स. So one friend's name is Halina, the other friend's name is Ruby. So they are very close friends. What happened? Ruby was missing for some time. There was a party going on in the house, and Ruby was missing. So what Halina did? Halina kept his portion of chicken so that she can come back and eat, because they are very close friends, right? So that's why you can remember that Halina kept Ruby's crispy fried chicken. Ruby was missing. She was not coming. Ruby was coming late. So Halina kept her portion of chicken. So that's why you can remember Halina kept Ruby's crispy fried chicken. Now Halina, this one covers hydrogen, lithium, and sodium. And from kept is starting with potassium, K sign. So this K represents potassium. Rubies. So rubies, from ruby, you can remember rubidium. Crispy. So from this crispy, CS, you have to remember CS is a symbol of cesium. Crispy fried chicken. So fried, Fr represents francium. So Halina kept Ruby's crispy fried chicken. To remember this group 1 elements. Next, we will move towards group 2. Yeah, so this will be group 2. Sorry, just ignore this. This will be group 2. And group 2 element in Hindi. फर्स्ट लेट्स सी कि क्या क्या एलिमेंट है ग्रुप 2 में. ग्रुप 2 में है बेरिलियम, मैग्नीशियम, कैल्शियम, स्ट्रोंशियम, बेरियम एंड रेडियम। तो इसको याद रखने के लिए बहुत ही एक सिंपल सा निमोनिक्स है जो कि बहुत ही लोग फॉलो करते हैं इसको। बेटा मांगे कार्ड, सारे बाप राजी। तो अगर घर में इकलौता लड़का है कोई, तो लड़का बहुत प्यार का होता है, लाड प्यार का होता है, मम्मी पापा का बहुत ज्यादा प्यार मिलता है, वो जो भी मांगता है मम्मी पापा उसको ला के देते हैं। तो दैट्स वाई अभी बेटा थोड़ा बड़ा हो गया, एज हो गया, थोड़ा उसका गर्लफ्रेंड पटाने का मन किया होगा, तो वो क्या, उसको चाहिए कार। तो वो घर पे मांगा कि पापा मुझे कार चाहिए। तो अगर इकलौता बेटा है, अब इकलौता बेटा अगर कार मांग रहा है तो पापा तो देंगे ही, है ना। तो दैट्स वाई बेटा मांगे कार, सारे बाप राजी। नाउ लेट्स सी, बेटा बीई से स्टार्ट हो रहा है, तो बीई से हमारा क्या आता है, बेरिलियम। मांगे मांगे में है एमजी, जो एमजी से होता है मैग्नीशियम। कार कार सी कैल्शियम, सारे सारे में है एस आर, तो एस आर से हो रहा है स्ट्रोंशियम। बाप बाप में बी ए आ रहा है, और बेटा में ये याद रखना कि बेटा में बीई दिए था, बीई से बेरिलियम हो रहा था, और बाप में बी ए आता है, तो बी ए से होगा बेरियम। राजी राजी से रेडियम। बेटा मांगे कार, सारे बाप राजी। तो ये है इसको ग्रुप 2 को याद रखने के लिए निमोनिक्स। नाउ लेट्स सी इट इन इंग्लिश। So in English, you can see this will be group 2, okay? I'm just apologies for this mistake. It will be group 2. So now group 2 elements: beryllium, magnesium, calcium, strontium, barium, and radium. Now, how to remember? So there was a match between women team and uh, men team. So there was a funny match or charity match between American women team and American men team. But what happened? Suddenly, American women team performed very well and they won the game. They won the game in 2-0. So what happened? Because the American players, they were very good at back pass. So they were passing from the longer radius, from the longer range. They were doing the back passes. So their back passes, forward passes, all those passes were very accurate. So that's why the main team lost the match. Now what is the reason why the main team lost the match? Because Morgan या फिर मेगन, दोनों का ही नाम ले सकते हो. So both are very famous soccer players. So this is Megan and this one is Morgan. Morgan seems like an actress, but she is a very talented American soccer player. So you can remember by any one of their name. So the reason why the main team lost, because Morgan or Megan, whichever you like, can strike or back pass from bigger radius. So they were striking from far away as well as they were giving good back passes. So because Morgan or Megan can strike or back pass from bigger radius, so that's why the main team lost the match. Now next we will look into the p block elements. So we'll start with this group 13. तो ग्रुप 13 में क्या क्या है, बोरोन, एल्यूमिनियम, गैलियम, इंडियम एंड थैलियम। तो इसको याद रखने के लिए एक बहुत ही सिंपल सा है कि बैगन, आलू, गाजर का इतना बड़ा थैला। तो आप शॉपिंग करने गए हो तो आपको पूरे हफ्ते का खाना लेके आना होगा। आपकी मम्मी ने बोला कि पूरे हफ्ते का खाना लेके आओ, जाओ आलू बैगन गाजर जो भी मिलेगा लेके आओगे, तो एक बड़ा सा थैला दिया है आपको लेके आने के लिए। तो दैट्स व्हाई बैगन, आलू, गाजर का इतना बड़ा थैला। तो इतना बड़ा थैला लेके आप गए हो शॉपिंग करने। और अगर आपको और भी छोटे से वर्ड याद रखना है, तो छोटे से वर्ड के लिए आप याद रख सकते हो बैगिट। सो बैगिट एक पर्स का कंपनी है, मतलब वो बनाते हैं, तो बैगिट आप याद रख सकते हो, जो कि मेंस और विमेंस बैग बनाते हैं। बैगिट से क्या होता है, तो बैगिट बी से आ रहा है बोरोन, फिर ए से आ रहा है एल्यूमिनियम, फिर जी से आ रहा है गैलियम, आई से आ रहा है इंडियम और टी से आ रहा है थैलियम। बैगिट सिमिलरली अगर इधर देखोगे बैगन, आलू, गाजर का इतना बड़ा थैला, तो बी से यहाँ पे बी से आएगा बोरोन, आलू में एल है तो एल से एल्यूमिनियम, गाजर का जीए से गैलियम, और इतना में आई और एन है, इतना में तो इंडियम, और थैला में पीएल, तो पीएल से थैलियम। तो बैगन, आलू, गाजर का इतना बड़ा थैला, और सिंपल से अगर याद रखना है तो बैगिट याद रख सकते हो। Now let's see the English version. So the English version for group 13 elements, you have to remember that this Galapagos, so Galapagos was found in Thailand. Now what you found, that suddenly a big Galapagos was found in Thailand, and people were thinking that these Galapagos are almost extinct or it is about to be finished. So suddenly some people found big alive Galapagos in Thailand. Big alive Galapagos in Thailand. So B, from B you have to remember boron. Alive gives Al, that is for aluminum. Galapagos, Ga, that is for gallium. In indium, and in Thailand Tl are there, so from the Tl you have to remember thallium. Big alive Galapagos in thallium. Or what happened, so suddenly this Avengers opened a mysterious portal, and from portal, so a lot of aliens started coming inside the earth. So they are coming from different planets, different places, or even from multiverse they are coming. So they might be coming from anywhere else, and they started coming in Thailand. So during this Avengers wars, these aliens are coming, and where they are gathering? They are gathering in Thailand. So black aliens gathered in Thailand. क्या हो रहा था? Because this Avengers war was going on, and that's why these black aliens gathered in Thailand. From black we'll get B for boron. Aliens, Al, aluminum, gathered, Ga, gallium, in indium, Thailand. From Thailand you have to remember Tl stands for thallium. So black aliens gathered in Thailand. Next we will see group 14 elements. तो अभी हम देखेंगे ग्रुप 14 एलिमेंट्स। तो ग्रुप 14 एलिमेंट्स में है कार्बन, सिलिकॉन, जर्मेनियम, टीन एंड लेड। तो ये एलिमेंट्स हमें याद रखना है ग्रुप 14 के लिए। तो अभी क्या हुआ, शिमला में स्नो पड़ रहे हैं, तो स्नो देखने के लिए आपके पड़ोस वाली चाची शिमला चली गई है। उनका बहुत दिन का मन था कि वो शिमला जाएंगे, स्नो से खेलेंगे। तभी एक उनके रिश्तेदार आए हैं कोई, तो वो आके आपसे पूछ रहे हैं कि ये लोग कहाँ गए हैं। तो आप बोल रहे हो कि चाची शिमला गई स्नो पे। जो आपकी नेबरिंग चाची थी वो शिमला में चली गई, आप उनको बता रहे हो कि चाची शिमला गई स्नो पे, क्योंकि स्नो पसंद है चाची को, इसलिए शिमला चली गई वो। तो चाची में सी आएगा, तो सी फॉर कार्बन। शिमला में एस आई आएगा, तो एस आई से होगा सिलिकन। गई से आपको याद रखना होगा कि गई जर्मेनियम। और स्नो, स्नो का स्टार्ट होता है एसएन से, तो एसएन मतलब होता है टीम। और फिर स्नो पे, पे से आपको याद रखना होगा कि ये पी से स्टार्ट होता है, तो पीपी लेट होगा इसमें। और अगर आपको ये याद रखना टफ लगता है तो यू कैन रिमेंबर दिस वन। तो यहाँ पे हमें सबको पता है कि शिव जी और पार्वती जी कितना क्लोज थे वो, उनका रिलेशन हमें पता है, हम जानते हैं उनको साथ में। तो आप बोल सकते हो कि चले शिव जी संग पार्वती, तो दोनों साथ में जा रहे हैं कहीं पे। तो चले शिव जी संग पार्वती, तो चले से होगा कार्बन, शिव, शिव में एस और आई आएगा, तो वहां से होगा सिलिकन। जी में जर्मेनियम, संग, संग में एस और एन आएगा, तो एस एन से टीन। और पार्वती, पार्वती के अंदर है पी एन बी, तो यहाँ पे आएगा लेड। चले शिव जी संग पार्वती। Now let's see this group 14 elements in English. So in group 14 we have carbon, silicon, germanium, tin and lead. So you are attending a chemistry lecture. Right now you are also attending chemistry lecture. But in your tuition, when you attend the chemistry lectures, so your teacher gives a very hard problems, very standard problems. So that's why you are not able to solve those things. Now when you are not able to solve, then your parents asked that why you cannot solve these things, what is happening. Then you said, father or mother, see, the teacher is giving very hard problems, or the teacher is giving very standard problems. So that's why when they were asking you why you are not able to solve these things, then you were telling to your parents that chemistry sir gave standard problems. So as chemistry sir gave standard problems, you could not solve these things. So from chemistry starts with C, so C for carbon. Sir, it starts with Si, Si for silicon. Gave, you have to remember this G and E. From this GE, germanium. Standard, from the standard you have to find out this S and N. So from this SN you have to remember tin. And problems, problems P and B. So it represents lead. So chemistry sir gave standard problems. अभी हम देखेंगे पी ब्लॉक एलिमेंट का ग्रुप 15। तो ग्रुप 15 में क्या क्या है, नाइट्रोजन, फास्फोरस, आर्सेनिक, एंटीमोनी एंड बिस्मथ। तो ये सारे हैं ग्रुप 15 में। तो इसको कैसे याद रखेंगे, तो आप एक फिल्म देख रहे थे, तो उस फिल्म में एक्शन मूवी है हिंदी का, तो हिंदी का एक्शन मूवी में हीरो कौन था, हीरो थे नाना पाटेकर। और उनको तो हम जानते हैं, उनके डायलॉग्स काफी फेमस है, एकदम सिग्मा मेल है वो। तो नाना पाटेकर थे हीरो, और ब्यूटी क्वीन ऐश्वर्या थी हीरोइन। तो अभी आपकी जो फिल्म आप देख रहे थे आपको बहुत पसंद आया, तो उस फिल्म में हीरो थे नाना पाटेकर और हीरोइन थी ऐश्वर्या। तो आप क्या बोलोगे, आपको फिल्म बहुत अच्छा लगा है, उनके एक्टिंग्स भी बहुत अच्छे लगे हैं, तो आप बोलोगे कि नाना पाटेकर ऐश्वर्या सब बिंदास, बहुत अच्छा खासा एक्टिंग किया उन्होंने, आपको फिल्म एकदम पसंद आया। दैट्स व्हाई नाना पाटेकर ऐश्वर्या सब बिंदास। तो नाना से एन से आएगा नाइट्रोजन, पाटेकर के पी से आएगा फास्फोरस, ऐश्वर्या के एस, यहाँ से आपको रिमेंबर करना होगा आर्सेनिक, सब, सब में एस एंड बी, तो यहाँ से एंटीमोनी। एंड बिंदास, बिंदास में बी आई, तो बिस्मथ। नाना पाटेकर ऐश्वर्या सब बिंदास। फाइन। Now let's see the English version. So in group 15 we have nitrogen, phosphorus, arsenic, antimony and bismuth. Now this person, this scientist, you already know, this is Newton, Sir Isaac Newton. So what happened? So we all know that one apple fell down from a tree and it had hit his head. So that's how he started thinking that why it is always coming down, why the apple always comes down and doesn't go up. And slowly he invented gravity. Now what happened, that you have to remember that after that he thought, let's take a bite of that apple. And he took a bite of that apple. After taking bite of that apple, so Newton passed away. He died. Why? Because in that apple there was too much antimony. The bioaccumulation of antimony happened in that apple. So that's why when Newton took a bite of that apple, it causes damage, or it caused his death. So you have to remember, Newton passed away as antimony bioaccumulated. So inside this apple, antimony got bioaccumulated, and after taking a bite from this, Newton passed away. So Newton passed away as antimony bioaccumulated. So Newton, from Newton, you will find out nitrogen, N for nitrogen, passed away, P, P stands for phosphorus, as, so this is as, AS is coming first. So A is for arsenic. And then antimony, it is already there, antimony. So after arsenic, antimony will come. Bioaccumulated. So bioaccumulated starts from Bi. So from Bi, it is bismuth. So Newton passed away as antimony bioaccumulated. तो अभी हम आते हैं पी ब्लॉक एलिमेंट के ग्रुप 16 में। तो ग्रुप 16 में क्या क्या है हमारा, ऑक्सीजन, सल्फर, सेलेनियम, टेलुरियम एंड पोलोनियम। तो इसको कैसे हम याद करेंगे, कि वो स्टाइल से तेल पॉलिश। तो बच्चे यहाँ पे ना देखें, ये बच्चों का कंटेंट नहीं है, ये बस केमिस्ट्री के लिए है, कुछ और मत सोचिए इसको। तो क्या हुआ, अभी आपका फ्रेंड बाहर गई है, तो बाहर एक कंट्री में जाके उनको पता चला कि वहाँ पे बहुत अच्छे से मसाज दिया जाता है। तो मसाज देने के लिए क्या करते हैं, तेल यूज करते हैं। तो सोचो आपका फ्रेंड किसी कंट्री में गई है, सोचो जापान में गई है या कहीं पे गई है, एंड वहाँ पे जाके वो मसाज ले रही है। तो जो मसाज देगी पहले, मतलब देंगे जो मसाज, वो पहले उनको तेल पॉलिश करेंगे, फिर अच्छे से मसाज करेंगे। तो वो प्रोसेस बहुत अच्छा लगा आपको देख के, तो फिर आप क्या बोलोगे, ओह स्टाइल से तेल पॉलिश, मतलब बहुत अच्छे से वो कर रहे हैं। तो ओ के ओ से आपको याद रखना होगा ऑक्सीजन, स्टाइल, स्टाइल के पहले आ रहा है एस, एस से आपको याद रखना होगा सल्फर, से में आ रहा है एसई, एसई फॉर सेलेनियम, तेल, तेल में आ रहा है टीई, टीई फॉर टेलुरियम, और पॉलिश, पॉलिश में पीओ, पीओ फॉर पोलोनियम, वो स्टाइल से तेल पॉलिश। और अगर आप मार्वल फैंस हो मेरी तरह, देन यू कैन रिमेंबर ओ स्टाइल से टेलीपोर्टेशन। तो आप जानते हो डॉक्टर स्ट्रेंज, दिस इज डॉक्टर स्ट्रेंज, वो टेलीपोर्टेशन करने के लिए एक्सपर्ट थे। तो आप क्या बोल सकते हो कि ओ स्टाइल से टेलीपोर्टेशन। और अगर आप नहीं जानते हो देन गो वॉच बोथ द पार्ट्स ऑफ डॉक्टर स्ट्रेंज, पार्ट 1 पार्ट 2, एंड अभी तो बहुत सारे सीक्वल्स में भी आ रहे हैं वो। तो ओ स्टाइल से टेलीपोर्टेशन, ओ फॉर ऑक्सीजन, स्टाइल केस से सल्फर, से सेलेनियम, टेली में टी से टेलुरियम, एंड पोर्टेशन के पीओ से पोलोनियम। So next we will move to English. So for group 16, P block elements oxygen, sulfur, selenium, tellurium, and polonium. Polonium. How to remember this? So you know this British actor Oliver Stark, the very famous actor. So what happened? So in the initial days before he got famous, he used to sell telephones. So this is not, I'm telling, I have already told in the beginning of the lecture. So these stories are not true, but you have to believe that these are the true stories to remember these mnemonics. So Oliver Stark used to sell telephones before he got famous. So that's why you can remember that Oliver Stark sells telephone. So Oliver Stark sells telephone. So Oliver from O, from Oliver you will get this O, which is for oxygen. Stark, in the Stark there is only single S. So from this S you have to remember sulfur. And cells, in this cells you have Se. So from Se you have to remember selenium. Telephone, from the telephone you have Te for tellurium. And phone, in the phone you have P and O. So this PO stands for polonium. So Oliver Stark sells telephone. Or you can remember like this. So this actor Oliver Stark, so he is sending tempting photos. What happened? You have gone for a meeting and Oliver Stark is your friend, and Oliver Stark, he's having a party in his home, he's having biryani or something, and he's sending you that, oh friend, see you missed this, you would have come here so you could have eat this biryani. So he's sending you tempting photos of biryani and other things. So you have to remember Oliver Stark sends tempting photos, or Oliver Stark is sending tempting photos. So from Oliver, O stands for oxygen. In the Stark, S stands for sulfur. Sense, in this sense there is Se, so this Se stands for selenium. Tempting, tempting starts with Te, that is for tellurium. And photos, this PO represents polonium. So Oliver Stark sends tempting photos. Next अभी हम आएंगे ग्रुप 17 में. तो P block element ग्रुप 17, this is also known as halogens. तो halogens में क्या क्या है? फ्लोरीन, क्लोरीन, ब्रोमीन, आयोडीन, एस्टरीन. तो इसको कैसे याद रखना है? ऐसे याद रखो कि कल आप चिकन बिरयानी खा रहे थे और चिकन बिरयानी खाते खाते क्या हुआ कि चिकन का एक बोन जाके गले में अटक गया. तो आपको थोड़ा प्रॉब्लम हुआ, तो आपको अभी बिरयानी खाने से थोड़ा बहुत डर लग रहा है कि फिर से चिकन ना अटक जाए. तो आपके फ्रेंड्स फिर से आपको बोल रहे हैं कि चल बिरयानी खाते हैं, चल जाते हैं बिरयानी खाते हैं. आप बोलो नहीं 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 मैं नहीं जाऊंगा, मैं नहीं जाऊंगा. तो वो बोल रहे हैं कि क्यों क्यों नहीं जाएगा तू, क्यों क्यों नहीं मना कर रहे तू तो बिरयानी पसंद करता है. तो तब आप बोल रहे हो कि नहीं नहीं मैं बिरयानी खाने नहीं जाऊंगा क्योंकि फिर से कल बिरयानी अटका. तो ये आपके साथ पहले भी हो चुका है और कल कल फिर से हुआ था कि बिरयानी में जो चिकन का बोन था वो आपके गले में अटक गया था. तो इसलिए आप थोड़ा फ्राइटेंड हो बिरयानी खाने के लिए और बोल रहे हो कि नहीं जाना है मुझे, तुम लोग जाओ, मुझे नहीं जाना है क्योंकि फिर से कल बिरयानी अटका. तो फिर से के पहले आता है F, सो F स्टैंड्स फॉर फ्लोरीन. फिर कल में Cl, Cl से क्लोरीन. बिरयानी, बिरयानी में आपको याद रखना है कि दो एलिमेंट हो गए थे. तो बिरयानी में Br स्टैंड्स फॉर ब्रोमीन, एंड लास्ट में जो I है, सो I स्टैंड्स फॉर आयोडीन. तो फिर से कल बिरयानी अटका, अटका में जो At है, सो यू हैव टू रिमेंबर एस्टाडीन फ्रॉम दिस. और ऐसा भी याद रख सकते हो कि आपका एक दोस्त है फिलिप, बहुत शरारती दोस्त है, नॉटी दोस्त है. वो क्या करता है, उसको दारू पीने का बहुत शौक है. तो वो खुद अकेला नहीं पीता है, वो साथ में अपने दोस्तों को भी पिलाता है. तो अभी वो कॉलेज में आया है, कॉलेज के बाहर वो बियर लेके आया है. कौन सा बियर? ऑल्ट बियर. और उसके साथ साथ सिर्फ ऑल्ट बियर नहीं, वो आइस भी लाया था कि आइस डाल के सभी मिलके, सभी दोस्त मिलके पी पाए. जब कॉलेज खत्म हो जाए शाम को सभी दोस्त मिलके वो ऑल्ट बियर पी पाए. तो क्या हुआ, आपका फ्रेंड जिसका नाम है फिलिप, तो फिलिप कॉलेज के बाहर लाया आइस वाला ऑल्ट बियर. तो सभी दोस्तों मिलकर खाने के लिए वो कॉलेज के बाहर लेके आ गया कि सब जैसे ही कॉलेज खत्म होगा सभी दोस्त मिलकर बैठेंगे और ऑल्ट ऑल्ट बियर पिएंगे. तो क्या याद रखना है कि फिलिप कॉलेज के बाहर लाया आइस वाला ऑल्ट बियर. तो फिलिप से आएगा एफ, एफ फॉर क्लोरीन. कॉलेज से आएगा Cl, Cl फॉर क्लोरीन. बाहर, बाहर में आएगा Br, Br फॉर ब्रोमीन. और आइस वाला ऐसे ऑल्ट बियर नहीं लाया, आइस के साथ लाया, तो आइस वाला ऑल्ट बियर. तो आइस में I, I फॉर आयोडीन. और ऑल्ट बियर में आएगा आपका A और T, तो AT एस्टाडीन. तो फिलिप कॉलेज के बाहर लाया आइस वाला ऑल्ट बियर. Now next we will see the English version of the mnemonics for group 17. P block elements group 17. The elements are fluorine, chlorine, bromine, iodine, astatine. Now how to remember this? So you know Roger Federer, a very famous player. So Roger Federer, he used to like a beer. He had a pet beer. So now that beer died because of old age. So what he did, he told his team that he wants to clone that beer, and he cloned that same beer and he took it as a pet. So that's why his old beer died, but he has already cloned that beer and he's keeping as a pet. Where he's keeping, he cannot keep it at his home, so he is keeping it in Atlanta. So that's why Federer's cloned beer is in Atlanta, because he cannot keep it in home, right? Then the beer will eat all the homemates. So that's why Federer has cloned a beer and he's keeping it in Atlanta. So you have to remember Federer's cloned beer is in Atlanta. So from Federer's F stands for fluorine. Clone Br, so this clone Cl, this represents chlorine. Beer, B and R, so this beer represents bromine. Is in, so both in is or in you have I, so the starting letter is I. So from the I you can remember iodine, and where it is in Atlanta. So Atlanta starts with AT, that is for astatine. So Frederick's clone beer is in Atlanta. Or what you can think, that you are flying, you are going through airplane, and you are traveling in the first class, and in the first class you have been served a very special beer, and you are going to Atlanta, and in Atlanta they have served you a special beer. So that's why you are saying that first class beer in Atlanta. So you have enjoyed that thing very much, and then you are talking to your friend, and then you are saying, oh, they gave first class beer in Atlanta. So in Atlanta you got a very nice beer. So first class beer in Atlanta. So from first you have to remember F stands for fluorine. Then in the class Cl stands for chlorine. Br, B and R, this Br stands for bromine, and in I stands for iodine. Atlanta, AT stands for astatine. The first class beer in Atlanta. Now we will come to P block element group 18. अभी ये ग्रुप 18 में क्या क्या एलिमेंट है? ग्रुप 18 को बोला जाता है इनर्ट गैसेस. यहाँ पे सारे इनर्ट गैसेस हैं. इट स्टार्ट्स विद हीलियम, नियॉन, आर्गन, क्रिप्टॉन, जेनॉन एंड रेडॉन. तो ग्रुप 18 में हीलियम, नियॉन, आर्गन, क्रिप्टॉन, जेनॉन, रेडॉन है. तो कैसे याद रखना है? तो ये याद रखना है कि ये तीन जो एक्ट्रेस, बहुत ही फेमस एक्ट्रेस है, इंडियन एक्ट्रेस, हेमा मालिनी, नेहा शर्मा, करीना कपूर, तीनों एक से एक बड़े एक्टर हैं. तो इनको एक साथ एक पिक्चर के लिए साइन किया गया, और तीनों का एक सीन है कि उन तीनों को एक साथ रेन डांस करना है. बारिश होगी तो बारिश में उनको डांस करना है अपने हीरो के साथ. तो वो डांस बहुत फेमस हुआ, बहुत पॉपुलर हुआ, और उस पॉपुलर होने की, और वो फिल्म भी पॉपुलर होने की रीजन क्या था कि हेमा, नेहा और करीना जी की रेन डांस. तो वो फिल्म चलने की मेन रीजन थी कि इन तीनों ने जो रेन डांस किया था वो बहुत पसंद आया लोगों को, दर्शकों को बहुत पसंद आया. तो क्या याद रखना है कि हेमा, नेहा और करीना जी की रेन डांस की वजह से वो फिल्म पॉपुलर हुआ. अभी देखते हैं इसमें एलिमेंट्स. तो हेमा में आता है Ag फॉर हीलियम, नेहा में Ne फॉर नियॉन, और में आपको ऐसे रखना है कि AUR और, तो इसमें A एंड R आएगा, तो A एंड R से होगा आर्गन. करीना में आएगा K एंड R, तो KR से होगा क्रिप्टन. G को आपको याद रखना है Xc, तो ये Xc याद रखोगे तो इससे आएगा जेनॉन. और रेन, हेमा, नेहा और करीना जी की रेन डांस, तो रेन डांस में आएगा RN से रेडॉन. तो वो फिल्म चलने की मेन रीजन क्या थी? हेमा, नेहा और करीना जी की रेन डांस. तीनों ने साथ में एक रेन डांस किया था जो कि बहुत फेमस हुआ. ओके, ऐसे याद रखना है. Now we will come to the mnemonics of group 18 for p block element. What are the elements? The elements are helium, neon, argon, krypton, xenon and radon. So these 6 elements we will cover by this mnemonic. Now how to remember this? So there was a friendly match, cricket match between a girl team and a boy team. Now we all know that so these all are either politician or rapper or singer or actress, so they cannot play much cricket, right? So there was a match between these women team and men's cricket team. Now cricket team to अच्छे खेलेंगे, so that's why, so when they went for batting, so when this women team went for batting, so all of these got out in 0 run. So this is Hillary Clinton, Nicki Minaj, Ariana Grande and Kristen Stewart. So all these got bowled at 0 run because the main bowlers were bowling very well, so all of them got out at 0 run. And you have to remember that Hillary, Nicki, Ariana, Kristen all made 0 run. और इसीलिए because of this women team lost that friendly match and the main team won that friendly match. Why? What is the reason? Because Hillary, Nicki, Ariana, Kristen all made 0 runs. So from Hillary you will have He stands for helium. Then Nicki, from Nicki you have to remember Ne stands for neon. Ariana, Ar, so Ar stands for argon. Kristen is Kr stands for krypton. So all made 0 run. So 0 you have to remember as Xero, not ZRO. You have to remember that 0 means Xe. So Xe stands for xenon and run, Rn. So this Rn stands for radon. So Hillary, Nicki, Ariana, Kristen all made 0 run. That is the reason this women team lost that friendly cricket match against men team. Okay. Now next one is this 7p period, and these elements are often neglected in all the mnemonics. So whenever we made the mnemonics, we considered up to 6p, and we have not considered the 7p. So you just take this 7p and make a mnemonic with that. So 7p में क्या है? नाइहोनियम, सेरोबियम, मॉस्कोवियम, लिवरमोरियम, टेनेसिन, ऑर्गेनिसन. तो ये 6 एलिमेंट है 7p में. तो इसको कैसे याद रखना है? तो अभी ओमेगल बहुत फेमस है, आपने भी यूट्यूब में वीडियोस देखा ही होगा कि ओमेगल में लड़का लड़की बात करते हैं और बहुत फनी कंटेंट भी क्रिएट करते हैं वो. तो ओमेगल में क्या होता है, बहुत अलग अलग टाइप के फनी कंटेंट्स बनाते हैं लड़के या फिर लड़कियां. तो उसमें क्या है, ओमेगल में एक तुलसी नाम की लड़की बहुत फेमस है. तो अभी तुलसी क्या करती है, वो रोज देती है, और अगर आप ले लेते हो उसका रोज तो फिर वो बहुत गंदा सा प्रैंक करती है आपके साथ. तो वो तुलसी पहले आपको प्रपोज करने की कोशिश करेगी. तो प्रपोज करने की कोशिश में वो आपको रोज देगी. अगर आप बोलते हैं कि हाँ आप एक्सेप्ट कर रहे हो उसका रोज, तो फिर वो आपका मजाक उड़ाएगी. सो दैट्स व्हाई यू डोंट, मतलब आपको नहीं लेना चाहिए तुलसी का जो फ्लावर है वो नहीं लेना चाहिए. इसलिए आपका फ्रेंड आपको वार्न कर रहा है कि नहीं फ्लावर मत लेना तुलसी से ओमेगल पे. तो नहीं फ्लावर मत लेना तुलसी से ओमेगल पे, क्योंकि फ्लावर लोगे तो उसके बाद वो बेइज्जती करेगी और फिर बेइज्जती करके वो यूट्यूब में वीडियो छोड़ देगी, तो फिर आपका बेइज्जती हो जाएगा. तो दैट्स व्हाई आपका फ्रेंड आपको वार्न कर रहा है कि नहीं फ्लावर मत लेना तुलसी से ओमेगल पे। तो नहीं में आ रहा है NH, NH फॉर नायोनियम और निहोनियम। फ्लावर में आ रहा है FL, FL से हो रहा है फ्लेरोवियम। मत मत में आपको याद रखना होगा MC, मत से होगा मॉस्कोवियम। लेना लेना में आपको याद रखना है LV आएगा लिवरमोरियम। तो इसको थोड़ा सा आपको ट्रिकी है, थोड़ा सा आपको याद रखना होगा कि मत में MC होगा क्योंकि M से स्टार्ट हो रहा है, लेना L से स्टार्ट हो रहा है तो ये लिवरमोरियम होगा। और तुलसी, तुलसी में TS है तो तुलसी होगा टेनेसाइन। तुलसी से ओमेगल पे तो ओमेगल में है ONG तो ONG से होगा ऑर्गेनिज्म। तो नहीं फ्लावर मत लेना तुलसी से ओमेगल पे, क्योंकि अगर आपने फ्लावर ले लिया तो फिर वो आपका बेइज्जती करेगी, फिर उसका वीडियो यूट्यूब में छोड़ देगी तो आप पे लोग हंसेंगे, है ना। तो फ्लावर मत लेना तुलसी से ओमेगल पे। तो अभी जाओ जाके सर्च करके देखो तुलसी नाम का कोई है भी या नहीं जो ऐसे ओमेगल के ऊपर ओमेगल वीडियोस छोड़ दिया। आई डोंट नो, हो भी सकता है कोई। Okay, so if you want to remember these 7p elements along period, so these 7p elements, these are often neglected in the mnemonics and mostly people don't include them in the mnemonics. That's why I have made this separate mnemonics for these 7p elements along period. So in 7p we have nihonium, flerovium, moscovium, livermorium, tennessine, organism. So how to remember this? So you can remember that this Niho and Augie, they are actually friend. They are friend to each other. So this bird's name is Niho, which is a flamingo bird. So Niho and Augie, they are friend to each other and they love teasing each other in a friendly manner. So that's why you have to remember that Niho, flamingo of Moscow. So this flamingo is coming from Moscow. So this one is from Moscow. So Niho, flamingo of Moscow, loves teasing Augie because they are friend to each other. That's why they, in a friendly manner, they tease each other. They like to do it. They love to do it. So you have to remember Niho, flamingo of Moscow, loves teasing Augie. So in this Niho, NH will come from this NH or from the entire Niho. You can remember it will be Nihonium, Nihonium or Nihonium. And flamingo FL will come from this flamingo or FL. It represents Flerovium. And Moscow. In this Moscow, you can see M and C are there. Or if you even remember this Moscow, that Moscow will remember Moscovium, which this is MC stands for Moscovium. Loves, in this loves L and V, that stands for livermorium. And teasing, teasing T and S, that stands for tennessine. And Augie, Augie stands for organism. So Niho, flamingo of Moscow, loves teasing Augie in a friendly manner. So that's why, that's how you can remember this 7p elements. So this much was for this video. Hey genius, welcome back to the lecture 4 part B of the series periodic table and periodic trends. So in the previous lecture, we have discussed about mnemonics for S block elements and mnemonics for P block element. So that is lecture 4 part A. If you have not seen that, please go and watch that video. I think it will be helpful for you. And in this lecture, which is lecture 4 part B, we are going to cover mnemonics for D block elements, and that we will cover along the group. And in the next part, lecture 4 part C, we will discuss mnemonics for D block elements along period and mnemonics for F block elements. So all these mnemonics I have made or I have collected in both Hindi as well as English language. So whichever you feel is easier for you, easier to remember, you can note it down. And if you have any other alternative options, if you think you have a better or easier mnemonics, you can comment down below and share your knowledge with other fellow students. And one more thing, so while making these mnemonics, we will make up some stories, we will show some facts that are not real, but you have to believe in those facts, or you have to believe that, okay, maybe this is the correct thing or this is the right thing, so that just you can remember those mnemonics. But that does not mean that those facts are real. Okay, this is just to remember easily. This is just for making the mnemonics. These facts are not correct. So without wasting any time, let's start. So this is the D block elements, and in the periodic table, you can see from group 3 to group 12, these D block element or transition metal elements exist. Now we will remember the elements or atoms according to the group. So we will go group wise. The first one is group 3. तो चलिए देखते हैं ग्रुप 3 में क्या क्या है। ग्रुप 3 में पहले आता है स्कैंडियम, एट्रियम, फिर लैंथनम एंड एक्टिनम। तो इन चारों को हमें याद रखना होगा। तो इसके लिए हम क्या क्या याद रखेंगे कि आपको एक स्कूटी चाहिए और आप अपने घर में बोला है, आपने जिद किया है कि आपको स्कूटी चाहिए, तो फिर घर वाले ने अल्टीमेटली मान लिया है। अब घर का बच्चा अगर मांगेगा तो घर वाले मान जाते हैं, अगर फाइनेंशियल कंडीशन सही हो तो फिर आपने क्या बोला, फिर पापा ने बोला ठीक है हम चलो लेके आएंगे, स्कूटी लेके आएंगे। तो आप पापा को क्या बोलो, पापा बोलो पापा स्कूटर यामाहा का लेके आना। मीन्स अगर स्कूटर लाने जा रहे हो तो यामाहा का ही लेना, यामाहा का कंपनी आपको पसंद है, तो आप पापा को बोलो कि पापा स्कूटर यामाहा का लेके आना। तो स्कूटर में आ रहा है SC, सो SC स्टैंड फॉर स्कैंडियम। यामाहा के में आ रहा है Y, Y फॉर एट्रियम। लेके यहाँ पे आपको याद रखना होगा कि ये लैंथनम, इससे लैंथनम को याद रख सकते हो, और आना से AC याद रख सकते हो, दैट इज एक्टिनम। सो आप क्या बोलो पापा को, पापा स्कूटर यामाहा का लेके आना। Next, let's see this group 3 elements in English. So in the group 3 we have scandium, yttrium, lanthanum, actinum. So in this scenario, what is happening? There is a shooting going on. There is a shooting of a movie going on, and the main character who is playing the lead actress role, that girl's name is Shaila. So Shaila is doing her part. So that's why you can see Shaila acting, because Shaila is the main actress in that movie, and she is playing her role. Shaila acting. From this Shaila, you can find SCYLA. You have to remember these three elements from the Shaila. First one is scandium, Then Y stands for yttrium. From this La, you can remember lanthanum, and actin, it is AC there. From this AC, you can remember actinum. So Shala, actin. Next, we will come to group 4. तो अभी ग्रुप 4 में क्या क्या है? ग्रुप 4 में है टाइटेनियम, जर्कोनियम, हाफनियम एंड रदरफोर्डियम. तो ये रदरफोर्डियम 104th एलिमेंट है, तो इतना कॉमनली नोन नहीं है, बट दिस आल्सो बिलोंग्स टू ग्रुप 4. तो इसमें क्या हुआ? तो आपके घर में एक पेट है, पेट कैट, तो उसका नाम है टिम. अब टिम बहुत शरारती है, उसको कहीं पे भी खाना मिल जाए वो जाके खा लेता है, लेकिन छोटा बच्चा है, अब छोटे बच्चे का भूख तो ज्यादा नहीं होगा, तो पूरा खा नहीं पाता है, तो वो क्या करता है? वो आधा खा के छोड़ देता है. तो अभी आपके घर में पापा ने रेड फिश लेके आए थे पापा, तो पापा जब मार्केट से रेड फिश लेके आए, उन्होंने रख दिया टेबल में. अभी थोड़ी देर आप लोगों ने ध्यान नहीं दिया, तो फिर क्या हो गया? फिर थोड़ी देर बाद देख रहे हो कि वो रेड फिश आधा खाया हुआ पड़ा हुआ है. तो आधा खाया हुआ पड़ा हुआ है, उसको देख के आप लोगों को पता चल गया कि टिम ने या फिर टिमी ने जरूर हाफ रेड फिश खाया. तो ये टिम और टिमी, इसी ने हाफ रेड फिश खा के छोड़ दिया, क्योंकि पूरा खा नहीं पाता, ये बच्चा है. तो आपको याद रखना होगा, टिम और टिमी ने जरूर हाफ रेड फिश खाया. और टिमी या फिर टिम, इसमें आएगा आपका टीआई, टीआई फॉर टाइटेनियम, और जरूर में आएगा जेड आर, जेड आर से जर्कोनियम. हाफ, यहाँ पे हाफ से आप याद रख सकते हो हाफनियम, हाफ से आ रहा है हाफनियम. और रेड फिश में आर और एफ है, तो रेड फिश से रदरफोर्डियम. तो ये शरारती पेट टिमी, इसने हाफ रेड फिश खा लिया, तो ऐसे आप याद रख सकते हो इसको. नेक्स्ट वी विल कम टू द इंग्लिश. So in English and group 4, we have titanium, zirconium, hafnium, rutherfordium. So these 4 elements we have to remember for group 4. Now there is a movie which is coming in 2026. So that movie's name is Half Draft. So Half Draft is the movie which is going to be a blockbuster movie, and already many tickets are sold. So recently the teaser has been released in 2025. So the movie is coming in 2026, but the teaser has come in 2025. So what is the thing? That teaser of Half Draft. So the movie teaser which has come out, and the movie name is Half Draft. So teaser of Half Draft. So from this teaser you can remember titanium and zirconium, teaser, and half, from the half you can remember hafnium, and this raft RF, this RF represents rutherfordium. So you can remember teaser of half raft. तो नेक्स्ट देखते हैं हम ग्रुप 5 में. ग्रुप 5 में है वेनेडियम, नायोबियम, टेंटलम, डबनियम. इन 4 एलिमेंट्स को हमें याद रखना है ग्रुप 5 में, बी ब्लॉक एलिमेंट्स. तो क्या याद रख सकते हो? तो कुछ दिन पहले हमें पता है कि विराट कोहली और अनुष्का का एक बेबी हुआ. तो उस बेबी होने के बाद बहुत केयर करना होता है, और विराट कोहली नए नए पापा बने हैं, तो बहुत केयरिंग है वो. तो वो क्या कर रहे हैं कि विराट ने न्यूबॉर्न बेबी का टांग दबाया, मतलब बेबी को प्यार करने के लिए विराट कोहली ने न्यूबॉर्न बेबी का टांग दबाया. या फिर आप ये भी याद रख सकते हो कि अगर आप डोरेमोन फैन हो, तो डोरेमोन में आपको पता है नोबिता एक फेमस कैरेक्टर है, तो आप ये याद रख सकते हो कि विराट ने नोबिता का टांग दबाया. तो विराट से आता है वी, वी फॉर वेनेडियम, और ये नोबिता या फिर न्यूबॉर्न यहाँ से आएगा एनबी, नायोबियम, एंड टांग, टांग से आएगा टेंटलम, और दबाया, दबाया में आपको याद रखना होगा ये डी और डी आ रहा है, तो दबाया इस डी और डी से आएगा डबनियम. तो याद रख सकते हो विराट ने न्यूबॉर्न बेबी का टांग दबाया, या फिर आप याद रख सकते हो विराट ने नोबिता का टांग दबाया. Fine. Now next we will see this group 5 in English. So in group 5 we have vanadium, niobium, tantalum and dubnium. So we know the very famous cartoon characters Doraemon and Nobita. What happened? One day they were playing football, and as usually Nobita cannot play well, but that day Nobita was exceptionally playing. So all the players, they cannot defeat Nobita, and Nobita was dribbling very well. So that's why you can remember vegan Nobita dribbles. So vegan Nobita dribbles. So in vegan you have V, so V stands for vanadium, and in Nobita you can remember NB is niobium and TA for tantalum. So in Nobita you will get 2 elements, NB niobium and for TA tantalum. And dribbles, in the dribbles you have to remember this D and B. So from this D and B it is representing dubnium. So Nobita is playing exceptionally well that day, and vegan Nobita dribbles. So next हम देखेंगे group 6. तो group 6 में है chromium, molybdenum, tungsten and seaborgium. So chromium, molybdenum, tungsten and seaborgium. तो इसको हम कैसे याद रखेंगे? तो ये है मिमी वेब, एक सिंगर एंड सॉन्ग राइटर है, तो बहुत पॉपुलर है. तो आई होप ये शी गेट्स लॉन्ग लाइफ, बट फॉर द सेक ऑफ रिमेंबरिंग दिस 4 एलिमेंट्स वी कैन गो विद कार में मौत वेब सिंगर की. तो कार में मौत वेब सिंगर की, एक भयंकर एक्सीडेंट हुआ और उसमें मौत हो गया वेब का. तो आई रियली होप कि शी लिव्स लॉन्ग, and I like the person, but just for the sake of remembering this we have to make these mnemonics, that कार में मौत वेब सिंगर की. From the car, कार से आएगा CR, CR for chromium, मौत, मौत में MO, तो MO से हमें याद रखना होगा molybdenum, एंड सिंगर का नाम क्या है? वेब, वेब, वेब से W, और W आएगा टंगस्टन के लिए. सिंगर में आएगा SG, तो SG से आ रहा है सीबोर्जियम. तो कार में मौत वेब सिंगर की. So next we will go to group 6 in English, and in group 6 we have chromium, molybdenum, tungsten, seaborgium. So now we can remember it in this way, that you have gone to a maybe Iceland or somewhere else where you have a lot of ice, and there you can see a monk seal. you observed a monk seal, and so it was acting very crazily. So it was kind of, he got food recently and he was happy, so he was enjoying his time. That's why you can remember crazy monk seal in white sheet. So you can see in white sheet, so there's a crazy monk seal. From crazy, you have to remember the Cr represents chromium. Monk seal, what kind of seal? Monk seal. So monk, Mo, is molybdenum, where in white sheet, white. So white, W stands for tungsten. And from the C, you can easily remember the C is standing for this seaborgium. This also starts with C, the seaborgium. Or you, if you are a monkey lover and you love the movies which monkeys, I mean, in which monkeys play the central role or monkeys are the heroes. So in that way, you can remember that crazy monkey wants swag. So there is a monkey, and that has very popularity, and he stays in his own swag. So you can remember that crazy monkey wants swag. So from this crazy, Cr represents chromium, monkey, Mo represents molybdenum. Wants, in the wants we have W, so W stands for tungsten, and swag. So in the swag we have S and G. So this Sg will give seaborgium. So crazy monkey wants swag. नेक्स्ट हम जाएंगे ग्रुप 7 में. तो ग्रुप 7 में हमारे पास है मैंगनीज, टेक्नीशियम, रेडियम एंड बोरियम. तो क्या हुआ, एग्जाम पे आप गए हो, अचानक से एग्जाम आ गया, सरप्राइज टेस्ट, और सरप्राइज टेस्ट में आपने कुछ प्रिपरेशन नहीं किया, आपको पता नहीं था कि एग्जाम होने वाला है, आपने पढ़ा नहीं अच्छे से. तो अभी आप क्या करोगे, अभी आप अपने साथ में जो दोस्त है जो कि पढ़ के आती है, तो पहले जाके ऐसे दोस्त को ढूंढोगे कि जो बहुत पढ़ती है, और बेसिकली लड़कियां ज्यादा पढ़ती है. तो अभी एक लड़की के पास चले गए, उनको बोलो जाके कि देख मैं कुछ पढ़ के नहीं आया हूँ, तो अभी मैं तेरे भरोसे एग्जाम देने वाला हूँ. दैट्स व्हाई आई एम काउंटिंग ऑन यू, मैं तेरे भरोसे. तो मैं से आएगा Mn फॉर मैंगनीज, और तेरे में आपको याद रखना है कि तेरे में दो एलिमेंट्स आएंगे, पहले आएगा टेक्नीशियम और रे से आएगा रेडियम, और भरोसे से BH, तो BH से आएगा बोरियम. तो आपने एग्जाम में प्रिपरेशन लिया नहीं अच्छे से, तो फिर आप अपने दोस्त को जाके बोल रहे हो कि देख भाई मैं तो तेरे भरोसे. या फिर ये सिनेरियो आप याद रख सकते हो कि आप एक दोस्त के अपार्टमेंट में रह रहे हो, शेयरिंग में रह रहे हो, दोनों दोस्त शेयर करके रह रहे हो. तो क्या होता है, हर मंथ आप आधा रेंट देते हो, वो आधा रेंट देता है. तो अभी क्या हुआ, रिसेंटली आप रेंट देना भूल गए. तो आप क्या करते हो, आप अपना हिस्से का रेंट उसको देते हो, आधा रेंट दोस्त को देते हो, और दोस्त अपना आधा आपका आधा मिला के पूरा रेंट देता है. पर रिसेंटली आप भूल गए, तो फिर आप क्या बोल रहे हो कि मैं तेरे को रेंट देना भूल गया था. तो मैं तेरे को रेंट देना भूल गया था, तो मैं से आएगा Mn फॉर मैंगनीज, तेरे को से याद रख सकते हो TC से टेक्नीशियम, और रेंट में आ रहा है RE से रेडियम, और भूल गया मैं BH, तो BH से याद रखना होगा बोरियम. तो आप क्या कर रहे हो, आप अपोलोजाइज कर रहे हो उसको कि यार मैं तेरे को रेंट देना भूल गया था. Next we will see this group 7 in English. So in group 7 we have manganese, technetium, rhenium and borium. Now you are in the office, you are a working person, and in your office manager takes care of all the things, so he has a lot of workload, right? You have workload, that's fine, and manager is in higher position compared to you, so he has more workload. He has to do his works as well as he has to check all other people are working or not. So what happened, one day you see that manager is so stressed that he is taking rest in the lunch hour, so he fell asleep, and you observe that manager taking rest in break hours, because manager has a lot of workload or work pressure, so that's why he is taking rest in break hours. So from this manager you can remember Mn stands for manganese. From this taking you can remember technetium. Rest in the rest that is Re. From this Re you can remember rhenium in breaking hours. So from this breaking hours you have to remember B and H. BH stands for borium. So manager taking rest in break hours. अभी हम आएंगे ग्रुप 8 में. तो ग्रुप 8 में क्या क्या है, ग्रुप 8 में है आयरन, रुथेनियम, ऑस्मियम एंड हेसियम. तो अभी कैसे याद रखना है, तो आपके पास बहुत सारे दोस्त हैं, उनमें से एक दोस्त है फिरोज और एक दोस्त है उस्मान. अभी फिरोज क्या है, फिरोज बहुत शैतान है. अगर आपने नोबी मतलब डोरेमोन देखा होगा तो आपको पता होगा कि वहाँ पे जियान होता है जो सबको जा जाके मारता है, डराता है. तो फिरोज ऐसा है कि सबको डराता है, मारता है, और वहीं पे डोरेमोन जो होता है सबको हेल्प करता है. तो वैसे आपका एक और दोस्त है उस्मान जो हेल्प करता है, सबको खुश रखता है. तो इसलिए आप बोलोगे फिरोज रुलाए उस्मान हंसाए. तो आपके दोस्त में फिरोज और उस्मान, इसमें फिरोज जो है वो बहुत शैतान है, तो फिरोज रुलाता है सबको, फिरोज रुलाए, और उस्मान जो है वो अच्छा बंदा है, सबको हंसाता है, तो उस्मान हंसाए. फिरोज रुलाए उस्मान हंसाए. तो यहाँ पे फिरोज में आएगा Fe स्टैंड्स फॉर आयरन, रुलाए में आएगा Ru, सो Ru से आपको याद रखना है रुथेनियम, उस्मान से आपको याद रखना है ऑस्मियम, और हंसाए इसमें HS, तो इससे आपको याद रखना होगा हेसियम. तो फिरोज रुलाए उस्मान हंसाए. या फिर ऐसा भी हो सकता है कि कुछ सेंसिटिव बात चल रहा था, तो फिरोज अपने लाइफ का कुछ सेंसिटिव बात बोल रहा था. उस टाइम पे क्या हुआ, उस्मान चीजें सीरियसली लेता नहीं है, तो वो थोड़ा हंसी मजाक में रहता है, तो उसने कुछ हंसी मजाक कर दिया और हंसने लगा खुद. तो उसमें फिरोज को बुरा लग गया, फिरोज रूठ गया उससे. तो क्या हुआ, आपके जो दोस्त फिरोज और उस्मान, फिरोज अपना कुछ सेंसिटिव बात बोल रहा था और उस्मान ने उस पर हंस दिया, तो फिरोज रूठा उस्मान के हंसी पे, क्योंकि उस्मान ने हंस दिया तो फिरोज को बुरा लग गया और रूठ गया वो. तो फिरोज रूठा उस्मान के हंसी पे. फिरोज में आ रहा है Fe से आएगा आयरन, रूठा से Ru से आएगा रुथेनियम, और उस्मान से आएगा OS से आपको याद रखना ऑस्मियम, और हंसी में आपको हंसी से याद आ जाएगा हेसियम. यहाँ पे देख सकते हो हेसियम, तो हेसियम और हंसी में बहुत सिमिलरिटी है, तो ये आपको इजीली याद रह जाएगा. Now let's talk about group 8 in English. So in group 8 we have iron, ruthenium, osmium, hesium. So how to remember this? Now we know there was a very dangerous terrorist, Osama bin Laden. So after that Osama bin Laden, you can remember or you can think that after Osama bin Laden, there is another one terrorist whose name is Osama Hussein. So Osama Hussein is another bad guy. Okay. Now what happened? Firoz is a cop. Firoz is a very responsible cop. He's a very good person. So what happened? There was a fight between the cops and the bad boys. So there, Firoz, being a cop, he has to kill Osama Hussein. So that's why Firoz ruthlessly killed Osama Hussein. So what happened? There was a fight between the cops and the bad guys. So there, Firoz was a cop and Osama Hussein, which was a bad guy. So that Firoz killed that bad guy. So you have to remember Firoz ruthlessly killed Osama Hussein. So from this Firoz, you can see Fe, this stands for iron. From the ruthlessly, from Ru, you have to remember ruthenium and Osama. And this Osama, you will have OS. OS stands for osmium. Hussein, you will get HS. So from this, you have to remember hassium. So Firoz ruthlessly killed Osama Hussein. नेक्स्ट अभी हम आएंगे ग्रुप 9 में। तो ग्रुप 9 में क्या क्या है? ग्रुप 9 में है कोबाल्ट, रोडियम, इरिडियम एंड मैग्नीशियम। तो इसमें क्या है, आपका एक दोस्त है जो कि मिलिट्री में ज्वाइन किया है और मिलिट्री में ज्वाइन करके बहुत ज्यादा प्रेशर आ रहा है क्योंकि बहुत इंटेंस ट्रेनिंग रहता है। तो आपने उसको कॉल किया तो वो गिव अप कर रहे हो, बोला कि नहीं इतना नहीं रह पाऊंगा, बहुत मेहनत करवा रहे हैं, मेरे से नहीं हो रहा है, कौन रहेगा ईरानी मिलिट्री में। तो आपके दोस्त ने जो ईरानी मिलिट्री ज्वाइन किया था वो अभी नहीं कंटिन्यू कर पा रहे हैं वहाँ पे, तो इसलिए वो बहुत निराश हो चुका है। आपको कॉल में बोला है कि कौन रहेगा ईरानी मिलिट्री में। तो कौन कौन से आपको याद रखना होगा? सीओ से कोबाल्ट, रहेगा में आएगा आरएच, आरएच से रोडियम, ईरानी में आईआर, आईआर से इरिडियम, और कहाँ रहना है कि मिलिट्री में, ईरानी मिलिट्री से आएगा एमटी, तो एमटी से आपको याद रखना है मैग्नीशियम। तो आपका दोस्त बोल रहा है कौन रहेगा ईरानी मिलिट्री में। और इन अदर वे ये हो रहा है कि आप ईरान में गए हो और ईरान में उस टाइम पे उनका मिलिट्री का मार्च चल रहा है, तो आपको उस रोड अवॉइड करना है, उस रोड से जा नहीं पाओगे। तो दैट्स व्हाई आप वहाँ पे लोकल लोगों से पूछ रहे हो कि कौन सी रोड पे ईरानी मिलिट्री है, मतलब कौन से रोड पे ईरानी मिलिट्री है। आप वो वाला रोड नहीं लोगे, आप दूसरे वाले रोड से जाओगे क्योंकि उस रोड से जा नहीं पाओगे। तो आप इसलिए लोगों को पूछ रहे हो कि कौन सी रोड पे ईरानी मिलिट्री है। तो कौन सी में आएगा? सीओ से आप याद रखना कोबाल्ट, रोड पे आरएच, आरएच से याद रखना होगा रोडियम, और रोड से भी रोडियम याद करना ईजी हो जाएगा। और ईरानी से आईआर, आईआर से आपको याद रखना है इरिडियम, और मिलिट्री के एमटी से आपको याद रखना है मैग्नीशियम। तो कौन सी रोड पे ईरानी मिलिट्री है आप पूछ रहे हो किसी को। Now let's see this group 9 in English. So in group 9 we have cobalt, rhodium, iridium and magnesium. So there is a simple situation that everyone faces in some part of their life. So in some part either you have to take career or other responsibilities or home responsibilities or your love life, all these things. So in that case either it may appear that you have a situation where either you have to choose your career or you have to choose your loved ones. So in that scenario your friend, he is suggesting you that bro, see, girlfriend will come and go, if it goes another will come, but career is must, so you have to choose the career. Your friend is suggesting you to take the path where you can build your career, so that's why your friend is saying career must. So from this career you can remember three elements: cobalt, rhodium and iridium in this career. And from this must, M and T, this M and T represents magnesium. So simply you can remember these four elements in group 9 by remembering career must. And obviously career is very important, that's why I will request you all to learn and read very sincerely, and whatever you are doing in your life, do it with discipline and sincerity, because career is really a must thing. Okay, so next है group 10. So group 10 में क्या क्या है? Group 10 में है निकल, पैलाडियम, प्लैटिनम एंड डमस्टर्डियम। तो ये क्या हुआ, अभी आपके घर के बगल में एक और घर है, तो उसमें घर वालों ने रेंट पे दिया है। अभी रेंट पे जो लोग होते हैं वो कभी ना कभी चेंज होते रहते हैं, रेंट वाले जो किराएदार होते हैं, है ना। तो अभी रिसेंटली वो किराएदार चेंज हुआ है और एक नई फैमिली मूव इन किया है। तो उसमें जो लड़की है, उस फैमिली में जो लड़की है वो आपको बहुत पसंद आ गया है, आप देख के लट्टू हो गए उस पर। तो आप अपने दोस्त को कॉल करके क्या बोल लो, अरे भाई मैंने देखा उनकी पड़ोसी में बहुत मस्त लड़की है, एकदम नई पड़ोसन, पटाखा देसी। तो देसी लड़की और बहुत अच्छी दिखने में है, और दिखने में बहुत अच्छी है और आपको बहुत ज्यादा पसंद है, तो आप अपने दोस्त को बोल लो नई पड़ोसन पटाखा देसी। तो नई में आपको याद रखना होगा निकेल, और पड़ोसन में आ रहा है पीएनटी, पड़ोसन, तो इस पीडी से आपको याद रखना होगा पैलाडियम, और उसके बाद आपको याद रखना होगा पटाखा में है पीएनटी। तो यहाँ पे कंफ्यूज मत करना, पड़ोसन पटाखा देसी, तो नई पड़ोसन पटाखा देसी पहले आ रहा है पड़ोसन, पड़ोसन में पीडी, पैलाडियम पहले आता है, उसके बाद आता है पटाखा, पटाखा में आएगा पीटी, पीटी में प्लैटिनम आता है, और कैसा है ना देसी है, देसी लड़की एकदम शुद्ध देसी लड़की है, तो देसी में डीएस, तो डीएस से आएगा डमस्टर्डियम। सो नई पड़ोसन पटाखा देसी। और फिर आपका दोस्त आपको एनकरेज करता है कि हाँ ठीक है ट्राई कर, तू भी तो हैंडसम है, गुड लुकिंग है, ट्राई कर देख होगा या नहीं। फिर आपको वो चैलेंज करता है, तू करके दिखा कि वो तेरा गर्लफ्रेंड बनेगा। आप भी चैलेंज ले लेते हो, जो जोश में होते हैं ना, जब यंग रहते हैं, तो आपने भी चैलेंज ले लिया। फिर आप चैलेंज करके उसको बोलो कि हाँ देख लेना, नई पर्सन को पटाऊंगा 10 दिन में। तो वो जो नई पर्सन आई है जो आपको बहुत पसंद है, तो आप अपने दोस्त के साथ फोन पे बात कर रहे हो, उसको बोल लो कि नई पर्सन आई है, वो आपको चैलेंज कर रहा है, आप चैलेंज एक्सेप्ट कर रहे हो, और फिर बोल लो कि नई पर्सन को पटाऊंगा 10 दिन में। तो यहाँ पे नई से आएगा एन एन आई, तो एन आई से आपको याद रखना है निकेल, पड़ोसन में आएगा पीडी, तो पीडी से आपको याद रखना है पैलाडियम, पटाऊंगा में आएगा पीएनटी, तो पीटी से याद रखना है प्लैटिनम, और 10 दिन, कितने दिन टाइम दिया आपने? 10 दिन, तो 10 दिन में DNS है, तो उसमें आपको याद रखना है ड्रमस्टर्डियम। ओके, तो ये सब देख के अपने पड़ोसन को झांकना मत, और उल्टा उल्टा कुछ हरकत मत करना, फिर मत बोलना कि हाँ यूट्यूब वीडियो में देखा है ऐसा, तो ऐसे करते रहो, ऐसा नहीं है कुछ, ये बस नेमोनिक्स है, याद रखने के लिए है। तो प्लीज किसी भी तरह का किसी को मैं मतलब एनकरेज नहीं कर रहा हूँ कि किसी को डिस्टर्ब मत करना, अगर कंसेंट नहीं है तो किसी को भी कोई भी डिस्टर्बेंस मत करना। These things are not good things, so you should not disturb any other person, maybe it's a boy or girl, you should not disturb anyone. Liking may be there but you should not disturb anyone, okay? And ये जो stalking walking ये भी अच्छी चीज नहीं है, ये सब भी मत करना, these things are not good. Be a nice person. Being a nice person, you can go, you can approach, you can say that you like him or her. If it is a yes, then you can continue. If it is a no, then go back. Right? Now let's come to the English. So group 10, we have nickel, palladium, platinum, and dubsturdium. So you have, the scenario is that you have a lot of pet dogs in your home, and you love those dogs, and those dogs love pet foods. So in the pet food, one of the best option is Pedigree, right? So Pedigree launched his new product, and they have done the marketing. From there, you came to know that they have launched a new product. So new product for pet dogs, and they are giving a massive discount for this new Pedigree. So the scenario is that you have dogs in your home, and there is a new product for Pedigree. So new Pedigree for pet dogs, and you are going to buy those for your dogs. So you have to remember new Pedigree for pet dogs. So new से आपको याद रखना है NI निकल, Pedigree में आ रहा है P and D से होता है पैलाडियम, और for pet dogs means P and T. So from PT you have to remember platinum, and dogs D and S. From this DS you have to remember dubsturdium. So new Pedigree for pet dogs. Next is group 11. So in group 11 हमारे पास क्या क्या है? Group 11 में है कॉपर, सिल्वर जिसका सिंबल है Ag, तो Ag से सिल्वर होता है, फिर है गोल्ड का सिंबल है Au, और उसके बाद है रोंचेनियम, कॉपर सिल्वर गोल्ड रोंचेनियम। तो आपने, अगर आप मार्वल फैंस हो तो मार्वल की मूवीज देखा है, या फिर वंडर वुमन देखा है, तो ये है वंडर वुमन का सीन, और यहाँ पे है स्कारलेट विच का सीन। तो ये सब बहुत फेमस मूवीज है, और आपको पता है कि अगर कोई औरत गुस्सा हो जाती है तो उससे ज्यादा पावरफुल कोई नहीं होता है ना? तो हमने देखा है कि स्कारलेट विच भी जब गुस्सा हो जाती है बहुत ज्यादा पावरफुल हो जाती है, बहुत भयंकर हो जाती है। तो औरत के गुस्से के आगे कोई नहीं टिक सकता, कोई मर्द भी नहीं टिक सकता अगर एक औरत गुस्सा हो गई है ना? तो आपको ये याद रखना है, बस यही याद रखना है कि अगर एक औरत गुस्सा कर रही है तो सारे मर्द चुप हो जाएंगे, कोई कुछ नहीं कर पाएगा, कोई कुछ नहीं बोल पाएगा। ठीक है, जब औरत को गुस्सा आ जाए, गुस्सा या फिर राग, गुस्से का मतलब है राग, तो राग हो जाए उनका अगर, तो उनके राग के सामने कोई कुछ नहीं बोल पाएगा। तो कौन आगे जब औरत रागे, तो कौन आगे आ पाएगा? आपको ऐसा याद रखना है कि कौन आगे आ पाएगा, कोई आगे नहीं आ पाएगा। कब ना, जब औरत औरत को गुस्सा हो जाए फिर राग हो जाए। कौन आगे जब औरत रागे, कौन से आपको याद रखना है? सी यू कॉपर, आगे आगे से एजी है आगे में, तो एजी से सिल्वर, और जब औरत में है एयू, तो एयू से होगा गोल्ड, एंड औरत को क्या हुआ है? गुस्सा हुआ है, फिर राग हुआ है, तो राग से आरजी से आएगा रोंचेनियम। तो कौन आगे जब औरत रागे? Okay, so next one is group 11 in English. So in group 11 we have copper, silver is represented as Ag, then gold is represented as Au, and rontgenium. So in group 11 we have copper, silver, gold, and rontgenium. So this is another naughty thing, but I know that students like to remember naughty things, and they easily remember the naughty things, right? So what happened? You know little Johnny. So this is little Johnny, and little Johnny is having an affair with the older women. So little Johnny is having an affair with the older women, and they were doing those naughty stuff. So being naughty, that auntie is saying that come again, auntie is British. So this come is a little bit different, I mean little bit dirty meaning. So this means, okay, so you can ignore this. You just remember come again, auntie is British. So little Johnny and this older woman, they are having an affair. So auntie is expecting more from him, and she wants more. She is horny. So that's why she's saying come again, hey little Johnny, come again, auntie is British. So from come you have to remember CU for copper. Again starts with A and G. So AG stands for silver, and the auntie AU stands for gold, and auntie is Rigish. So Rigish means from Rigish you have RG. RG stands for rontgenium. So auntie is very horny, and she is asking little Johnny to do the sexual activity again. That's why she is telling that come again, auntie is Rigish. Yeah, so these things are purely for educational purpose, and I do not promote this kind of activities or anything, but to make this mnemonics easier so that you can easily remember these things, we are making these kind of things. But I'll sincerely tell you that do not promote or do not involve yourself in these kind of acts. Okay, so next one is group 12. तो group 12 में क्या है हमारे पास है जिंक, कैडमियम, मरकरी और कोपर्निसियम। तो मरकरी का सिंबल होता है Hg। तो जिंक, कैडमियम, मरकरी एंड कोपर्निसियम। मरकरी को Hg से भी हम याद रख सकते हैं। तो इसमें क्या है? इसमें दो लवर्स हैं, एक लड़की का नाम है जिंकी और उसका एक बॉयफ्रेंड है। तो वो क्या करते हैं? कडल करना बहुत पसंद करते हैं, हग करना, कडल करना बहुत पसंद करते हैं। तो जिंकी अपने बॉयफ्रेंड को बुला रही है, बोल रही है कि आ जाओ मुझे कडल करना है, तो इसलिए जिंकी चाहता हग करना। तो दिस इज इन पंजाबी काइंड ऑफ। सो चाहता मींस शी इज वांटिंग, मतलब उसको वो चाह रही है हग करना, तो जिंकी चाहता हग करना। तो जिंकी आपको याद रखना होगा जेड एन स्टैंड फॉर जिंक, और यहाँ पे जिंक भी आपको पता चल रहा है जिंकी से जिंक। और चाहता चाहता में आएगा सी एन डी, सी डी में आएगा कैडमियम। और क्या चाहती है जिंकी? जिंकी चाहती है हग करना। हग से एक जी से आपको याद रखना होगा मर्करी। एंड करना, करना में आपको थोड़ा यहाँ पे याद रखना होगा, करना में सी एन आपको याद रखना है, तो सी एन से आएगा कोपर्निसियम। तो जिंकी क्या चाहती है? जिंकी चाहता हग करना। Now we will come to group 12 in English. So in group 12 we have zinc, cadmium, mercury and copernicium. So these four elements are there in group 12. Now you have a pet dog whose name is Zinky, or you can even say Zane according to your preference. So Zinky is your favorite pet dog, and she is a very friendly dog, and she always licks or hugs the human friends. So you can remember that your pet dog Zinky cuddles and hugs constantly. Zinky is a very friendly dog, and Zinky cuddles and hugs constantly. So from this Zane or Zinky, you can remember zinc. Zn stands for zinc. Now cuddles, in the cuddles we have C and D. From the CD you have to remember cadmium. Hugs, from this hug you will get H and G. So Hg stands for mercury. And constantly, constant in the constantly you have C and N. So Cn stands for copernicium. So Zinky cuddles and hugs constantly. So this much was for this video. So in this lecture for part B, we have covered mnemonics for D block elements along group in Hindi as well as English. So you can pick up the ones which you like most or which you feel those are very easier to remember. There are some naughty mnemonics as well, but those are just to remember, just for the educational purpose. Okay. So, hey genius, welcome back to the lecture for part C of the series periodic table and periodic trends. In the last two videos, we have learned mnemonics for S block element, mnemonics for P block element, and in the last video, we have learned mnemonics for D block elements along period. Now in this video, we are going to learn mnemonics for D block elements along group and mnemonics for F block elements, both in Hindi and English. So without wasting any time, let's start. So these are the D block elements, and now we are going to see them as or along period, along row, and we are going to have our mnemonics along row. So first comes this 3D. अभी 3D सीरीज में हमारे पास है स्कैंडियम, टाइटेनियम, वैनाडियम, क्रोमियम, मैंगनीज, आयरन, कोबाल्ट, निकल, कॉपर एंड जिंक। तो इसको कैसे याद रखना है? तो एक कुआं है, उस कुआं में एक छोटी सी बच्ची गिर गई है जिसका नाम है जिंकी। और उसमें क्या है, ऊपर बहुत सारे पत्थर रखे हुए कुआं के ऊपर। तो कोई भी आम आदमी उसको निकालने जाएगा तो वो पत्थर वगैरह कुआं में गिर सकता है और उसमें जिंकी को चोट लग सकता है। तो इसलिए क्या बोल रहे हैं, शक्तिमान मना कर रहे हैं, बोल रहे हैं कि आम आदमी आप लोग ट्राई मत करो, मैं आ रहा हूँ। तो लोग चाह रहे हैं उनको निकालना खुद से, बस शक्तिमान मना कर रहे हैं, बोले नहीं मैं आके निकालूंगा, आप लोग मेरे ऊपर छोड़ो, मैं उसको सेफली निकालूंगा। तो शक्तिमान करे मना, फिर कौन निकाले कुआं से जिंकी को? क्योंकि शक्तिमान ने मना किया है तो कोई नहीं निकाल सकता कुआं से जिंकी को। शक्तिमान करे मना, फिर कौन निकाले कुआं से जिंकी को? शक्तिमान में आपको याद रखना होगा, इसमें आएगा 3 एलिमेंट्स, Sc स्कैंडियम, यहाँ पे Ti से टाइटेनियम और V से वैनाडियम। कड़े में आप याद रख सकते हो CnR क्रोमियम, मना से आप याद रख सकते हो मैंगनीज Mn, फिर से आपको याद रखना होगा Fe आयरन, कौन में CO, कौन से CO याद रखना होगा कोबाल्ट, एंड निकाले से Ni निकल, कुआं से कहां से? कुआं में Cu आता है तो Cu से होगा कॉपर, कुआं से जिंकी को, तो जिंकी में आएगा Zn से जिंक। तो क्या हुआ, कुआं में जिंक गिर गई है, तो आसपास में बहुत से पत्थर रखे हुए कुआं के ऊपर, तो नॉर्मल आदमी आम आदमी ट्राई करेंगे तो पत्थर वगैरह गिर सकता है जिंकी के ऊपर, तो इसलिए शक्तिमान मना कर रहा है कि आप लोग मत करो कुछ। तो शक्तिमान करे मना, फिर कौन निकाले कुआं से जिंकी को? अभी 3D सीरीज को आप ऐसे भी याद रख सकते हो, ये किसी और टीचर ने किया है, बनाया है ये, तो काफी इंटरेस्टिंग लगा था मुझे, तो इसलिए मैंने सोचा कि मैं ये आप लोगों के साथ भी शेयर करता हूँ। तो यूट्यूब में मैंने देखा था, तो इसमें क्या हुआ, नहीं एक स्कूल में बच्चा है, 10th क्लास का एक बच्चा, उसको एक लड़की पसंद है। तो अभी वो डायरेक्टली नहीं बोल पा रहा है, वो क्या बोल रहा है कि देखो तुम, मतलब ये लड़की बहुत अच्छे दिखने में है, तो लड़के मरते हैं उसमें, तो लड़के प्रपोज भी करते हैं और वो रिजेक्ट करती है। तो वो लड़का क्या बोल रहा है, बोल रहा है कि देखो तुम मेरे से शादी कर लो, फिर कोई तुम्हें परेशान नहीं करेगा, डिस्टर्ब नहीं करेगा, कुछ नहीं बोलेगा। तो ये नियम ऐसा है कि सुनो तुम विवाह कर लो मुझसे, फिर कोई ना कहेगा जानू, मतलब देखो तुम मेरे साथ विवाह कर लो तो फिर कोई तुम्हें परेशान नहीं करेगा, कोई तुम्हें जानू जानू नहीं बोलेगा। तो ये काफी इंटरेस्टिंग लगा था मुझे, इसलिए मैंने सोचा कि ये नियम शेयर करता हूँ आप लोगों के साथ। सुनो तुम विवाह कर लो मुझसे, फिर कोई ना कहेगा जानू। तो सुनो से आपको याद रखना होगा स्कैंडियम, तुम में आएगा टाइटेनियम, विवाह से आपको याद रखना होगा वी फॉर वैनाडियम, कर लो से क्रोमियम Cr, मुझसे में आपको याद रखना होगा मैंगनीज Mn, फिर से Fe, कोई से CO कोबाल्ट, ना कहेगा इसमें आपको याद रखना होगा निकल आएगा इसमें, कहेगा से Cu याद रखना होगा कॉपर, एंड जानू जानू से Zn जिंक। तो वो बच्चा एक अनोखे रूप में प्रपोज कर रहा है लड़की को, और डायरेक्टली ना बोल के इनडायरेक्टली बोल रहा है कि देखो तुम मेरे साथ शादी कर लो, तुम्हारे फायदा ही है, तुम्हें कोई और लड़का डिस्टर्ब नहीं करेगा। तो इसलिए वो लड़का बोल रहा है कि सुनो तुम विवाह कर लो मुझसे, फिर कोई ना कहेगा जानू। Okay, now we will see this 3D series in English. So in 3D series, we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Now how to remember is, remember there is a person or there is a science teacher whose name is Vivek Kriplani, and there is another person whose name is William or something, just remember. So he is the manager of fog company. So both were there in the bar, and then there was an argument in between those two, and then they started fighting. So that science teacher and that manager of the fog company, they started fighting. And while the fight, that science teacher Vivek Kriplani, he hits the manager, and he hit in the cuticle zone. So you have to remember, science teacher Vivek Kriplani hits manager of fog company near cuticle zone. So from the science, you have to remember this. SC stands for scandium. Teacher, from this teacher you can remember titanium. From this Vivek, it starts with V. So from V you have to remember vanadium. And Kriplani, in the Kriplani you can see Cr. So Cr stands for chromium. And from the manager you will get Mn, Mn for manganese. Fog company. So from fog you have to remember Fe. Fe represents iron. And company, from the company you will have Co. Co stands for cobalt. Near, from near you can remember Ni for nickel. In which zone? Cuticle zone. From the cuticle, Cu will be there. So from Cu you have to remember copper. And the zone Zn, from the Zn you have to remember zinc. So science teacher Vivek Kriplani hits manager of fog company near cuticle zone. And this part is actually called cuticle. This white part in the finger is called cuticle. Now, if we see an alternative version of this mnemonics to remember 3D series, so we can say the science teacher, that teacher is a very cruel person and very bad person, or he does bad stuff, bad things. So in a couple zone, there is a couple zone near the sea beach, and in that zone, you cannot feel or you cannot drink Coke. Okay, so that is forbidden in that zone. But because that science teacher is a very bad person, so he feels Coke near that couple zone. So that's how you can remember that science teacher, very cruel man, feels Coke near couple zone. Because he's a very cruel person, very bad person, so he violates the law and he does all this wrong stuff. So what he does? So science teacher, very cruel man, feels Coke near couple zone. So from here, SC stands for scandium. From the teacher, you have to remember Ti. Ti stands for titanium. From the very V, V represents vanadium. And cruel, in the cruel, you will have C and R. So the Cr stands for chromium. Don't get confused with this cruel Cr and Co. So Cr comes first, then Co comes. So from the cruel, you will remember Cr for chromium. Then from the man, you have to remember Mn stands for manganese. Now he feels Coke, so feels Fe stands for iron. Coke, Co stands for cobalt. And near, in the near, you have to remember Ni stands for nickel. Couple, in the couple, you have Ce and U, so that will give you copper. And zone, Zn stands for zinc. So in this 3D series, so chromium, cobalt, and copper. These three don't get confused with the positions of these three. So you have to remember this cruel man, cruel comes first, so Cr will come first, and then in Coke, Co, it will come in the middle, and then copper or couple, in couple you have C and U, so that copper will come at the end. तो चलिए अभी देखते हैं 4D सीरीज को। तो 4D सीरीज में हमारे पास है इट्रियम, जर्कोनियम, नायोबियम, मोलिब्डेनम, टेक्नीशियम, रुथेनियम, रोडियम, पैलेडियम, सिल्वर एंड कैडमियम। तो ये 10 एलिमेंट है 4D सीरीज में। तो यहाँ पे क्या हुआ, अभी इंडिया में कुछ लोग बैंक से पैसा लेके लोन लेके फरार हो जाते हैं, है ना। तो बहुत सारे कंट्री में ही होगा ये सब चीज, कुछ ना कुछ लोग, कुछ ना कुछ परसेंटेज लोग तो रहते हैं जो इलीगल काम करते हैं और बुरे काम करते हैं, तो हर कंट्री में होता है। तो ऐसे ही इंडिया में जो नीरव मोदी हैं, हम सब जानते हैं, वो इंडिया से काफी पैसा लेके फरार हो चुके हैं, दूसरी कंट्री में चले गए। तो क्या हुआ, तो वो नीरव मोदी ने जिस जिस एयरपोर्ट है, जिस प्लेटफॉर्म से टिकट लिया था, वो आपको दिख गया, पता चल गया। उस प्लेटफॉर्म देख के आपको पहले से पता था कि इस प्लेटफॉर्म से लिया है, और आप जब जा रहे हो उस प्लेटफॉर्म में, तब आपको प्लेटफॉर्म देख के पता चल गया कि अच्छा यहाँ से नीरव मोदी ने टिकट लिया था। तो अब ऐसे याद रखो कि इस काउंटर से नीरव मोदी ने टिकट लिया था, और टिकट लेके वो रशिया में चले गए, रशिया में उड़ के चले गए। तो उस टिकट काउंटर के पास जाके आप क्या बोल लो, आप बोलो यहाँ से जरूर नीरव मोदी टिकट लिए रशिया के राह पर आगे चले गए। तो आप उस काउंटर के सामने गए हो, काउंटर से आपको पता चल गया कि यहाँ से ही नीरव मोदी भागा था, तो आप बोलो यहाँ से जरूर नीरव मोदी टिकट लिए रशिया के राह पर आगे चले गए। तो यहाँ से में है वाई, वाई स्टैंड फॉर इट्रियम, जरूर में आएगा जेड एंड आर, जेड आर से आपको याद रखना होगा जर्कोनियम, और कौन, नीरव मोदी, तो नीरव में आएगा एन एन बी, एन एन बी से आपको याद रखना होगा नायोबियम, मोदी में आएगा एमओ, एमओ से मोलिब्डेनम, टिकट लिए तो टिकट में आएगा टीएनसी, टीएनसी से होगा टेक्नीशियम, और कहाँ चले गए, रशिया में, तो रशिया में आएगा आर यू, आर यू स्टैंड फॉर रुथेनियम, और रशिया की राह पर, तो राह में आएगा आर एन एच, तो आर एच स्टैंड फॉर रोडियम। तो इस जगह कंफ्यूज मत होइएगा, रुथेनियम कम्स फर्स्ट देन रोडियम, तो आर यू पहले आएगा फिर आर एच, और रुथेनियम या रुथेनियम देन रोडियम, और पर राह पर में आएगा पी एन डी, सो पी डी से पैलेडियम, आगे आगे में आएगा एजी, सो एजी स्टैंड फॉर सिल्वर, आगे चले गए, तो ये चले से आपको याद रखना होगा, इसमें सी है तो सी एन डी कैडमियम। तो यहाँ से जरूर नीरव मोदी टिकट लिए रशिया के राह पर आगे चले गए। नाउ एक और ऑल्टरनेटिव वर्जन देखते हैं। तो ऑल्टरनेटिव वर्जन में हम कैसे याद रख सकते हैं 4D सीरीज को, कि दो दोस्त हैं, बहुत पक्के दोस्त हैं, बचपन से दोस्त हैं, बहुत सालों के दोस्त हैं, और जब ये दोस्ती बहुत सालों की हो जाती है ना, जब इसमें रूठना, मनाना, झगड़ा करना, फाइट करना, सब कुछ बहुत कॉमन हो जाता है। बट अच्छे दोस्त और सच्चे दोस्त वही होते हैं जो इन सब के बावजूद भी एक दूसरे को हेल्प करें। कितना भी झगड़ा हो, आपको पता है कि आपको जब जरूरत होगा वो दोस्त आपके लिए खड़ा रहेगा। तो ऐसे ही आप अपने जो दोस्त है, आपके बेस्ट फ्रेंड है, उसको आप बोल रहे हो कि यारी जरूर निभाना मौत तक, रूठे रोए पर आगे चले। तो आप अपने दोस्त को, अपने बेस्ट फ्रेंड को बोल रहे हो कि दोस्त मेरे साथ रहना हमेशा, हमारी जिंदगी के लास्ट तक, जितना भी प्रॉब्लम हो, जितना भी हम एक दूसरे से रूठ जाए, जितना भी हम झगड़ा करें, रोए, फिर भी हम एक दूसरे के साथ आगे बढ़े। तो अब ऐसा बोल रहे हो कि यारी जरूर निभाना मौत तक, रूठे रोए पर आगे चले। तो यारी में आएगा वाई, सो वाई से आएगा इट्रियम। जरूर में आएगा जेड आर, जेड आर से आएगा जर्कोनियम। निभाना, निभाना में एन एन बी है, तो एन बी से आएगा नायोबियम। मौत, मौत में आएगा एमओ, एमओ से आपको याद रखना होगा मोलिब्डेनम। तक, तक में आएगा टीएनसी, तो टीसी से आपको याद रखना होगा टेक्नीशियम। और रूठे रोए, तो रूठे में आपको आर यू आ रहा है, तो आर यू से आपको याद रखना होगा रूथेनियम। और रोए, रोए में आर एच आप याद रख सकते हो, तो आर एच स्टैंड फॉर रोडियम। पर, सो पर में आएगा पी एन डी, पी डी से पैलाडियम। आगे, आगे में आएगा ए एन जी, ए जी स्टैंड फॉर सिल्वर। चले, चले से आपको याद रखना होगा कैडमियम, सी डी। तो यारी जरूर निभाना मौत तक, रूठे रोए पर आगे चले। Next, let's see this 40 series in English. So in 40 series, we have yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. Now, how to remember this? So in the jungle, there was an angry crocodile, and that angry crocodile, you all know that crocodile eats everything, whichever animal comes near the pond or the lake, he will just eat it. So what happened? The entire jungle got united, and they thought that they will give a lesson to this crocodile. So that's why this yak, zebra, numbat, monkey, all those came together, and then they discussed. Then they came up with a way that how to punish that angry crocodile. So after the meeting, they took a rusty road, and from that road they went. And then the crocodile was not expecting them to come from that road. These all animals went from the rusty road, and then they hit the crocodile from the behind, and the crocodile died there. So how you can remember? You can remember yak, zebra, numbat, monkey took rusty road to punish angry crocodile. This crocodile was very angry and very bad. He used to eat everyone. So that's why all these animals, yak, zebra, numbat, monkey, all they came together, and then they punished that crocodile. So yak, zebra, numbat, monkey took rusty road to punish angry crocodile. Now from this yak, Y is there. So Y stands for yttrium. Zebra, in the zebra we have Z and R. Z stands for zirconium. And numbat, numbat in the number we have N and B. So NB stands for niobium. Monkey. So from the monkey, MO stands for molybdenum. Now in this took you have to remember it's T and C. So TC stands for technetium. Rusty road. So rusty, in the rusty there is R and U. RU stands for ruthenium. Road, in the road you have to remember RH. RH stands for rhodium. To punish, in the punish you have to remember PD. PD stands for palladium. Angry crocodile. So in angry we have ANG. AG stands for silver. And crocodile, C and D. So CD stands for cadmium. So yak, zebra, numbat, monkey took rusty road to punish angry crocodile. तो चलिए अब हम देखते हैं 5D सीरीज और हिंदी में। 5D सीरीज में हमारे पास है लैंथनम, हाफनियम, टैंटलम, टंगस्टेन, रेनियम, ऑस्मियम, इरिडियम, प्लैटिनम, गोल्ड और मरकरी। तो इसको कैसे हम याद रख सकते हैं कि कुछ लोग यहाँ पे आए हैं, एक बच्चे को बुली कर रहे हैं, और बोल रहे हैं कि हम सब सीनियर है तुम लोग के, तो तुम्हें हमें हफ्ता देना होगा। अगर हफ्ता नहीं दोगे तो हम लोग और हमारे दोस्त लोग तुम्हें मारेंगे और पीटेंगे और फिर हंसेंगे तुम्हारे ऊपर। तो सीनियर्स आए हैं जूनियर को बुली करने और फिर बोल रहे हैं कि ला हफ्ता, वरना रेजाउल, ओस्मान एंड इरफान पीटेंगे और हंसेंगे। तो अगर हफ्ता नहीं देगा तो तेरे को हम पहले पीटेंगे और फिर तेरे ऊपर हंसेंगे। तो गाइस, बुली करना सबसे गंदी बात है। और अभी रिसेंटली तो बहुत सारे केसेस आ रहे हैं, या फिर बहुत से बड़े बड़े एजुकेशन इंस्टीट्यूट में भी रैगिंग होता है और बच्चों एक्सट्रीम स्टेप लेते हैं उसके बाद उस रैगिंग को झेलना पाके। और ऐसा काफी सारी चीज मुझे खुद पता है, काफी सारी स्टोरीज पता है मुझे, और काफी सारी चीजें सोसाइटी में मैंने देखा है खुद। तो ये बुली करना या फिर रैगिंग करना बहुत खराब बात है, बहुत ही खराब बात है, किसी को फिजिकली और मेंटली टॉर्चर करना। तो प्लीज 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 ये सब कुछ मत करना। दिस इज जस्ट टू रिमेंबर दिस 5D सीरीज। और लाइफ में कभी भी किसी के भी साथ, कोई कितना भी वीक हो, किसी के भी साथ बुरा या अन्याय मत करना। तो जस्ट रिमेंबरिंग पर्पस में हम ऐसा करके याद रखेंगे कि ये सीनियर्स अपने जूनियर को जाके बोल रहे हैं कि हफ्ता दे वरना हम पीटेंगे और हंसेंगे। और अपनी लाइफ में कभी भी ये चीज अपने जूनियर्स के साथ मत करना। ओके, सो ला हफ्ता, वरना रिजाउल, ओस्मान एंड इरफान पीटेंगे और हंसेंगे। तो ला हफ्ता में आएगा ला स्टैंड्स फॉर लैंथनम। हफ्ता में आपको याद रखना होगा दो एलिमेंट, हाफनियम एंड टैंटलम। वरना में आएगा डब्ल्यू से आपको याद रखना होगा टंगस्टेन। और कौन कौन? रेजाउल में आएगा आरी से रेनियम। फिर ओस्मान में ओएस से ऑस्मियम। एंड इरफान से आईआर से इरिडियम। पहले क्या करेंगे? पहले पीटेंगे, तो पीटी में आएगा पीटी से प्लैटिनम, और उसके ऊपर हंसेंगे तो और में AUR, और AU से आप याद रखना गोल्ड, और हंसेंगे में H और G, तो H G से आप याद रखना होगा मरकरी। तो ला हफ्ता, वरना रेजाउल, ओस्मान एंड इरफान पीटेंगे और हंसेंगे। Now let's see this 5D series in English. So in 5D we have lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. So there's a football match going in between Brazil and Australia, and Brazil was performing very well, and they were scoring in the first half time. They scored a few goals, So what happened? So the game was going to be one-sided. The Brazil was dominating over the Australian team. So what happened in the first half? They already scored 2 goals. So in the next half, the Australian team got high pressure and they have to give back those goals. They have to equalize those goals. So last half time, so you can remember like this, that last half time went remarkable. Oscar and Irfan put Aussies in high pressure because Oscar and Irfan they scored 1-1 goal. So Brazil has 2 goals and they have a lead of 2-0. And that's why in the next half or in the second half, this Australian team got high pressure. So last half time went remarkable. Oscar and Irfan put Aussies in high pressure. So in the last we have LA. LA stands for length. Half. In the half you can see H and F. HF, or if you remember the entire half, you can remember Hafnium. So from the half you can remember Hafnium. Time you have to remember TA. TA stands for tantalum. Wind. W is the first letter of this wind. So W stands for tungsten. Remarkable. And remarkable, RE is there. So RE stands for radium. And who scored the goal? Oscar. Oscar scored the first goal. So Oscar, OS, OS stands for osmium. And the second goal was scored by Irfan. So Irfan, IR, IR stands for iridium. Put, PT, PT stands for platinum. Aussies, AU, AU stands for gold. In high pressure. So in high, we have H and G. So HG stands for mercury. So in the match, what happened? Brazil's team got lead and they put the pressure the Australian team. Last half time went remarkable. Oscar and Irfan put Aussies in high pressure. नेक्स्ट अभी हमारे पास है 60 सीरीज. तो 60 सीरीज में क्या क्या है? एक्टिनियम, रदरफोर्डियम, डबनियम, सिबर्जेनियम, बोरियम, हेसियम, मेटनरियम, डमस्टर्डियम, रॉन्जेनियम एंड कोपर्निसियम. तो ये सारे एलिमेंट और ये 10 एलिमेंट है हमारे पास 60 सीरीज में. तो कैसे याद रख सकते हो? ये दोनों है इंडिया के फेमस टीवी सीरियल एक्ट्रेस. तो ये दोनों काफी अच्छे दोस्त भी हैं. दोनों बिग बॉस में साथ में भी आए थे, कंटेस्टेंट बने थे और काफी अच्छी गहरी दोस्ती है दोनों की. तो वही बिग बॉस के बाद ये दोनों गप्पे शप्पे कर रहे हैं रश्मि के घर में उनके छत में जाके. तो घर के छत में जाके दोनों गप्पे कर रहे हैं और नीचे से उनका पापा आए, रश्मि जी के पापा आए और फिर वो बोल रहे हैं कि अच्छा दोनों बैठ के गप्पे शप्पे कर रहे हो, हंसी मजाक चल रहा है, चलो जाओ मार्केट से मेरे लिए डर्मीकूल का बॉटल लेके आओ. तो रश्मि के पापा को डर्मीकूल का बॉटल चाहिए, तो इसलिए वो लेके आने के लिए बोल रहे हैं रश्मि को. तो पापा के क्या बोल रहे हैं? पापा के बोल रहे हैं कि अच्छा रूफ पे देवों के संग बैठ के हंस मत. मतलब वो जो हंसी मजाक कर रहे थे वो लोग, तो पापा सर गुस्सा के बोल रहे हैं कि देवों के साथ बैठ के भी हंस मत, डर्मीकूल का रंगीन कंटेनर ला, मतलब जा मार्केट से डर्मीकूल का बॉटल खरीद के ला. तो फिर से हम देखते हैं कि क्या हुआ. रश्मि एंड देवो वो लोग बातें कर रहे थे, हंसी मजाक कर रहे थे छत पे. तो रश्मि के पापा आके छत पे बोल रहे हैं कि अच्छा रूफ पे देवों के संग बैठ के हंस मत, डर्मीकूल का रंगीन कंटेनर ला. तो अच्छा में आएगा एसी, एसी से याद रखना होगा एक्टिनियम. रूफ में आएगा आरएनएफ, आरएफ से याद रखना होगा रदरफोर्डियम. और रूफ पे देवों के संग, तो देवों में डीएनबी, डीबी से आता है डबनियम. संग में आएगा एसएनजी, तो एसजी से आपको याद रखना होगा सिबर्जियम. और बैठ के कैसे है ना, वो लोग बैठे हुए हैं, तो बैठ के बीएनएच, बीएच से आपको याद रखना होगा बोरियम. हंस, हंस से आपको याद रखना होगा हेसियम, या जो एचएस हेसियम. मत से आपको याद रखना होगा एमएनटी, एमएनटी स्टैंड्स फॉर मेटनरियम. उसके बाद क्या बोल रहे हैं? डर्मीकूल का रंगीन कंटेनर ला. तो डर्मी में आएगा डीएस, डीएस आपको याद रखना होगा, या फिर आप याद रख सकते हो डर्मस्टर्डियम. तो ये जो डीआरएम पहले 4 लेटर है उससे भी आप याद रख सकते हो डर्मस्टर्डियम. डर्मीकूल का रंगीन, तो रंगीन में आएगा आरएनजी, तो आरएनजी, आरजी स्टैंड्स फॉर रॉन्जेनियम. एंड कंटेनर ला, तो कंटेनर में आएगा सीएनई, सॉरी सीएनएन, तो सीएन स्टैंड्स फॉर कोपर्निसियम. तो अच्छा रूफ पे देवों के संग बैठ के हंस मत, डर्मीकूल का रंगीन कंटेनर ला. So now we will see the 60 series in English. So in 60 we have actinium, rutherfordium, dubnium, sibergium, borium, hesium, meitnerium, drumsturdium, rhongenium, and copernicium. So how to remember this? So remember, so there was a contest, and in that contest, it's a fun contest. So in that contest, there was also prize, first, second, third prize distribution was there. So in that contest, Rutherford and Rongen, they participated together as a team. So in that team-wise contest, so Rutherford, he actually messed up. He did a bad acting. He forgot his part, and then his singing also he forgot. So both the mistakes, because of both the mistakes, wrong acting and wrong singing or doubtful singing. So both Rutherford and Rongen, they got dismissed from the contest. So there was no, Rongen didn't have any fault, but still because of Rutherford's fault, he got dismissed from the contest. So you have to remember that act of Rutherford. So both his acting and singing, doubtful singing, because of those 2 reasons, they got dismissed. So you can remember that act of Rutherford, doubtful singing, both his mistakes dismisses Rongen from contest. So Rutherford's act and doubtful singing, both the mistakes dismisses Rongen from the contest. Now let's see, in the act we have AC, AC stands for actinium. Rutherford, from the Rutherford you can remember Rutherfordium. Doubtful singing, so in the doubtful we have D and B, so DB stands for dubnium. Singing S and G, S and G stands for sibergium. In the both we have B and H, so BH stands for borium. In the his we have H and S, so HS stands for hesium. Mistakes M and T, so M and T stands for meitnerium. Dismisses D and S, so DS stands for drumsturdium. Rongen, so RNG stands for, or you can remember this entire name. From this Rongen you can remember rongenium. from contest. So in contest we have C and N. So CN stands for Copernicium. So act of Rutherford and doubtful sinking, both his mistakes, dismisses Rontgen from contest. So this is how you can remember the 60 series. Now we will look into F block elements. So in the F block we have only these two series, lanthanides and actinides. So we will see mnemonics for these two, lanthanides and actinides. तो अभी हम देखते हैं लैंथेनाइड्स और 4F सीरीज इन हिंदी. तो 4F सीरीज में हमारे पास है सीरियम, प्रसियोडाइमियम, नियोडाइमियम, प्रोमेथियम, समारियम, यूरोपियम, गैडोलिनियम, टर्बियम, डिस्प्रोसियम, हॉल्मियम, इर्बियम, थूरियम, इटर्बियम एंड लुटेसियम. तो हम कैसे याद रख सकते हैं इसको ना? ऐसा है कि चार दोस्त जो जॉन सेना, प्रभास और उनके साथ पैमी एंड सिमी, तो ये चारों लोग यूरोप में गए हैं और यूरोप में वो डाइनिंग कर रहे थे ग्राउंड टेबल में बैठ के. उनमें एक संडे के दिन वो यूरोप में गए हैं, राउंड टेबल में बैठ के अच्छा अच्छा खाना खा रहे हैं और उनका मेन डिश क्या था? मेन कोर्स में था टमाटर वाला यबी. सो दिस थिंग इज कॉल्ड टमाटर यबी, दिस डिश. तो वो लोग क्या कर रहे हैं? अच्छे से हॉलीडे एंजॉय करते हैं यूरोप में राउंड टेबल डाइनिंग करके और वहां पे जाके टमाटर यबी खा रहे हैं या फिर टमाटर यबी का मजा ले रहे हैं. तो ऐसे याद रखना है कि सेना, प्रभास एंड पैमी सिमी यूरोप के ग्राउंड टेबल डाइनिंग में हॉलीडे एंजॉय किया टमाटर यबी लूट के. मतलब उन्होंने बहुत ज्यादा करके खाया, टमाटर यबी उनको बहुत ज्यादा पसंद आया और ऐसे करके उन्होंने हॉलीडे एंजॉय किया ग्राउंड टेबल डाइनिंग करके. तो आपको याद रखना है कि सेना या फिर चलो जॉन सेना, प्रभास एंड पैमी सिमी यूरोप के ग्राउंड टेबल डाइनिंग में हॉलीडे एंजॉय किया टमाटर यबी लूट के. तो सेना में आएगा सीई, सीई से आपको याद रखना होगा सीरियम. प्रभास में आएगा पीएनआर, पीआर से आपको याद रखना होगा प्रेसिडियोडाइमियम. एंड में लास्ट में है एनडी, तो एनडी से आपको याद रखना होगा नियोडाइमियम. पैमी में आएगा पीएम, पीएम से प्रोमेथियम. सिमी में आएगा एसएम, एसएम में समारियम. यूरोप से आपको याद रखना होगा यूरोपियम, जो कि इजी है, यूरोप से ही यूरोपियम आएगा. और ग्राउंड में है जीडी, ग्राउंड टेबल के ग्राउंड में है जीडी, जीडी से आपको याद रखना होगा गैडोलिनियम. और टेबल में है टीबी, टीबी से आपको याद रखना होगा टर्बियम. डाइनिंग में डीवाई आपको याद रखना होगा और डीवाई से याद रखना होगा डिस्प्रोसियम. डाइनिंग में हॉलीडे एंजॉय किया, तो हॉलीडे के एचओ, एचओ से आपको याद रखना होगा हॉल्मियम. और एंजॉय में आपको याद रखना होगा ईआर, ईआर से इर्बियम. हॉलीडे एंजॉय किया टमाटर यबी लूट के, तो टमाटर में टीएनएम आएगा, तो टीएम से आपको याद रखना होगा थूरियम. और यबी में आएगा वाईएनबी, वाईबी से इटर्बियम. और लूट के में एलयू आता है, तो एलयू से होगा लुटेशियम, या फिर लूट के से भी आपको याद आ जाएगा कि लुटेशियम. तो जॉन सेना, प्रभास एंड पैमी सिमी यूरोप के ग्राउंड टेबल डाइनिंग में हॉलीडे एंजॉय किया टमाटर यबी लूट के. तो ऐसे आप याद रख सकते हो 40 सीरीज को. नाउ इफ यू सी द 4F, so ऐसे आप याद रख सकते हो 4F सीरीज को, 4F सीरीज. Now if you see the 4F series in English, so in 4F we have cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. So if you want to remember this, how we can remember? So what happened? There's a person whose name is Summer. So Summer went Europe. So that Summer, he is actually ceramic producer and promoter. So he was in charge of a big project. In that project, they had to make a great turbine. So in that project in charge, Summer, he went Europe and he gave the project charge to his juniors. He said that I'm going for a few days, you guys please manage. So what happened? When the boss is not there, the employees will not work properly, right? They will just reluctantly try to finish their job without paying attention to the details. So same thing happened when that ceramic producer and promoter Summer, when he went to Europe. So there's some problem happened, and in that big project where they have to make the great turbine, that in that turbine the juniors used cheap materials, and because of that the turbine disrupted. And luckily, one honest engineer, he saw it and he yelled it and he informed everyone, no, we are doing it wrong and this is not correct. This will harm people. So you have to remember that ceramic producer and promoter Summer went Europe. Meanwhile, so great turbine disrupts. Honest engineer team yelled luckily. So because of this team, honest engineer team, people got saved. So in the ceramic producer, CE stands for cerium, and the producer you have PR. PR stands for praseodymium, and NND, ND stands for neodymium. Promoter, and the promoter we have P and M, or even in the if you remember this prom, so from this prom you can get promethium. So what is the name of the promoter? Summer. So from the Summer you can remember samarium. Went Europe. In Europe, or from the entire Europe you can remember europium. So ceramic producer and promoter Summer went Europe. Meanwhile, great turbine. From this great you have to remember GD or gadolinium. Turbine, in the turbine there is T and B. The TB stands for terbium, or even from the turbine you can remember terbium. And disrupts, in the disrupts there is D and Y. I mean you can remember D and Y. It's not there in the word, but you can remember D and Y. So DY stands for dysprosium. Honest start with H and O. So HO stands for holmium. Engineer, in the engineer we have E and R. So ER stands for erbium. Team, in the team we have T and M. So TM stands for thulium. Yield, in the yield you can remember Y and B. So YB stands for ytterbium. And luckily, so in the luckily we have L and U. So LU stands for lutetium. So ceramic producer and promoter Summer went Europe. So meanwhile people were not working properly. So that's why great turbine disrupts. honest engineer Tim yelled luckily, and he saved the life of all the people. Okay, नेक्स्ट हम देखेंगे 5f सीरीज। तो 5f सीरीज में हमारे पास है थोरियम, और इनको एक्टिनाइड्स भी बोलते हैं। तो एक्टिनाइड्स में है थोरियम, प्रोटैक्टिनियम, यूरेनियम, नेपच्यूनियम, प्लूटोनियम, अमेरिशियम, कुरियम, बर्केलियम, कैलिफोर्नियम, आइंस्टाइनियम, फर्मियम, मेंडेलिवियम, नोबेलियम एंड लॉरेंसियम। तो इन 14 एलिमेंट्स को कैसे याद रखना है? तो हमें पता था कि एक मूवी आया था 2012, तो उसमें क्या हुआ था कि वर्ल्ड का वाटर लेवल इंक्रीज हो रहा था, और उस वाटर के नीचे सारे कंट्रीज आ जाएंगे, तो पूरा वर्ल्ड डिस्ट्रॉय हो जाएगा, ऐसा कुछ था कॉन्सेप्ट। तो उसमें क्या हुआ, जब वाटर लेवल इंक्रीज होना स्टार्ट हुआ, तो तभी सभी लोग पैनिक करने लगे कि अरे अभी तो पूरा वर्ल्ड डिस्ट्रॉय हो जाएगा, पूरा वर्ल्ड डिस्ट्रॉय हो जाएगा, जो भी करना है कुछ दिनों में करना है, धीरे धीरे पूरा वर्ल्ड डिस्ट्रॉय हो जाएगा। तो जब इनिशियली स्टार्ट हुआ थोड़ा पानी इंक्रीज होने के लिए, तो थोड़ा पानी ऊपर से नीचे गिरा, मतलब थोड़ा सा पानी अगर ऊपर से नीचे गिरा, थोड़ा सा पानी का लेवल बढ़ा, तो सारे लोग तो एकदम बौखला गए। तो उसमें क्या क्या इफेक्ट हुआ ना, पुराने आम कम बिके कैलिफोर्निया में, जो पुराने आम बहुत ज्यादा बिकते थे वो कम बिके। और साइंस कम्युनिटी में क्या हुआ, साइंस कम्युनिटी में आइंस्टाइन, फर्मी, मेंडलीव नोबेल के लिए लड़े। तो ऐसा भी याद रखना होगा कि जब वो पानी का लेवल बढ़ने लगा, सारे लोग बौखला गए, और उसके इफेक्ट में क्या हुआ कि पुराने आम कम बिके कैलिफोर्निया में, और जो साइंटिस्ट थे आइंस्टाइन, फर्मी और मेंडलीव, वो नोबेल के लिए लड़ने लगे एक दूसरे से कि अरे मुझे चाहिए, मुझे चाहिए, मुझे चाहिए, मरने से पहले मैं नोबेल लूंगा, ऐसा करके। तो क्या याद रखोगे कि थोड़ा पानी ऊपर से नीचे गिरा, पुराने आम कम बिके कैलिफोर्निया में, आइंस्टाइन, फर्मी, मेंडलीव नोबेल के लिए लड़े। तो थोड़ा से आपको याद रखना होगा थोड़ियम, पानी में पीए, पीए से याद रखना होगा प्रोटैक्टिनियम, ऊपर में आएगा यू, यू से याद रखना होगा यूरेनियम, ऊपर से नीचे गिरा तो नीचे में आपको याद रखना होगा एनएनपी, एनपी स्टैंड्स फॉर नेपच्यूनियम। पुराने आम कम बिके तो पुराने में आएगा पीयू, पीयू से याद रखना होगा प्लूटोनियम, आम से आपको याद रखना होगा अमेरिशियम, कम कम में आपको याद रखना होगा सीएम, सीएम स्टैंड्स फॉर कुरियम, बीके, बीके में बीएनके, सो बीके से आपको याद रखना होगा बर्केलियम। कैलिफोर्निया में, तो कैलिफोर्निया में सीएफ, सीएफ से आपको याद रखना होगा, या फिर पूरा कैलिफोर्निया से भी आप याद रख सकते हो कैलिफोर्निया। और कौन कौन लड़े ना, आइंस्टाइन, फर्मी एंड मेंडलीव। तो इन तीनों से आपको याद रहेगा आइंस्टाइनियम, फर्मियम एंड मेंडलीवियम, और मेंडलीवियम। तो किस लिए लड़े ना, नोबेल के लिए लड़े, तो नोबेल से आपको याद आएगा नोबेलियम, और लड़े लड़े में आएगा एल आर, तो एल आर से आपको याद रखना होगा लॉरेंशियम। तो कैसे याद रखना है 5F सीरीज को, कि थोड़ा पानी ऊपर से नीचे गिरा, पुराने आम कम बिके कैलिफोर्निया में, उस पानी ऊपर से नीचे गिरने का इफेक्ट कि पुराने आम कम बिके कैलिफोर्निया में, एंड आइंस्टाइन, फर्मी, मेंडलीव नोबेल के लिए लड़े। तो ऐसे आप याद रख सकते हो 5F सीरीज को। नाउ लेट्स सी दिस 5F series in English. So in 5F we have thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. So these 14 elements we have in 5F. Now how to remember? So there is an American company UNP. So that company, or three members or three partners from that company, they actually sent black coffee to these three scientists as a token, or for showing their respect. So these three partners from this UNP company, they sent black coffee because their company produces black coffee. So they send a sample to these three big scientists. So how you can remember? You have to remember that three partners of UNP American company sends black coffee to EFM Nobel laureates. So it's very easy to remember. You can remember three partners of UNP American company sends black coffee to EFM Nobel laureates. Now this three, in the three we have TH, TH stands for thorium. Partners we have PA. So from the PA you have to remember protactinium, and UNP. What is the company name? UNP. From this UNP, these are the initials of this uranium, neptunium, and plutonium. So because these three, in the solar system also, Uranus, Neptune, and Pluto, they are back to back. So from this UNP, you can easily remember these three elements: uranium, neptunium, plutonium. So three partners of UNP, American company. From the American, you can remember americium, and company CM. From the CM, you can remember curium, sends black coffee. So in the black we have B and K. So BK stands for berkelium, and in the coffee we have C and F. The CF stands for californium. To EFM Nobel laureates. Now in this EFM, you have to remember that this EFM is actually alphabetical. So E comes first, then F, and after that M is so E and F, they comes before M, and then M is coming. So EFM, as we were remembering three elements from this UNP company name, similarly EFM you can remember three scientists name. So E stands for Einsteinium, F stands for fermium, and M stands for Mendeleevium. So EFM Nobel laureates. So in this Nobel we have NO, or from the Nobel you can remember Nobelium, and in the laureates we have L and R. So LR stands for Lawrencium. So how to remember this 5F series? Now three partners of UNP American company sends black coffee to EFM Nobel laureates. Or this EFM stands for Einstein, Mendeleev, and Enrico Fermi. So this was all in this video, and in this video we have covered this D block elements along period and F block elements along period. Hey genius, welcome back to the lecture 5 of the series Periodic Table and Periodic Trends. In the previous video, means lecture 4, which is divided into three parts, we have discussed about the mnemonics for S block and P block elements in the part A, mnemonics for D block elements along period in part B, and mnemonics for D block elements along group, and mnemonics for F block elements in part C. All these mnemonics I have covered in both Hindi as well as English language. So if you have not seen that video, please go and see those videos. I hope that will help you to remember the elements in a periodic table. In this lecture 5, which is going to be a lengthy lecture, we are going to cover a lot of things. So we will start with showing the drawing of periodic table and what are the things you need to remember. That will be helpful. And then we will show the trick to find out the period and group of a given atomic number. We will also discuss the concept of isotope, isotone, and isobar. Then we will discuss the filling of electron, orbit and orbital concept, and Aufbau principle for the filling of electron. And at the end, I will also show a tricky way how you can easily remember this Aufbau principle, which orbital will be filled first and then which orbital will be filled. So there is a simple way to remember it. Thereafter, we will discuss nomenclature of super heavy elements, trivial name of different elements, lanthanide and actinide construction. After that, we will discuss Slaughter's rule and determination of shielding constant of electrons based on Slaughter's rule. And towards the end, we will discuss Goldsmith's geochemical and cosmochemical classification of elements based on chemical affinity. So these many things we are going to cover in this video. So without wasting any time, let's start. So this is going to be the image of a complete periodic table. This periodic table I have in my room, and you may have a different periodic table, but there are some minor details that you need to know, or color coding and different scheme coding that you need to know, that what this periodic table, what kind of information this is providing. So in your periodic table also you can find a small indexing from which you can know what are the informations given in the periodic table. I have already discussed about this indexing in the previous videos. You can go and check that what are the informations hidden in the periodic table. So as we know, in the periodic table we have 7 periods and 18 groups. So these rows are called periods and we have 7 periods, and these columns are called groups. So we have total 18 groups. Now group 1 is called alkali metals. Group 2 elements are called alkali earth metals. Now here group 11 elements are called coinage metals. Group 15 elements are called nitrogens. Group 16 elements are called chalcogens. Group 17 elements are called halogens, and group 18 elements are called noble gas. Now this group 1 and 2, these are actually S block elements. Group 13 to 18, they are P block elements, and in between them we have group 3 to group 12, these are D block elements. And inside this D block, in this space, we have these F block elements. Now when I used to practice remembering this periodic table, so I used to write all these elements with their atomic number and some of the atomic weights I used to remember. For example, from hydrogen to calcium, I used to remember both the atomic number and atomic weight. And after that, I used to remember atomic weight for iron, copper, zinc, bromine, here iodine, and you can see some more elements, for example, mercury, lead. So these elements, which we are going to come across very soon, very frequently in our chemistry practical or any other fields. So for that, I used to remember these atomic weights. Now, as you know, this group 18, where we have these noble gas elements, so these are the atomic number for those noble gas elements. Now we have to remember these numbers, because based on these numbers, we can find out the period and group of any given atomic number. So how to remember these things? So first and foremost, we have to remember this. And I will take a pen here. So we have to remember that element 1 and 2, those two elements are in period 1. Now from atomic number 3 to 10, those elements are in period 2. Now from atomic number 11 to 18, those elements are in period 3. From 19 to 36, those elements are in period 4. From 37 to 54, those elements are in period 5. So from 55 to 86, those elements are in period 6. And from 87 to 118, those elements are in period 7. So we have to remember these numbers. So if you remember these numbers, we can easily find out the group and period. For example, let's take zinc, the case of zinc. So its atomic number is 30. So 30 comes in between 18 and 36. So here, 30 comes here. So if you remember this numbering, from there we can count, that is 1, 2, 3, and 4. So zinc or element or the atomic number 30 will be an element which is housed in period 4. Now how to find out the group number? To find out the group number, you have to subtract the previous inert gas element's atomic number from the given atomic number value. For example, if you are given atomic number 30, so your A is 30, so you have to do A minus this previous inert gas element. So I'll write I. A minus I. Now as A you are given 30, so you have to do 30 minus, and the previous inert gas has atomic number 18, so I will just subtract 18 from here, and I will get 12. So this element will be in period 4, group 12. So for that, you just have to remember these inert gas elements atomic numbers. If you remember that, you can easily calculate the period and group of any given atomic number. Now, how to remember these values? To remember these values, you have to take help of your ideal life story or your ideal love life. For that, you can think that you are in love with a girl and two of you know each other since last 10 years. So what? Two of you madly love each other and you guys know each other since last 10 years. And when your girlfriend became 18, you guys get married. And at the age of 36, you have a happy family, two of you and your children. And at the age of 54, you have become grandparents. You have son and daughter and their son and daughter. You have grandchildren. And 86 is the age where you do coffin dance from staying inside the coffin. For example, I will just draw the sign of death. So the god of death comes and takes you at the age of 86. And when you were dying, so that time 118 people were there who were grieving at your death. So that's how you can remember these elements, atomic numbers. Two of you love each other since last 10 years. You guys get married at the age of 18. At the age of 36, you have a happy family. And at the age of 54, you have grandchildren and you have enlarged the family. At the age of 86, everything is over and you pass away. At that time, 118 people came to your last journey. So this is how you can remember the atomic numbers of the noble gas elements. Another thing I can say is see, this one is for another small tree. So this one is fourth period. So this one will be, just a second. So this one is the fourth period. So this is actually 40 minus 4. 40 minus 4, you will get 36. This one is the fifth period. So this one is actually 50 plus 4. And this one is although the sixth period, we will do 90 minus 4. 90 minus 4. So yeah, if you get confused whether it is 36 or 38, whether it is 56 or 54, that time you remember this thing, that this one is 40 minus 4, this one is 50 plus 4, and this one is 90 minus 4. So this is how also you can remember these three values. And these two are easy. This is 18. You just add 100, you will get 118. These two are also easy. Next, we will discuss about the concept of isotope, isotone, and isobar. So these three are actually very confusing terms, but very simple to remember if you know what is the basic difference between these three terms. So isotopes are actually same elements that contain equal numbers of protons but different numbers of neutrons. So in isotope, your proton number is same, but the neutron number is different. So in nucleus, for example, if you take hydrogen, here we have one proton and no neutron. Here we have one proton, one neutron. So this is called protium, this is called deuterium, this is called tritium. Here you have one proton and two neutron. So these three elements are called isotopes to each other. Here number of proton is same, but number of neutron is different. So these three are called isotopes. Now in case of isotone, so elements that have same number of neutrons and differ in the number of protons. So in case of isotope, we have same number of proton, different number of neutron. Here it is exactly opposite. So you have different number of proton, but the same number of neutrons. So these are called isotone. For example, if you take O16, N15, and C14, so in case of that, we have different number of protons, but we have same number of neutrons. So these are called isotone. Again, if you see silicon and phosphorus, we have different number of protons. Here we have 14 and here we have 15, but we have same number of neutrons, that is 16 in both the cases. So these are called isotone. Whereas in case of isobar, we have different elements. That means the number of proton is different, but we have same atomic weight. Now, atomic weight is a summation of number of protons and number of neutrons. So we have different number of protons, but we have same atomic weights. So that means we have both the proton and neutrons different, but the atomic weight is same. For example, if you take this argon and calcium, so here we have 18 protons and 22 neutrons. Whereas in case of calcium, we have 20 protons and 20 neutrons. See, both the protons, number of protons and number of neutrons, both are different. But this atomic weight, which is 40, that is identical. So we have only same atomic weight. So that's why these are called isobar. Here we have some more examples. You can take this one, cerium or selenium, cerium 76, selenium 76, or you can have this iron 58 and nickel 58. You can have argon 40, potassium 40, or calcium 40. And if you get sodium 24, magnesium 24, cobalt 64, nickel 64, these are all the pairs that are isobar to each other. So just a quick recap, in case of isotope, we have same number of protons, but different number of neutrons. In case of isotone, that is exactly opposite. We have same number of neutrons, but different number of protons. And in case of isobar, both the number of protons and neutrons are different, but we have same atomic weight. Now let's see some examples of isotopes. So we have already discussed about the isotopes of hydrogen in the previous slide. Let's see it again. So we have these three isotopes of hydrogen. In protium, we have only proton, there is no neutron. In deuterium, we have one proton, one neutron. And in case of tritium, we have one proton and two neutron. Now in case of carbon, we have carbon 12, carbon 13 and carbon 14. So if you see carbon 12, we have 6 protons and 6 neutrons. In case of carbon 13, we have 6 protons and 7 neutrons. And in case of carbon 14, we have 6 protons and 8 neutrons. Now let's see the isotopes of oxygen. So we have oxygen 16, oxygen 17 and oxygen 18. So in case of oxygen 16, we have 8 protons and 8 neutrons. Whereas in case of oxygen 17, we have 8 protons and 9 neutrons. And in case of oxygen 18, we have 8 protons and 10 neutrons. So these pairs are called isotopes to each other. Now let's see the IUPAC periodic table of the isotopes. So I will recommend you that you go in that website and you check this periodic table of the isotopes. So in this periodic table, it is given that one element, how many isotopes are there for each and every element. You can see these wheels. So the number of segment of these wheels tells how many isotopes are there. And you can see the color coding as well. Here the color coding is not properly visible. You can go and watch from the website that what is the meaning of these colors, different colors, pink, yellow, blue, white. So I strongly recommend you that you go and just take a look of this IUPAC periodic table of isotopes. Next, we are going to discuss about the filling of electrons in an atom. The first thing is that the number of electrons, how many electrons we have, that determines the number of orbits. Depending upon the number of electrons, the number of orbit will be determined. And the number of protons, depending upon the number of protons, the electrostatic interaction between the nucleus and the electrons will differ. So if you have more number of protons, the electrostatic interaction will increase, and when you have lesser number of protons, the electrostatic interaction will decrease. For example, you can see here in case of hydrogen, we have one proton and one electron here in first orbit. In case of helium, we have 2 protons and 2 neutrons in the nucleus, and we have 2 electrons in the first orbit. In case of lithium, we have 3 protons and 4 neutrons. You see these red ones are the protons and these blue balls are the neutrons. So we have 3 protons and 4 neutrons, and we have 2 electrons in the first orbit, this one, and another 1 electron in the second orbit, this one. Now in case of beryllium also, the next electron also comes in the second orbit. So now we are going to learn how these electrons will come and how many electrons we can fill in orbitals. So those things we are going to learn. So if you see this diagram, so first we have hydrogen. In case of hydrogen, we have only 1 electron. That 1 electron will come and fill in this first orbit. I'll make a cross sign to denote the electrons. In case of helium, we have 2 electrons, and both the electrons will be filled in the first orbit. 1 electron here, another electron here. Now in case of lithium, when we add another electron, so first 2 electrons will go in the orbit number 1. You can see here, first 2 electrons will be filled in the first orbit. Now the next electron, the third electron, will be filled in the second orbit. Now one by one we'll put electrons in the second orbit, and you can see after the lithium we will get beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And let's see in the case of neon. So in the case of neon, we have 2 electrons here, 1, 2, and we will have 8 electrons. One by one we have put 8 electrons in the second orbit. 3, 4, 5, 6, 7, and 8. So in case of neon, first 2 electrons are in first orbit, and next 8 electrons are there in the second orbit. Now when we have another electron coming, in case of sodium, so that 1 electron will actually occupy the third orbit, and then we will put 1 by 1 electrons in the third orbit. So as you go along this period, you put 1 by 1 electrons in the same orbit, and after this inert gas, when you put 1 more electron, that electron goes in the next orbit. So here you can see the putting of electrons here. For example, here in the hydrogen there is 1 electron. In helium we have put 2 electrons. Now when we add another electron in case of lithium, that goes and takes the second orbit. Now we put electrons 1 by 1 in the second orbit, 5 electrons in case of nitrogen, 6 electrons in case of oxygen, 7 electrons in case of fluorine, and 8 electrons in the second orbit in case of neon. And then when we want to put 1 more electron, that will go and take house in the other orbit, third orbit. And again we will fill electrons here. And in case of argon, we will have 2 electrons in the first orbit, 8 electrons in the second orbit, again 8 electrons in the third orbit. And again when we put 1 more electron in case of potassium, that will go and fill the fourth orbit. So likewise, we fill electrons 1 by 1 in one atom. This is just for conceptualization. Now we will go into more details. Before that, if you see the periodic table of elements, atomic radius, so this periodic table gives you the size of the elements. If you see these left ones, they are in bigger size, or these spheres are bigger in size. That means their atomic radius is bigger. And as you go along a period, here from left to right, the size decreases. Now, why it happens? So from left to right, when we are going, now we are putting more and more electrons as well as protons. From left to right, the number of proton is also increasing. So when we increase the proton number, so that time the electrostatic attraction between the nucleus and the electrons increases. So as the attracting power increases, so it's like a, see, we have proton here, and then surrounding it we have electrons, right? Just sorry, where is it? Just a second. So we have nucleus, and then surrounding that we have electrons and different shells of electrons. Now assume this nucleus is a girl, and these electrons, those are actually boys. Now when we put more and more protons, so the girl is more and more attractive. So that time this nucleus, sorry, these electrons, means the boys, they try to come close. So these shells will come close. These orbits will try to come close because the girl is very attractive. The more number of protons are there, as the girl is more attractive, the electrons, the boys, they will try to come close to that girl. So the orbit will shrink because the electrostatic attraction is more. The electrons will try to come close to the nucleus, or the positively charged nucleus, or positively charged protons. So as the girl is more and more attractive, as the number of proton is more, the electrons or the boys will try to come more and more close. So that's why the size actually shrinks from left to right in a period. These things I will discuss in detail in the next lecture, lecture 6. Do not miss that. That is a very important lecture, and I will discuss each and every periodic trend and their why is it happening, and the detail I will discuss in the next lecture. This is just to give you a preliminary idea that how if you increase the number of protons and electrons, so how the size will shrink, and if you increase more and more electrons, how it will be filled in the orbitals or orbits. So next we will come to the discussion of orbits and orbitals. So for this, let's think this is your home. Just let me draw a home for you. Just think this is your home, and this one over here is your school. School generally has a bigger gate, right? And all the classrooms, they have small windows. Oh, sorry, my drawing is pretty bad. So this is your home and this is your school. Now from home to school, you can go either by walk, or you can take a cycle and roam here and there, here and there, here and there, and then you can go to the school. Or when your father is free, he can tell you that come son, we will go by our car today. So you can take a car and you can take a main road and you can go like this, right? So there are different possibilities. From home to the school, the distance is same, but still there are different possibilities, right? You can go simply by walk, or you can go by cycle, or you can go with your father with a car. So different possibilities are there. So similarly, for the electrons also, they have different possibilities or probabilities. So they can occupy different paths or different portions of an orbit. Now let's try to understand the definition of orbit and orbitals. So an orbit is designated as the path for electrons to revolve around the nucleus. So this is actually a two-dimensional conception, that the electron is rotating around the nucleus. So here this yellow one is the nucleus and the electrons are rotating around it. So if I draw like this is the protons or the nucleus, sorry, and in this path the electrons are circulating. My drawing is pretty bad in this one. Actually, I'm using a very bad setup. Yeah, so this one is your proton and your electron is revolving around it. So this is a two-dimensional picture, and this one here is called orbit because this is a two-dimensional thing. I have just given what is designated the path in which the electron is revolving around the nucleus. Whereas an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So inside this same path, we have different three-dimensional space. For example, in your case, you can take different travel mode to reach to the school. Similarly, electron can take different 3D space to orbit that nucleus. So an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So as we discussed that orbitals are the 3D space occupied by electrons where the electron density is maximum. So inside one orbit, there can be different orbitals. For example, when we have orbit number 1, 2, and 3, which are also known as K, L, and M. So in that case, in orbit 1, we have only one s. So that is only one orbital, 1s. In case of second orbit, we have 2s and 2p. In case of third orbit, we have three different orbitals, that is 3s, 3p, and 3d. Similarly, in the fourth orbit, we have 4s, 4p, 4d, and 4f. Now let's see the shape of s orbital. So s orbital is actually spherical in nature. So this one you can see spherical shape. This is the shape of s orbital. So electron density is almost same in all directions, and it takes a shape of a sphere. Now this is for 1s. So if you go to the 2s, that will be a bigger sphere. Compared to 1s, the 2s will be a bigger sphere. Similarly, the 3s will be much bigger sphere. Now let's see the p orbitals. P orbitals are having three different compartments. So these are called px. This one is px. This one is py. Sorry, this one is pz, and this one is py. Oh, sorry. So p orbital has px, py, and pz. These three different compartments. Now these p orbitals, they look like a dumbbell. You can see in center the electron density is 0, and as you go further from the nucleus, the electron density increases. So it actually looks like a dumbbell. So in the center, the electron density is 0, and as you increase the r, as you go away from the nucleus, the electron density increases. So these are kind of like this, dumbbell shaped. So if there is only one dumbbell, that is p orbital, and in case of d orbital, there are actually two dumbbells. So as I have drawn this shape, this looks like the d orbital. Now in case of d orbital, so we have five different orbitals. So these are named as dxy, dyz, dzx, dx square minus y square, and dz square. Similarly, f orbital, it has 7 different compartments. So these things I will discuss in some later videos. I will make dedicated videos to discuss these things. But for the time being, we will see this video, which I have taken from this channel, scienceviz.com. I will put this link in the comment or description. If you want, you can go and check this video. It's a very nice video. From this, you can conceptualize how these electrons are revolving. Now, I'll show it. So first, we have this electron. Here, this one is the nucleus, or just write P, or proton, positively charged nucleus, and this electron is revolving around it. Now, in the 2D space, we can see the electron is circularly moving, but actually in the 3D space, it will create a sphere. So the electron density will be like a sphere. Let's see. In case of 1H, we have one proton and one electron. So the electron is circulating that proton. So in the 2D direction, we can see only like a circle, but when we see the 3D space, it is actually a sphere, and the electron density is equivalent in the entire sphere. So this is in case of proton. In case of 1H, hydrogen, only one electron. Now, if we add another electron, so that means we have two protons and two electrons. We are adding another electron. In case of helium, both the electrons will occupy 1s. That's why we write 1s2 in case of helium. Now, when we add another electron, that will come, and that cannot take 1s because 1s is already filled. So that will take 2s, and that we get lithium, 3 protons and 3 electrons. Now we add another electron, that will also go and take 2s. So we get beryllium, 2 protons and 2 electrons. Now when we add another electron, that goes in the p to p. In case of boron, that takes p, or it can be sp2 hybridized. This is how it will look in the sp2 hybridization. Now when we add another electron, in case of carbon, it can either take sp2 and 2p. This is the 2p and sp2, or it can become sp3 hybridization. This is how it looks when carbon is sp3 hybridized. Or it can be sp2 hybridized and one electron can be in the 2p. This is how it will look. Or it can be sp hybridized and 2 electrons can remain in the 2p. This is how it will look. So there are different hybridizations. Based upon that, the electrons can occupy different 3D space or different orbitals. So these things, just take a note. These things we will discuss in detail for some other videos in other chapter. So that time I will discuss in details about these things. Now let's see the electronic configuration. So in case of hydrogen, we have seen that the hydrogen, the electron will go in the 1s orbital. So that we write like this. So this box means one orbital, and this one is 1s orbital. So in case of hydrogen, the first electron goes in 1s. Then in case of helium, we have 2 electrons. So both the electrons goes in the 1s orbital. And each and every orbital can take only 2 electrons, or up to 2 electrons. When we have another electron, that will go in the 2s. Now, when we add another electron, that goes also in the 2s. And these arrows actually denote spin. So for electrons, you have to write like this. This is called up spin, and this is called down spin. When we have only one electron, we write it as up spin, and when the second electrons come, we add the down spin. In the same orbital, both electrons cannot have same spin. Okay, just try to remember this, that if there are two electrons, both electrons cannot have same direction. One will be up, one will be down. So in this case, this is up spin, and when we add another electron, that electron becomes down spin. In case of boron, we add another electron in the 2p, and this one is the 2p, which has 3 orbitals, 2px, 2py, 2pz. And in total, it can accommodate 6 electrons. So let's see, in case of proton, the electronic configuration is 1s1. In case, sorry, I'm saying proton is actually in case of hydrogen. I'm sorry. In case of hydrogen, the electronic configuration is 1s1. In case of helium, the electronic configuration is 1s2. In case of lithium, another one electron comes and that occupies 2s. So the electronic configuration becomes 1s2 and 2s1. In case of beryllium, the next electron also takes 2s, so 1s2, 2s2. In case of boron, the next electron takes 2p, so the electronic configuration becomes 1s2, 2s2, and 2p1. In case of carbon, we have 1s2, 2s2, 2p2. In case of nitrogen, it will simply become 2p3. In case of oxygen, it will become 2p4. In case of fluorine, it will become 2p5. And in case of neon, it will become 2p6. Now, in this case, 1s2, 2s2, 2p6, total electrons are 10, and it is inert gas element. After that, whenever we add another electron, that will go in the 3s. So in case of sodium, we get 1s2, 2s2, 2p6, 3s1. Then in case of magnesium, it will become 3s2. In case of aluminium, when we increase another electron, that time it goes in the 3p, and we get 1s2, 2s2, 2p6, 3s2, 3p1. Then in case of silicon, we add another electron in the 3p, and we add another electron in phosphorus, sulfur, chlorine, and argon. So again, in case of argon, the last electron is going in 3p, and we get the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now, as the 3p6 happens, so the orbital is closed. Now, if we add another electron, that will go in the next orbital, that is 4s, 4s1. So in case of potassium, we get 4s1. In case of calcium, we get 4s2. So this is called the filling of electrons, how electrons are getting filled one by one, in which orbital, and which orbital will come first, which orbital will come next, that we are going to learn later in this video. So the thing you have to remember is that how these electrons are getting filled, and it cannot accommodate more than 2 electrons. The orbitals cannot accommodate more than 2 electrons. So to understand this filling of electrons, we will learn Bohr principle. Now we have seen that in the first period we have 1s, in the second period we have 2s and 2p, or second orbit. In the third orbit we have 3s, 3p, 3d. In the fourth orbit we have 4s, 4p, 4d, and 4f. Similarly, in the fifth orbit we have 5s, 5p, 5d, 5f, and 5g. Now when we are filling electrons, first we fill 1s, next we fill 2s, next we fill 2p, and then 3s. So we are coming actually from this end. First we fill this, and then we fill this. Then we fill 3p. After filling 3p, so you cannot simply fill 3d. You have to go to 4s. And now after filling 4s, you cannot simply fill 4p. You have to actually fill 3d first, then 4p, and then 5s. So that is why this arrow. So this arrow means first we are filling 1s, then we are filling 2s, then we are filling 2p, then 3s, then 3p, then 4s, and then 3d, then 4p, 5s. This seems very hard to remember, right? So that's why you can remember this alternative path. This is how I remember this electron filling orbitals. So I remember like this s. So this is a lonely s, just one s. Now here s has p, so s is not single anymore. When it has a partner, I write square because it is not single anymore. So first it is s, then sp square, sdp square, sfdp square. Then what? Now what does it mean? So first, when the electron will come, that will fill s, and again it will be sp square. Means next line it will be s and p, and again there will be another sp because it was sp square, right? So s, then sp square. Now sdp square. So next line there will be s d p, and again another sdp because it was square. Next it will be sfdp square. So again next I have to write s, then f, then d, and p. Similarly, I have to write another SFDP, which I'm not writing. Now, what I will do, so this is kind of pyramid-like order, right? First, we have S on top, then SP, again SP, then SDP, again SDP. Now, you have to remember, so these S and P are actually NS and P. Means this one is the first row, right? So this one will be 1S. Now, this S and P, these are in the second row. So it will be 2S, 2P. This one in the third row, 3S, 3P. And next, this one is the fourth row. According to which pyramid I'm writing, this one comes in the fourth row. So this one will be 4s. Now in case of D, you have to write n minus 1. In case of S and P, it will be ns and P. In case of D, it will be n minus 1D. And in case of F, it will be n minus 2F. So this one is the fourth row. So I will write 4s. And n minus 1 means 4 minus 1, so 3d, and then 4p. Now again, this one is the fifth row according to my pyramid, so I will write 5s. This one will be n minus 1, so 5 minus 1 means 4d, and again this one is the np means 5p. And in case of this one is actually 6s, and in case of f, we have to write n minus 2. So in the sixth row, it will be 6 minus 2 means 4f. And d will be n minus 1, so 6 minus 1, it will be 5d. And again, np, so 6p. So I remember this pyramid, and whenever I'm doing any electronic configuration, I will quickly draw this S, SP, SP, SDP, SDP, and SMTP. So first, electron will be filled in 1s, then 2s, then 2p, then 3s, 3p, then 4s, 3d, 4p, after that 5s, 4d, 5p, then 6s, 4f, 5d, and 6p. So you can remember either this alpha principle, you can write down and then put these arrows to determine that where the electron will be filled first, or you can do like this pyramidal way: S, SP square, SDP square, S, SP square, SDP square, SFDP square. And then when you break the squares, you have to write this in two different rows, and it will be filled one by one according to the row. So any one way you can choose to remember this electronic configuration filling or electronic filling. You can choose anyway, whichever seems easy to you. Now we will discuss about the nomenclature of super heavy elements. For example, if someone says what will be the name of the element whose molecular weight, whose atomic weight or atomic number, whose atomic number will be 200, or whose atomic number will be 600 or 500, what will be the name? Now to determine these higher elements or super heavy elements, we came up with this nomenclature system. According to this, so if you see this one, 200, atomic number is 200. So first we will separate it later by later. First we have 2, then we have 0, then we have 0. So there is coding, nomenclature for each and every number. So for 0, we will write un. For 1, we will write nil. For 2, we will write bi. For 3, we will write tri. For 4, we have to write quad. For 5, we have to write pent. For 6, we have to write hex. For 7, it is sept. For 8, we have to write oct. For 9, we have to write n. So whenever we are saying that what will be the name of this atomic number 110, so we will separate it by number. So first there one number, then another one, then 0. For 1, we will write un. First for 1, we are writing this un. For another one, we are writing another un. So another un. And for 0, we have to write nil. So we are writing nil. And at the last, you have to use yum, IUM or UM. If I is already present, you have to write UM. I think there will be I here. So again, let's see for 117. If you see 117, for 1, we have to write this un. For another one, we have to write another un. And for 7, we have to write sept. And then we will add this suffix yum. So the name will be unseptium. Similarly, now we will do the atomic number 200. So for 2, we will write bi. For 0, we will write nil. For another 0, we will write another nil. So we will get bi nil nilium. Right? Let's take this one, 109. For 1, it will come un. For 0, there will be nil. And for 9, we have to add n. And then we will add suffix yum, IUM. So the name will be un nil n yum. Fine. And this symbol will actually take the first letter of each numerical root. For example, if you see for atomic number 200, bi nil nilium. So in the bi, the first letter is B, and in case of nil, the first letters are N. So it will be B and N. Similarly, in case of 109, unil enium, it will be U, N, E, the first letters of these roots or codes. So this is how you do the nomenclature of super heavy elements. So you don't have to assign any name. You can just simply call it by its atomic number. Now we will discuss about the trivial names of different elements. So the alkali metals, so the group 1 metals are called alkali metals. Now hydroxides of these metals are strongly alkaline. So that's why these group 1 elements are called alkali metals. Now group 2 elements, those are called alkaline earth metals. So the substances that remained unchanged by fire were called earths by the ancient chemists. The oxides, that is lime, magnesia, strontia, baryta, these actually refer to the earths, and these oxides are alkaline in reaction. So these alkali earth metals or the group 2 elements, their oxides are also alkaline in nature. So thus the term alkaline earths actually refers to the oxides of the metals. It may be noted that barium oxide is amphoteric. So in this group 2, the exception is the barium oxide, whose oxide is the exception is the beryllium, whose oxide is the amphoteric in nature. Other than that, the rest of the elements, they make alkaline oxides. That's why the name of this group is alkaline earth metals. Now group 16 elements are called chalcogens. Greek word chalkos means copper. I'll just take this laser pointer. Greek word chalkos mean copper. In nature, copper is usually found associated with sulfur and its congeners. So that's why we call these group elements or 16 group elements which contains sulfur and the other elements, we call them by chalcogens. Now elements of group 17, those are called halogens. So Greek word halogen means salt producer. Element of this group react with the metals to produce ionic halide salts. This justifies the name halogens. So in fact, the term halogen was first given to chlorine for its salt forming ability, salt forming ability with the metals. The term was subsequently extended to all members of the group. Now we have noble gases or inert or rare gases. So group 18 elements are called noble gases. They are named so for their chemical inertness. Because they are chemically inert, they don't react with most of the elements. That's why they are called inert gases or noble gases. Lanthanum series. So the elements from lanthanum to lutetium are called lanthanum. So it is named so because the chemically similar elements appear after lanthanum. So after lanthanum till lutetium, all these elements are chemically similar. So that's why they are named from the name of lanthanum. And they are called lanthanum series or lanthanides. Next, lanthanides or rare earths. The cerium to lutetium. So the word earths refer to the oxides, and in fact these elements were first discovered as their oxides. So this is why these were called rare earths. So however, these are not rare and they occur widely in nature, usually together. Similarly, we have seen alkaline earth metals. So those were also available in oxide forms. Similarly, these are also discovered in their oxide forms, and these are called rare earth metals. Now, actinum series, actinum to lawrencium, these are called actinum series. Actinides or actinoids from thorium to lawrencium, these elements are called actinides. Now, lawrencium was originally represented by Lw, but now, as per IUPAC recommendation, it is presented by Lr. Now we'll see the coinage metals, copper, silver, and gold. These are in group 11. So these are called coinage metals. So these are known as coinage metals because of their former uses in making the coins used in primitive currency. So in earlier days, when a human used to make coins or currency, they used to use these metals, copper, silver, and gold. Platinum metals, so ruthenium, rhodium, palladium, osmium, iridium, platinum. These group 7b in the Mendeleev's periodic table or group 8, 9, and 10 elements, these are called platinum metals. So in this family, platinum is the oldest one and it is also the most abundant one in this family. Its chemistry is also most extensively studied among the members. This is why the whole family is known by its name. Noble metals, so platinum metals, gold, silver, and mercury, these elements are also known as noble metals. Transuranium metals, so elements after uranium is called transuranium metals. Now we will discuss about another major topic, that is lanthanide and actinide contraction, which is also known as F contraction. Now what is this? So if we consider lanthanides from cerium to lutetium or actinides, which is from thorium to lawrencium, their atomic and ionic radii gradually decreases along the series with the increase of atomic number. So if you go from left to right in these lanthanides, the atomic radius and ionic radius decreases very much. So this is called F contraction or lanthanide and actinide contraction. The same trend can be also observed in case of d block elements. So this D contraction is known as Scandite contraction. Now let's see what are the reasons. The reasons are poor shielding power of n-2f orbitals, and you can also see relativistic contraction of ns orbital. So I'll try to explain it. Let's see. This one is your, sorry, let me draw it. Let's just give you a basic idea about this. So this one is our positively charged nucleus. Think it as of an attractive curl, and there we have different layers of electrons, different orbits. Now we have some electrons here, some electrons here. Now try to understand. So the poor shielding power of n-2f orbitals. So let's suppose we have some electron here and here. Now these electrons, let's consider these are the f electrons, n-2f electrons. Now these electrons, if they don't charge this positive charge, so this positive charge is showing some attraction. It's attracting all the electrons, right? Now it is attracting this one, this one, this one, this one, all of these electrons. Now these previous electrons, they are screening the positive charge of the proton. Now if they fail to screen that, if their shielding power is not good, then this proton will have higher attraction to this electron, to this outermost electron, right? Now just forget all these things. Now consider these two. These are the f electrons. Let's consider it as f electrons, and these are the next maybe s or p electrons. Okay. Now these f electrons, if they have stronger shielding power, that means if they can they can reduce this attraction of this nucleus to these electrons, that time we will say that these electrons have stronger shielding power. But actually these f electrons, those are actually diffused in nature and they have very less shielding power. So that's why the attraction of this nucleus to this outermost electron increases. Now let's try to understand it in simple words. For example, this is an attractive girl and these are the some lovers of that girl. Okay, now if these lovers, they don't have money, if they don't have sufficient money, then this girl will go for other boys, right? Now if this boy has money and these f electrons or f boys, they don't have money, then this girl will give importance or will get attracted to the other boy, this outermost boy, right? So the girl will try to make him close, the rich boy, which is in s or p orbital here. Again, I will try to explain. So these are different boys. If those boys, they will not read much, they will not get educated, then they will not get good job, they will not have money. So then this girl, this attractive girl, will not be interested in these boys. So that time this girl will get attracted, or that girl will attract these boys, these S and P orbital boys, which have good job and they have good money. Similarly, in the electronic world, if this F electrons, they are actually diffused in nature, they cannot shield this attraction of this nucleus to these electrons, to the outermost S and P electrons, because these F electrons are diffused in nature. So that poor shielding power of n-2 orbital electrons, because of that, these electrons get attracted and this radius actually decreases. Now these orbits or orbitals gets shrinked. The entire orbital or the radius RDF or radial distribution function of this orbital gets shrinked. Because of that, these electrons come closer, the atomic and ionic radius of these F block elements decreases. Because this F electron, they are not reading properly, they are not putting their effort in reading, and that's why they have lesser shielding power. That's why you all please read properly, be properly educated, and whatever you will do in life, it will be great. So take a proper education. Don't be like this F electrons, okay? Then your girl will also get attracted to the other S and P electrons. So because of this, as these other S and P electrons, they experience higher attraction towards the nucleus. That's why there is a relativistic contraction of NS orbital. So this orbital contracts, and the size of the atomic and ionic radius decreases. So these are the reasons. These are the main two reasons behind F contraction. Now what are the results? So 5D members are almost similar in size to the 4D members. So the same kind of contraction happens in the D block elements also, which are known as Scandite contraction. Because of that, so the 5D members and the 4D members are in the similar size. Actually, the 5D members should be bigger in size because they have additional orbit, but still it is almost similar in size. Now the size is same, but the atomic number is more, atomic weight is more. So that's why the density gets increased. So high density in the post-lanthanides. And due to the enhanced effective nuclear charge experienced by the valence shell electrons, post-lanthanides are noble elements. Now this point let's try to understand. So you see this nucleus that is attracting these electrons, these furthermore these valence electrons. So now these electrons are having higher affinity to the nucleus. So that's why these electrons will not be get lost. So you cannot simply just remove this electron. You cannot easily remove these electrons. That's why it is difficult to remove these valence electrons in case of noble elements, and that's why they are not reactive. The reaction is nothing but exchange of electrons. So because the attraction is more, it will not easily get lost. The electron will not get easily exchanged. So that's why these elements are called noble elements. Now let's see some other results. Due to greater effective nuclear charge, post-lanthanides have abnormally high electron affinity. The electron affinity is high because you can put more and more electrons as the electrostatic interaction is higher, so it can accommodate the electrons. Now because of F contraction, covalency increases from lanthanum to lutetium. So as the size becomes smaller and smaller, it tries to make covalent bond from lanthanum to lutetium. If you go, it tries to make covalent bond. It will not try to make ionic bond because it will not try to give up the electrons, which are tightly bound. Now covalency proportional to acidity of oxides. So acidity also increases from lanthanum to lutetium. Next is the thermal stability of carbonates and sulfates decreases from lanthanum to lutetium. Standard reduction potential of M3 plus 2M increases from lanthanum to lutetium. So these are the results which are occurring due to this lanthanide and actinide contraction. So take a note of this thing and just try to understand that this nucleus is like an attractive girl because these F electrons, they have not read properly during their class or during their courseworks. That's why these F electrons are diffuse in nature. They have very less shielding power. They have very less money. So this girl is attracted towards the other electrons, SP electrons, outermost electrons. And because of that, there is a relativistic contraction in this orbit or orbital, whatever you say. and those elements will become inert in nature. Hope this idea is clear. This is difficult to understand. This idea is a little bit tricky to understand. If you are lower standard, if you are in a lower standard, then you just note down the points. Maybe when you will go in your bachelor's or master's, that time you will get to know these things. Next, we will discuss Slaughter's rule. Now, this rule provides the numerical values for the effective nuclear charge in many electron atoms. It was formulated by John C. Slaughter in 1930. I'll take the laser pointer here. Sorry. So, according to this formula, Z effective is equals to Z, which is the atomic number of that molecule, minus S. S is the shielding constant. So, how to determine the S? So, to determine the Z effective, we already know the Z, the atomic number of the atom, and we just have to determine this shielding constant S. So, firstly, electrons are added according to their principal quantum number. Remember, not following the Aufbau principle. Okay, they will just simply grouped according to their principal quantum number, and taking S and P in the same shell. So the order will be like that: first we have 1s, then 2s and 2p in the same shell, 3s and 3p will be in the same shell, and then will come the 3d. So according to the Aufbau principle, after 3s and 3p, 4s will get filled, right? But here we are not following the Aufbau principle. Okay, in case of Slaughter's rule, you don't follow the Aufbau principle. You just arrange it and then calculate. So 3s, after 3s and 3p, you will put 3d. Then again you will put 4s and 4p together. Then you will put 4d. Then you will put 4f. So D and F are separately. Only S and P you can put together. Okay, D, F, G, these things you will put separate. Then you will again put 5S and 5P. Then you will put 5D and then 5F. Now let's see the quantitative value of this shielding constant. Okay, so the shielding constant for each group determined as, the first one is an amount of 0.35 from each extra electron within the same group. So if the electron for which you are counting the shielding constant, it is sharing the house with other electrons, so you have to calculate 0.35 for the other electrons, okay, and 0.30 for only 1s electron. In 1s it will be 0.30, other than 1s it will be 0.35 from the same group. So these ones are called actually groups. This one is one group, you have created this one is another group, this one is group. You have grouped the electrons for determining this shielding constant. If the electron which is to be considered is in ns or np, this group, so an amount of 0.85 from each electron with principal quantum number n-1, and an amount of 1 for each electron with the principal quantum number n-2 or lesser. Now next, if the considering electron is in D group or F group, an amount of 1 for each electron, those having smaller principal quantum number and same principal quantum number but smaller azimuthal quantum number or different group. Now we will try to understand it from the example, taking the example. So first, this is the summary, or this is the chart. Here are different groups, and here you can see for the other electrons in the same group, what will be the shielding constant value. From other electrons in the same principal quantum number but different azimuthal quantum number, from other electrons with n-1 quantum number, and from all other electrons up to n-2 quantum number. For 1s, we have maximum 2 electrons, so we have just 0.30 from the other electron in the same group. And for other ns and np, we can have total 8 electrons here. So for other electrons in the same group, you have 0.35, and for other electrons with n-1 quantum number, you have to add 0.85, and all other electrons up to n-2 quantum number, you will get 1, shielding constant as 1. Similarly for D, 0.35 from the other electrons in the same group, 1 from the electrons that are in the same n but other azimuthal quantum number, means in the S and P, and 1 from the other electrons whose quantum number is less than n. Similarly from the F group, if there are electrons in the same group, means more electrons in the F, that time you have to add 0.35 as a shielding constant. From other electrons in the same principal quantum number but different L, means in the D or SP group, you have to add 1. And similarly from the other electrons in the different quantum numbers, you have to add 1 for the shielding constant. Now we will take an example and we will determine the shielding constant for all the electrons of this iron. For this I will choose the pen. Yeah, see, so for iron, this is the electronic configuration, 1s2. So this is not the ideal configuration, this is actually how you write to determine this shielding constant. First you write 1s2, then in one group you add 2s2 2p6, another group you add 3s2 3p6, then you write 3d6 and 4s2. Now we will determine the shielding constant of these 4s electrons. So here we have 2 electrons. So for 1 electron, if we calculate, so there is only 1 more electron in this 4s group, right? So from that electron, we will get 0.35 shielding constant. That's why 0.35 into 1. Now from these 14 electrons, they have same n, same principal quantum number, but different azimuthal quantum number. So we will get 0.85 into 14. So this much will be the shielding constant value from these two groups, this one and this one. So this one electron, this coming from 4s, that is giving 0.35. These 14 electrons, those are coming from this 3s2, 3p6 and 3d6, that is giving 0.85 each. And we have 10 more electrons in this 1s2 2s2 2p6, we have 10 more electrons. These 10 electrons are contributing total 1 value. The total shielding is depicted as 1, and if it is less than 1, so that means it is not shielding totally. Okay, so if we calculate, so we will get S as 22.25. Now our atomic number is 26, so Z is 26, and if we do Z minus S, we will get Z effective to be 3.75. So 3.75 is the Z effective in this 4s electrons. Means originally in the iron, so if this is a nucleus, I'll just shade it. So in the nucleus we have 26 electrons, right? Now after that we have different 1s, 2s, 2p, 3s, 3p, 3d, 4s. So we have all these electrons. Now just assume if it is 4s electrons here, and we have all other electrons here before this 4s electrons. So these 4s electrons, each electron, they will think that there is only 3.75 number of protons. So actually we have 26 number of protons. So there are 26 number of protons, and the 26 protons are attracting these electrons, but the inner electrons, they have shielding effect. So they are shielding the attraction of these protons. So that's why this 4s electron, they will think, or they will get the force that only 3.75 protons are there in the nucleus of iron. So that much attraction these 4s electrons will feel. Now let's come to the 3d electrons, and if we determine the shielding constant of 3d electrons. So for 3d electrons, there will not be any contribution from 4s. Okay, so we have to consider the electrons which are before 3d or in 3d. So from 4s, there will be 0 shielding constant. Now in the 3d electrons, we have 3d6, 6 electrons are in total. So each electron can see 5 more electrons. So 5 more electrons, and they are giving shielding constant 0.35. So that's why we have to multiply 0.35 with a 5. So this, from this 3d6, we get 0.35 into 5. And all other electrons with the same principal quantum number and different azimuthal quantum number, this one, and here's different principal quantum number, they all electrons contribute shielding constant 1. So that's why all 18 electrons before this 3d, they will give shielding constant 1. So the total shielding constant comes out to be 19.75. And if we subtract this S from the Z value, we get 6.25. So the Z effective is 6.25. So the electron which is at 3d, if the electrons are 3d, so those electrons will feel, those are much closer to the nucleus, right? So they will feel more attraction to the nucleus. So they will feel that per electron, there are actually 6.25 protons. So this will be their conception. Means that will be the Z effective to these 3d electrons. Now if we calculate for the 3s2 and 3p6, these electrons, so total there are 8 electrons in 3s2 and 3p6, and this 3d and 4s will not contribute anything. So we'll have 0 and 0 for 4s and 3d. Now 8 electrons are there in the 3s2 3p6. So one electron can see 7 more electrons. So 7 electrons will impart 0.35 shielding constant. Then before that, we have 8 more electrons in the 2s2 and 2p6. Those 8 electrons will give 0.85 shielding constant. And we have 2 electrons in the 1s. So those 2 electrons will give shielding constant 1. The total, the S will come out to be 11.25. And if we do Z minus S, we get 14.75 as the Z effective. So the electrons which are in the 3s and 3p, see here the principal quantum number is same, but as the azimuthal quantum number is different, so they will have different effective nuclear different effective nuclear charge. So they will feel the Z effective to be 14.75, whereas in case of 3d electrons, they are feeling only 6.25. So the 3s and 3p electrons, they will have higher attraction towards the nucleus. Now if we calculate for 2s and 2p, so for 2s and 2p, all this right hand part will be 0. So we have 0 for 4s, 0 for 3d, and 0 for 3s, 3p. So in the 2s and 2p, we have 8 electrons in total. So each electron will see there are 7 other electrons. So 7 other electrons will impart 0.35 shielding constant, and the 2 electrons in 1s2, they will impart 0.85 as the shielding constant. So the total shielding constant is 4.15. So if we calculate Z minus S, we will get 21.85. So the effective nuclear charge is 21.85 for 2s and 2p. So these 2s and 2p electrons, they will feel that this atomic number, or this number of proton in the nucleus is actually 21.85. So that much attraction they will feel. And if you consider for 1s electron, all other contribution will be 0 from 2s, 3s, 3p, 3d, and 4s. And in 1s we have only 2 electrons. One electron can see there is one more electron. So that electron will shield only 0.3 or 0.30 just for 1s. So the effective nuclear charge will be 25.7. So the electron which is very close here, 1s electron, that will feel that in the nucleus there are 25.7 protons. So this is the concept of effective nuclear charge. So this tells that in an atom, differently positioned electrons, they will feel different effective nuclear charge. And depending upon their effective nuclear charge, they will feel more or less attraction towards the nucleus. Fine. So next we will move on to Goldsmith geochemical classification of elements based on chemical affinity. So Goldsmith said that elements can be classified into four groups. First one is the siderophiles, means iron loving. So these metal elements have affinity towards iron and present in Earth's core in free state. They have incompletely filled outermost shell. For example, iron, cobalt, nickel, ruthenium, rhodium, palladium, platinum, osmium, iridium, and gold. Next one is chalcophiles. I'm sorry, this will be two actually. Next one is chalcophiles, means sulfide loving. So these metals tend to bind with sulfide and their ions are soft acids. So the soft acid, this thing comes in the hard soft acid base principle, which I will teach you sometime later. So this means these ions are more polarizable in nature and their ions contain 18 electrons in the valence shell. For example, copper, zinc, cadmium, mercury, lead, arsenic, antimony. So just a small, I will just say quickly, just wait 1 second. Yeah, from the hard soft acid base, if I have to say very briefly, you have this atom and you have this atom. Oh, my circles are very bad actually. So if you have two atoms, now in this atom, these electrons are very tightly bound. This atom size is very small and the electrons have stronger affinity towards the nucleus. Whereas in this atom, if this is your nucleus, and these electrons are far from the nucleus, the electrons which are here. So what can happen if you give another atom A? Now these electrons or electron density can be polarized, can be changed like this, something like this. So this is just a crude way to say that as these atoms which are far away from the nucleus, they can be polarized or they can be drawn together, they can be deformed. But that thing will be very difficult in these smaller atoms. That's why these smaller atoms are called hard atoms, and these ones are soft atoms. These bigger atoms are the soft atoms. Now the next one is lithophiles, stone loving. So these metals tend to bind with the oxides. These are hard acids according to the hard soft acid base theory, and their ions contain 8 electrons in the valence shell. For example, alkali metals, alkaline earth metals, early members of transition elements. And next, and the fourth group is the atmophiles or vapor loving. So these elements remain as gas in the atmosphere. For example, nitrogen, oxygen, inert gases. So the thing is, the chemical affinity may depend on environment too. Chromium is lithophilic in crust, but in an oxygen deficient condition, it can exist as a chalcophile. So based upon your atmosphere or environment, your atoms can act differently. Iron is siderophilic in the core, but lithophilic in the crust. So different atoms can behave differently according to its environment. Now this is the periodic table which shows Goldsmith's classification based on the chemical affinity, and you can see these blue ones are the atmophile. You can see these inert gases, carbon, nitrogen. These green ones are the lithophile. You can see these alkaline earth metals, alkaline earth metals, some transition metals. These are the lithophiles. These ones are the chalcophiles. You can see here sulfur, selenium, tellurium, arsenic, antimony. These elements are considered as chalcophiles, and these red ones are called siderophile. So you can see iron, cobalt, nickel. So these are called as siderophiles. And some elements can be both siderophile and lithophile. So some element can be both, and depending upon the environment, their nature can also change. Next, we will discuss about the Goldsmith's cosmochemical classification of elements based on cosmic abundance. So cosmochemistry or chemical cosmology is the study of the chemical composition of matter in the universe and the processes that led to those compositions. So according to that, elements are classified into four groups: refractory, moderately volatile, high volatile, and siderophile. So you can see the color coding, and from the color coding, this right hand side you can see the color coding, and from the color coding you can see these red ones, these are highly volatile. These yellow ones are volatile, and these light yellow ones, these are moderately volatile. So for example, these inert gas elements, they are highly volatile. Now if you see chlorine, these are volatile, and if you see phosphorus, that is moderately volatile, manganese moderately volatile, copper, gold, these are moderately volatile. Now the green ones, these are moderately refractory, and the blue ones are refractory. So aluminum, silicon, ruthenium, iridium, these are refractory. And this violet one is highly refractory. Tungstenium, osmium, rhenium, zirconium, these are highly refractory. So this is the periodic table which classifies the elements based on their cosmic abundance. So if you want to know more, if you want to know in detail about these things, you can Google these things, or you can see some lectures which are focused on this cosmochemistry. So these many things we have covered in this video. Hey genius, welcome back to the 6th lecture of the series Periodic Table and Periodic Trends. In the previous lecture, we have learned about drawing of periodic table, trick to find out period and group of a given atomic number. We have also discussed the concept between isotope, isotone, and isobar. We have learned filling of electrons, orbit and orbital concept, now above principle of filling of electrons, and also I have shown you a trick how you can easily remember that. Apart from that, we have learned nomenclature of super heavy elements, trivial name of different elements, lanthanide and actinide construction, Slaughter's rule, determination of Sealing constant, and at the end, we have discussed briefly about Goldsmith's geochemical and cosmochemical classification of elements based on chemical affinity. So these many things were discussed in lecture 5. If you have not seen that lecture 5, I will strongly recommend you please go and watch that video. And after that, you can come back to this video. Now this lecture 6 is going to be a longer video because in this video, I am going to discuss in detail about all the periodic trends. So just let me take the laser pointer. So in this video, we will discuss about the periodic trends in atomic radius, atomic volume, ionization energy, electron affinity, electronegativity, metallic character, and cohesive energy. And after discussing these things, each and every periodic property, I will give you some notes or some tricks to remember these periodic properties. In the right hand side, you can see for each property, I have designed or I have designated an arrow. So these arrow tells that at which side this property is increasing. So this one is down left. This arrow is in the down left corner. So this trend, the atomic radius is increasing in the down left side. Whereas this one is curve shaped. You can see this atomic volume and cohesive energy. These two are in curve shaped. This means that along a period, it sometimes increases or decreases, and then again the opposite trend. For example, it decreases and then again increases. And for cohesive energy, along the period, it first increases, then decreases. And atomic radius and this metallic character, in these two cases, these two trends, you can see down left arrow. So it increases in the down left corner of the periodic table. Whereas ionization energy, electron affinity, and electronegativity, these three properties increase in the upright corner. So these three properties increase in the upright corner of the periodic table. So the elements which are in the upright side, those elements are having higher ionization energy, electron affinity, and electronegativity. So these things we are going to discuss in detail today. So without wasting any time, let's start the video. First thing we have to know that what is a periodic property. So any property which is periodic in nature, that means show an increasing or decreasing trend along a group or period, is called periodic property. Now, the reason of periodicity. So the periodicity is the result of similar outer electronic configuration or valence shell configuration in atoms. So we can see, if we see the periodic table, we can see the atoms which are in the same group, they have similar number of valence electrons, whereas the atoms which are in the same period, they have similar number of orbits or similar number of shells. So those things matters, and those generate these periodic properties. Now, use of periodic property. So we can predict the nature of chemical bonds formed by the elements and compare their reactivity. Molecular shapes and crystal structures can also be predicted from these periodic properties. So the first property that we are going to learn about is the periodic trend of atomic radius. So this we will call it as down left property or DL property. Now let's see the model of an atom. So the right hand side, you can see this is the basic structure of an atom. So in the central core, we have proton and neutrons. Together we call it nucleus. So in nucleus, we have positively charged proton and neutral neutrons. So these two subatomic particles, they lie in the central. So this nucleus is actually positively charged. And surrounding that, these electrons rotate in their shells or orbits. So these electrons are actually tiny particles or tiny subatomic particles. Those are negatively charged. So in a neutral atom, if we have 5 protons, we will exactly have 5 electrons. For example, if we have, for example, in sodium, we have 11 protons and we have 11 electrons. So in a neutral atom, you have same number of proton and same number of electrons. Now in the first shell, only 2 electrons can be there, and in the next 2 shells, there can be 8, at max 8 electrons. And the way of putting electrons, that first you have to fill the inner circles, only then you can fill the outer circles. So one by one you have to put in the inner circles. So first electron will come here, second electron will also come in the first orbit, next third electron will come to the second orbit, and you have to fill 8, total 8 electrons in the second orbit, then the next one electron will come in the third orbit. So these things I have discussed in detail in the previous lecture, lecture 5. So you can go and check that lecture. Now here, let's take an analogy. So here we have positively charged nucleus and negatively charged electrons are rotating surrounding this nucleus. So these two are oppositely charged. This one is positively charged and electrons are negatively charged. So there is an electrostatic attraction between these nucleus and electrons. So take it as that this core, this positively charged is actually an attractive girl. The more number of protons it has, the girl is more attractive. Okay, and take these electrons as that girl's lovers. You know, one beautiful girl has many lovers. Many boy wants to get that girl's number, right? So similarly, just consider this nucleus is an attractive girl, and these electrons all are her lover. Now this girl will obviously attract these boys, all these boys. The boys who are closer, these boys will get more attraction compared to the boys who are far apart, right? So because these boys are feeling some attraction, So they will try to come close. So these orbits, some special cases, these orbits, they get more compressed. For example, see, this will feel some attraction toward this side. Again, this electron, this lover will also feel attraction towards the nucleus, right? Now here all the electrons will have similar type of attraction. Whatever attraction this electron feel, the electrons which are at the same orbital, they will feel the same type of attraction. Now these things you can determine from the effective nuclear charge, which I have shown you to calculate in the previous video, how to calculate the screening constant, shielding effect or screening constant, and how to determine the Z effective. So based upon that, you can understand that how much attraction is there for each of these electrons. Now as these electrons are trying to come close to this attractive girl, so what happened, this orbit, this will shrink, and this will come like this will become a little smaller. And this shrinkage is much more prominent in case of F block elements. D block elements also shrink a little, but in case of F block elements, this shrinkage is more prominent because F electrons are diffuse in nature, so the F electrons cannot do the shielding, and the outermost electrons, they get more attraction towards this nucleus, and those electrons shrink, the shell shrink. Now as this radius shrinks, as this orbit shrinks, the radius, atomic radius also shrinks. Now how to determine the atomic radius? So atomic radius is the distance from the center of the nucleus to the outermost electron. So see, from here we have, this is the center, let's assume this is the center of the nucleus. So originally the atomic radius was from here to here, this distance, right? But as the electrons are feeling some attraction towards the center, so the orbit will shrink, the last orbit is shrinking. So now the actual atomic radius is actually this much. So the atomic radius has also shrunk. So if you increase the number of protons, the electrostatic attraction increases. So the outermost shells may contract, they may shrink, and the atomic radius can also decrease. So this is the way how the atomic radius decreases. Now if you add one more shell, if you add fourth shell, so the fourth shell will come this way. So if you add more and more shell, that time the atomic radius of the atom will increase compared to the atoms which have lesser number of shells. Okay, so these things we are going to observe in the later slides. Let's take a look at this image. So this periodic table shows what is the relative atomic size of the atoms in the periodic table. So you can see the left hand side we have alkali metals, those are bigger in size, and as we go in the right hand side we can see very small spheres or circles. So these are very small in size. Noble gases and halogens, those are very small in size. So what is the trend? We will see that how it is happening, what are the reasons behind it, why this size is shrinking from left to right. You can see from left to right the size is shrinking, and whenever we are going to discuss a periodic property, we will go from left to right along a period, or we will go from top to bottom along a group. Now you can see from top to bottom the size is increasing, and left to right the size is decreasing. So this is the 3D diagram which shows the atomic radius data of all the elements in a periodic table. Now let's see the trend. We will see it first for a long period. So what are the factors that are working along period? So if we go from left to right, what are the factors there? The principal quantum number is fixed. So along period, the principal quantum number is same for lithium, beryllium, boron, carbon, nitrogen. All are having the outermost electron shell as to be the second shell or second orbit. Okay. So all these atoms have two shells or two orbits. These atoms have three orbits. These atoms have four orbits. So all these atoms in the period, they have same principal quantum number. Next is the effective nuclear charge increases. So let's see this third period. Okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So as we are going from left to right, we can see more and more protons are there in the nucleus. In case of sodium, there are 11 protons. In case of magnesium, there are 12 protons in the nucleus. Whereas in case of aluminum, there are 13. In case of silicon, there are 14. So the last shell is same, but in the nucleus we have more and more protons. So what I said, the nucleus is an attractive girl, right? So if it has more and more proton, so it is more and more beautiful, more attractive. So it will attract the electrons more. So I will try to show it here again. So if this is your nucleus, if you have more and more protons, it will attract more to the outermost electrons. So it will similarly attract all the electrons, even the inner electrons, but the outermost electrons, that will also shrink. So these electrons will come close. These electrons will feel more and more attraction if the proton number increases. So this shell will actually shrink. So the outermost shell will shrink, and the radius, which tells the distance from the center of the nucleus to the outermost shell, so the radius of the atom will decrease. Okay, and another factor is that when we are going from left to right, so the number of protons is increasing. Similarly, the number of electrons are also increasing. So we have more and more electrons in the shells, right, in the last outermost shell. So that actually increases electron-electron repulsion, because electrons are negatively charged, and we know similar charged particles, they repel each other. So that is also a factor, but this factor is not dominant. The other factors are actually dominant. The increase of effective nuclear charge, that is the dominant factor. So as you go from left to right in a period, the effective nuclear charge increases. So although the electron-electron repulsion increases, but that is a minor factor. Because the effective nuclear charge increases, the electrons, the lovers, they feel more attraction to the attractive girl, and the shells come down. That shrinks, because of which we see the atomic radius decreases. So along period, the atomic radius decreases. Got it? Now next, see the periodic trend of atomic radius along group. So along group means we are going from top to bottom this way. So what are the factors there? So along group, principal quantum number increases, means the shell number increases. So in the first one, we have this nucleus and only one cell in this one, whereas in this one we have nucleus, one cell like this, and we have one more shell on top of this. So I'm just doing half circles because I'm not showing the entire circle. Just consider this as an entire circle. Okay, now in case of third period, we have 3 shells. Similarly, in case of fourth period, we have 4 shells, then here 5 shells, 6 shells. So as we go from top to down, the principal quantum number increases, means the number of shell increases. Now effective nuclear charge also increases a little bit, but that is a minor factor. So the red ones, I have written the minor factors in the red ones, so these don't contribute much. So even if we see that we have seen a long period that electron-electron repulsion was also a factor, but that was also minor factor, so that's why I wrote it in red. Here also effective nuclear charge increases, but this is a minor factor, so that's why we will ignore it. We will ignore the contribution of this. This I have written just to give you the complete information that what are the factors working. So the black ones are the dominant, and these red ones are minor factors, so we can ignore them. But to teach you for learning purpose, you have to learn everything. Now the other factor is the size increases because we have more and more shells, right? But the increasing rate of size for the heavier containers decreases. Yeah, so the size will continuously increase when we have more and more shell, but the rate of the increase will decrease. Maybe just see here, from 37 it became 152 in a pm, means picometer. Now after that, there is 186, 227. Now if you see from 227 to 248, the increase is very less, and again 248 to 265, the increase there is increase, but the rate of increase is much lesser. So if we subtract this, we can see there is almost 115 picometer change. Now in between lithium and sodium, if we see, that is 34, the change in picometer. I'm just telling you the change in the size. Now sodium to potassium, so that will be here 14, here 27, means 41. Now from potassium to rubidium, you can see the change is only of 21 picometer. Now from rubidium to cesium, the change is just 17 picometer. So you can see as we go in the heavier atoms, the rate of increase, it is increasing, the atomic radius is increasing, but the rate of increase decreases. The rate of change is significantly less in D block elements due to the less shielding of D and F electrons. Yeah, so another factor is when you consider the D block elements, as I told that in the previous lecture, that D electrons and F electrons, they are more diffuse in nature, they have lesser shielding property, so the nucleus attracts the electron much more. Now if you put more and more protons, more and more electrons, still the attraction remains almost same, and because of that, the rate of change in the side by side elements, that is small. That I'll show you. I'll show you the periodic table. I'll show you here. You see these D block elements. If you see these D block elements, see if you go from top to bottom, the change of the size is less, not very significant. Whereas if you go in the S block elements, you see a huge change, huge increase in the atomic radius. Whereas in case of D block elements, the change is slow. So along the group, the atomic radius increases. Okay, what is the major factor? Major factor is that the principal quantum number is increasing as we have more, as we are going from top to down, the more and more shells are adding. So that's why the atomic radius is increasing. Now this is the chart which tells you Z versus R, means atomic number versus that radius of atom or radius of orbital. Now you can see for the so these are the S block elements. For S block elements, the atomic radius is more for the alkali metals. And as we go along the period from lithium to beryllium, boron, carbon, nitrogen, oxygen, so the atomic radius decreases. So it decreases till neon. So neon, which is the inert gas element that is having lowest one here. And again, in the next electron, when we fill the next electron, that goes in the third shell, right? Third orbit. So that's why again the size increases. Here you can see sodium. So again, if you put more and more proton and electrons, the size decreases till the next inert gas element, argon. And again, if you put one more electron and proton, the size again increases in the potassium. So just see this graph and try to understand. So this is the values that I have found, the atomic radius values. If you need, you can take a note of this. Now the values which are given without bracket, so that tells the single bond covalent radius. Single bonded covalent radius. And within the bracket, so these values which are inside the bracket, so that gives atomic or metallic radius. So in the atomic state. So these values are in the atomic state. Whereas these values which are non-bond without any parenthesis, without any bracket, so that gives a covalent radius. And yeah, these values are given in picometer. So picometer is actually 10 to the power minus 12 meter. So 1 picometer is 10 to the power minus 12 meter. So our hair is in the order of micrometer, 10 to the power minus 6 meter. Now, if you divide this 10 to the power 6 times, that will be a picometer. Then you can understand how much tiny that value is, how much smaller the value of an atom or radius of an atom is. Now we will discuss about some concepts regarding atomic radius and ionic radius. So cations having lesser number of electrons experiences higher electrostatic attraction, giving lesser radius compared to its elemental form. So let's see, we have these elements here in the elemental form: lithium, sodium, potassium, beryllium, magnesium, calcium, and in this side we have fluorine, chlorine, bromine, iodine. Now these atoms, here we have similar number of protons and same number of electrons. So number of proton and electrons are same. But when we take out an electron, in that case number of proton is more and number of electron is less. That time we get cations. These are the cations. And when we put an extra electron in this elemental form, so that time we have lesser number of protons and we have more number of electrons. So that time we get anions. So these right hand side ones are the anions. Now that is saying that cations having lesser number of electrons because we have already removed one or more electron, right? So in this case we have removed one electrons from lithium, sodium and potassium. So it has now less number of electron, one less electron. In sodium we had 11 protons and 11 neutrons, sorry, 11 protons and 11 electrons. Now we have removed one, so now we have 11 protons and 10 electrons. So we have less number of electrons, and that experiences higher electrostatic attraction because now we are removing one electron. So one lover is removed. So now the nucleus or the attractive girl that can give more love to each electrons, right? So that can give more time or more attraction. So that's why the electrons feel more attraction now. Just I will try to clear this concept here. See, this is my nucleus, and these are the shells. Let's see in case of sodium. In case of sodium, we have 2 electrons here in the first shell. Then we have 8 electrons in the next shell, and we have 1 electron in the last shell. So this one is in the last shell, right? Now what happens when we remove this electron? If we just remove this electron, we take it out. So sodium becomes sodium plus, and in that case, this orbit is completely empty. This third orbit, it had only 1 electron. Right now it is 0. So you can see only these 2 orbits are there now in Na plus, sodium plus. So obviously the number of orbit is less. And even if you take magnesium, so in magnesium there were 2 electrons. And if you remove 1 electron, that time we will have a total 12 proton, 12 number of proton, and 11 electrons in case of magnesium plus. But when we do magnesium 2 plus, that time we are removing both the electrons. This is also we are removing. So whenever we are removing both the electrons in case of magnesium, again this third shell is becoming vacant, 0. So that time we have 12 protons and 10 electrons. So we can see the number of proton is more, number of electron is less. So the attraction towards the nucleus for each electron will increase, and that decreases the size. So that's why cations are always in smaller size compared to their elements. You can see in case of lithium, the size is more compared to lithium plus. The sodium size is more compared to the sodium plus. Potassium size is more compared to potassium plus. And these are in given 10 to the minus 10 meter. Okay. So if you want to convert it into picometer, just multiply by 100. So this is 203 picometer, and this is now 138 picometer. Similarly, in case of beryllium, we had 96 picometer size, but beryllium 2 plus is only 45 picometer. Magnesium 1.45 picometer and Mg2 plus is only 0.72 picometer. But in case of anions, let's see the case of anions. Anions having higher number of electrons experiences higher electrostatic repulsion. See, in case of anions, in case of fluorine, if you take fluorine, so we had this, I will draw here. This is the nucleus, this is the first shell, and this is the second shell. So in the first shell we had 2 electrons, and in the second shell we had 7 electrons in case of fluorine. But when we are putting 1 electron, so we are putting one more electron here to here in the orbit. So we are doing 7 plus 1. So 1 electron is increasing. Now we have 2 electrons in the first orbit and 8 electrons in the next orbit. So in case of fluorine minus, we have total 9 protons but 10 electrons. So we are putting 1 extra electron. That electron, so we already had several electrons. We already had 7 electrons, and then we are putting 1 more electron. So what will happen if we increase more number of students? There will be more chaos, right? More fight, more quarrel. So when we are adding 1 more electron, that time the electron-electron repulsion increases. And because of that electron-electron repulsion, these electrons will try to go away from each other. This will try to go this side, this will try to go this side. So that will actually expand this orbit size. So because of this, the size of fluorine is smaller, but the size of fluoride ion is actually much bigger because these electrons are trying to go away from each other. So as we are putting extra electron, the electron-electron repulsion is increasing. Those electrons are trying to go away from each other, and because of that, the shell is expanding, and we are getting higher value of radius, ionic radius or anionic radius, compared to the elemental form. You can see even in case of bromine, in the elemental form it was 120 picometer, but in the bromide form it is 196 picometer. And you can see the expand of iodine as well from 139 picometer to 220 picometer. So we have understood that in case of cations, because we are removing electrons, so either the shell number of shell is decreasing or the electrostatic interaction is increasing. So both factors are reducing the size of the cations. It may happen that the shell is decreasing. Means earlier it was 3 shells. Now in case of sodium plus, there are only 2 shells. Similarly, in case of magnesium, it had 3 shells, but in case of Mg2 plus, there are only 2 shells. Or even the shell number is same, but still, if you remove electron, that will increase the electrostatic interaction. So because of that, the size of the cation is always smaller than the elemental form. And as we are putting extra electron, so that will increase the electron-electron repulsion. So because of that, the orbital or orbit will try to expand, and for that reason, the size of anions are every time bigger than the elemental size or elemental radius, right? Next point is similar charge species along a group follows the same periodic trend as of the corresponding atoms. So the ionic radius trend follows exactly the same as the atomic radius trend. For example, we see in case of lithium, sodium, and potassium, if we go from top to bottom, we can see the size is increasing, the atomic radius is increasing. Similarly, if we consider lithium plus, sodium plus, and potassium plus, we can see here also the size is gradually increasing from lithium to potassium. And that is the thing, this ionic species, if it has same number of charge, that will every time follow the same periodic trend as of the elemental forms. So even if you take electron or give electron, if you convert in the ions, and if you convert in the same nature of ion, if it is 1 plus, you have to compare it with 1 plus charge. If it is 2 plus, you have to compare this with the 2 plus charge. So if you do so, you will have the same periodic trend as of the atomic radius trend. But yes, you cannot compare the lithium plus to fluorine minus, F minus, right? These are not same charges. You can see here it is plus 1, here it is plus 1, and here it is minus 1. So you cannot compare those to take the periodic trend, or you cannot compare this plus 1 to plus 2. So these are not similar charge. If you have similar charge species, only then this rule will apply, and the ionic radius trend will exactly follow the atomic radius trend, right? So what we have learned in this segment. So from this segment, we have seen that the trend of atomic radius is actually a DL property, down left property. So it increases in the down and left side. And the size or radius of an atom decreases from the left to right of a period. We have also learned that size or radius of an atom increases from top to down of a group. So what we have observed, that from here to here, from left to right, it decreases, right? So we can see from right to left, it actually increases. And we have also seen that from top to bottom, it increases. So from top to bottom, it is increasing, and from right to left, it is increasing. So that's why we can see that this is the arrow which tells in which side the atomic radius is increasing. So that's why if you go back to my first slide, you can see that I have given a small arrow on the side, on the right hand side of periodic trend of atomic radius. Next point is that alkali metal ions are having highest atomic or ionic radius, and inert gases are having lowest atomic radius in a same period. The variation in ionic radius for a particular oxidation state follows the same trend as of the atomic trend. And additional information is that radial distribution function of the electrons in the outermost shell is required to calculate the atomic radius. So we calculate this atomic radius from the RDF function. So it is theoretically calculated in a free atomic state as the distance from the nucleus to the point at which the radial distribution probability of the outermost orbital electrons is maximum. So theoretically we calculate in a free atomic state this atomic radius, which is from the center of the nucleus to the outermost electron orbital, or where this radial distribution probability function is maximum. Next, we are going to discuss about the periodic trend of atomic volume. So this we will remember as a curvy property. Now, why curvy? That I will discuss. So let's see the 3D diagram. You can see the atomic volume is higher in this side, and as we going from left to right, it is actually flat or zero. And again, if we go more right, it is again increasing. It is again increasing. So the atomic volume, first it is decreasing, then it is almost similar in this range, and then again it is increasing. Now let's see the definition of atomic volume. So the volume occupied by 1 gram of atom of the element in solid state is called the atomic volume. So Lothar Meyer is remembered for atomic volume curve. He made a graph taking 28 elements. That time very less number of elements were known. Later which was modified and all other elements are also plotted. So the definition of atomic volume is simply the definition of volume, right? Atomic volume is atomic weight divided by its density. Now this atomic volume depends on multiple factors. For example, packing efficiency and crystal structure, allotropic forms, temperature. So all these things actually can influence the atomic volume. Now let's see the atomic volume along period. So first we will see it for S and P block elements. This is just for S and P block elements we are observing now. So what happens? Along period, if we go from left to right, the principal quantum number is fixed because in the same period we have same number of cells in all the elements, right? So the principal quantum number is fixed even if we go from left to right. Now at beginning, increased effective nuclear charge predominates. So what was happening in the beginning when we go from, let's take this, from lithium to beryllium to boron. So when we go from left to right, the effective nuclear charge is also increasing because we are putting more number of protons, right? So at the first, the effective nuclear charge predominates. So the electropositive elements of the period lies in the descending limb, it's lower atomic value. So that's why when we are increasing the number of protons from lithium to beryllium to boron, then we can see the effective nuclear charge is more. Because of that, the nucleus is attracting the electrons. I'll draw it again. So as we're putting more and more protons, the girl is becoming more and more attractive. So these lovers, they will try to come close, right? These faraway lovers or the electrons, they will try to come close and the orbit will shrink. So that's why the volume or space which it is occupying, that is also decreasing. And in case of electropositive elements, so as more and more proton we are putting, the volume is decreasing, again decreasing, again decreasing, again decreasing. Okay. That's why the electropositive elements lie in the descending limb. So these limbs in this graph, these limbs are called the descending limbs. You can see here. These are the descending limbs. So the electropositive elements lies in the descending limbs. Now while filling more electrons, now electron-electron repulsion increases. So now if you put more and more electrons, first it was happening that the effective nuclear charge was increasing and the size was shrinking, right? But now if you put more and more electrons, at a time what happens? Now these electrons start to fight. Okay. Now they start to repel each other because they are same charge, negatively charged particle. So they will start fighting and they will try to go away from each other. So now this component is less and this component is more. This electron will try to go away from each other. So because of that, the orbital size will increase. Or you can say this electron-electron repulsion will increase. So the electronegative elements lies in the ascending segment of the curve. So you can see these electronegative segment elements, they are lying in the ascending curves. Here. Now first the effective nuclear charge was dominating, and next is that electron-electron repulsion will dominate. So although size will not increase as much, but actually the atomic volume will start increasing. So this is true for S and P block element. Now next see what happens in case of D block elements. So we are now observing a long period for D block elements. So for D block elements, at first atomic volume decreases due to increasing effective nuclear charge. So the same thing as we increasing the number of protons and electrons from scandium, titanium to vanadium and chromium, we can see the number of protons is increasing, so the electrostatic attraction is increasing, and that's why the size is shrinking and the atomic volume decreases. So then electron-electron repulsion balances the effect of increasing effective nuclear charge. So more or less atomic volume remains constant. So now if you put more and more protons and electrons, if you go from iron to cobalt, nickel, so that time the electrostatic attraction is also increasing. At the same time, electron-electron repulsion is also increasing. So both the factors are actually balancing each other. Means if you see it again. So because of the electrostatic attraction, if it wants to come this side, so because of the electron-electron repulsion, it wants to go in the outer side. And those two magnitudes are almost same. So they actually cancels each other. The effect cancels each other. And at the last, electron-electron repulsion predominates and atomic volume increases for copper and zinc. Sorry, this will be zinc. So at the end of the d block elements, you put more and more electrons and protons. So that time this electron-electron repulsion predominates and the atomic volume increases. So this is the crude way to remember these things. But the main definition is that atomic volume is actually atomic weight divided by density. This thing. So both the factors actually contribute. Now let's see along the group. So what are the factors that are working along the group? Along the group, atomic weight increases. Yeah, so we are putting more and more protons and neutrons in the nucleus, so the atomic weight increases. Now atomic density also increases, which works in the opposite direction. Yeah, so these red ones, I have written the red ones, which are working in the opposite direction, or which are the minor factors, which this is not dominant. The black ones are the dominant factors, okay? Now we have seen that atomic volume is equals to atomic weight divided by density. Now atomic weight is increasing as well as density is also increasing, but the increase of atomic weight is the dominant, that is more. So hence the atomic volume increases along group. So if we see along group, we can see the atomic volume will increase because of the increase in atomic weight. Okay. Now we can see from here also. See this lithium. Then in the group we will have sodium, we will have potassium and rubidium. So these are in a group. And we can see the atomic volume amount is actually increasing. This is a Z versus atomic volume curve. So you can see if we increase the atomic number of protons, how this behaves. So I'll take this one. Yeah. Just take this potassium, calcium. So when we increase the number of protons, the electrostatic interaction is increasing. So the atomic volume is going down. Same thing is in the d block elements also, scandium, titanium, vanadium. When we increase more and more proton, the electrostatic interaction increases and the atomic volume decreases. Now after that, in case of this iron, cobalt, nickel, we can see this zone. So this zone, in this case, we are putting more and more electrons and protons. So as we are increasing the protons, the atomic attraction or electrostatic attraction is increasing. But at the same time, as we are putting electrons also, the electrostatic repulsion also increases between the electrons of the same shell. So both the factors balances out each other. And that's why we have almost same kind of atomic volume. Now when we put more and more protons and electrons, so that time the electron-electron repulsion, that increases. And because of that, we get increase in the atomic volume. Same thing happened in the p block elements also. As we put more and more electrons, the atomic volume will increase because of the electron-electron repulsion. Fine. So till now, what we have seen? We have seen that atomic volume is actually a curvy property. So it first decreases and then increases. So along the period, atomic volume first decreases due to the increasing effect. Just let me take this laser pointer. Yeah. So along the period, atomic volume first decreases due to the increasing effective nuclear charge. Then the electron-electron repulsion starts to increase and atomic volume also increases. Along a group, atomic volume increases due to the increase in atomic weight. Alkali metal ions having highest atomic volume occupies the peaks of the graph. So if you see this graph, so the peaks are occupied by the alkali metal ions here. All these are alkali metal ions which are occupying the peaks. With the increase of atomic number, the electropositive elements lie on the descending limb, whereas the electronegative elements lie on the ascending limbs. For the transition metals, the atomic volume remains almost same along the period, and they occupy the flat region at the bottom. Whereas in the case of lanthanides and actinides, they occupy the descending limbs near the bottom because of the lanthanide and actinide contraction. So this lanthanide and actinide contraction I have explained in the previous lecture. So these are some keynotes that you need to remember for the case of atomic volume or the periodic trend of atomic volume. Now let's discuss about the periodic trend of ionization energy. So this is a upright property. So I call it upright property. I will explain why it is called upright property. Just let me take the pen. Yeah, so first thing we have to understand that what is the concept of ionization energy. Now let's try to see this thing. You see, this is a kid who is holding a lot of balloons. Now what you can do, you can cut a wire, a rope, right? If you cut a rope, what will happen? One of the balloon will fly, right? Similarly, you can cut another rope, and similarly another balloon will fly, and those balloons will go out of his hand, out of his control. Okay. So what kind of energy you are providing? You are cutting the rope, and that's why these balloons can get free. Those are getting free and out of this boy's control. So similar concept you have to visualize in case of atom. In case of atom, you see they have electrons in the shells. What you can do, you can knock out this electron. You can provide some energy so that this electron will go away, and that will go out of control of this atom. So as this electron is going away, so this electron is minus charged, negatively charged, so this atom will become positively charged. So let's see the definition now. So the amount of energy required to knock out the loosely bound electron in the outermost shell in an isolated atom in the gaseous phase to generate a charged cation is referred as the ionization energy of the element. I know this looks a big definition, but let's try to understand it by small portions. So the amount of energy required, so the amount of energy that we are supplying to cut these balloons, okay? So that's what, that amount of energy, that is referring to the ionization energy. To knock out the loosely bound electron. So we can knock out the outermost electrons, or the electrons which are not tightly bound, which are loosely bound, so that we can easily knock them out, right? We can provide some energy and it will go out. In the outermost shell, as I already mentioned, that we will knock out the electrons from the outermost shell in an isolated atom. So this one is very important. In case of the definition of ionization energy, it has to consider the isolated atom. So this atom cannot be with the other atoms, or it cannot be bonded with another atom. It cannot be bonded with B, or it cannot stay with the other A type of atoms. If it stays with other atoms, so there will be some interaction. So that interaction energy also you have to keep it in mind. You have to calculate. So you have to calculate more things if it is in surroundings of other atoms. So what you have to do, first you have to provide some energy, and you have to take out this atom in seclusion. This has to be an isolated atom. No one should be in its surroundings. Only then this ionization energy definition you can apply. And in the gaseous phase, so you have to take this ion or atom to the gaseous phase to generate a charged cation. So as you are taking electrons from here, you can see if you are taking electron from here, so you will generate a cation, and that is referred as the ionization energy of element. So the energy you are providing, so the energy you are providing to take electrons from the outermost shell of an isolated atom, that much energy is called ionization energy. Now we will see these definitions or some examples. In case of this, see aluminium. So aluminium has 13 electrons. Now what will be the arrangement? I'll do it here. Just assume this one is the nucleus of aluminium. Then we have 2 electrons in the first shell, 8 electrons in the second shell, and 3 electrons in the third shell. So 2, 8, and 3. So in our outermost shell, we have 3 electrons. And all these 3 electrons we can take one by one. So what are we doing? First, we are taking 1 electron, and the ionization energy is this, 578 kJ per mole. Now, when we are taking 1 electron, so we are doing 3 minus 1. So in the last shell, now we have 2 electrons. So if there are less number of electrons and more number of protons, we know in case of cations, the electrostatic interaction will be more, and those outermost electrons will be now tightly bound. They will feel more attraction towards the attractive girl or the nucleus, right? So now when we are trying to take out another electron from this aluminum plus, from this, if we want to take out another electron, so we have to supply more energy. That's why this IE2 is actually greater than this IE1, ionization energy 1. Now we have taken out another electron, supplying more energy. So now we have, now we have only 1 electrons in the third shell or outermost shell. So in total now we have 13 protons and only 11 electrons. So now we have lesser number of electrons and much more lesser. So the attraction energy of the nucleus will be more and more. So when we try to take out another electron from aluminum 2 plus to generate aluminum 3 plus, we actually have to provide much more energy. And you can see this much energy we have to provide, 2744.8 kJ per mole, which is actually more than the summation of its IE1 and IE2. Even if you sum these two, this number is much greater. So you can take out electrons from an atom one by one, but as the number of electrons are decreasing and the number of protons are increasing in the ion, so they will experience more and more attraction. So you have to provide more and more energy to take out the outermost electrons. Okay, clear? Now let's see the periodic trend. So you can see I have already mentioned it. This is an upright property. So if you see the periodic table, the ionization energy increases from left to right in a period, and if you go from top to bottom, the ionization energy actually decreases. So we can say that ionization energy increases from bottom to top. So if you go from bottom to top, the ionization energy increases. So actually we can say that this is increasing in this upright corner of this periodic table, right? So that's why I tell it as UR property or upright property. Now let's see this 3D periodic table of ionization energy for your easier visualization. Now you can see from left to right, the ionization energy is increasing. And if you consider this part only p block element, let's see from left to right, the ionization energy is increasing. And from top to bottom, the ionization energy is decreasing. So actually from bottom to top, the ionization energy is increasing. So this corner is having the most ionization energy. So this graph is based on the first ionization energy, okay? Now let's see the detail of the periodic trend. First, we will see along period. What are the factors that are working along period? So along period, principal quantum number is fixed. So the number of shell is fixed. So if you go from boron to carbon to nitrogen, oxygen, the principal quantum number or the number of shell is fixed, or the number of orbit is fixed. Effective nuclear charge increases. We have already seen as we go from left to right, we are putting more and more protons in the nucleus. So the girl is more and more attractive. So that's why the girl attracts the lovers or the electrons more, right? So the effective nuclear charge increases from left to right along period. The size gradually decreases. The atomic size also is decreasing from left to right because of the increase in the effective nuclear charge, right? So all these factors actually increase the ionization energy from left to right. Now another factor, this electron-electron repulsion, that also increases from the left to right, but actually this is negligible factor in case of ionization energy. So that's why I'm writing it in red. Okay, so this factor is very minor, and you have to neglect this factor. So thus the electrostatic attraction towards the nucleus increases along the period, and ionization energy goes up. Just simply try to understand, if we have a smaller atom where the electrostatic interaction is more, and if we have a bigger atom, in case of bigger atoms, the shells, just consider that we have a bigger atom and these valence electrons are also far apart. So these valence electrons are far apart, it will not have much control. The nucleus will not have much control on the electron, right? So you can easily take out this outermost electron. But as the size is small and effective nuclear charge is more in this atom, so if you try to take out this electron, you have to put more and more energy, right? That's why as you go from left to right along the period, the effective nuclear charge increases, size decreases. So all these factors make this electron tightly bound or tightly attracted towards nucleus. So that's why it takes higher energy to take it out in the gaseous phase. Okay, so it takes higher energy. So that's why the ionization energy is more. Yeah, so there are some exceptional cases. For example, I can show you here. Just give. So you see, just see this: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So if you see this one, so we are expecting the ionization energy will increase along the period, right? That is happening from lithium to beryllium. But for some reason, from beryllium to boron, it is actually decreasing. And again, boron, carbon, nitrogen, these are increasing. So the trend is fine here. But again, here from nitrogen to oxygen, the ionization energy is decreasing. So there are some exceptions, and we are going to talk about that. So according to general periodic trend, oxygen should have higher ionization energy compared to nitrogen. Yeah, because nitrogen is having atomic number 7, oxygen is having atomic number 8, right? So oxygen comes right to the nitrogen. So according to the periodic trend, oxygen should have higher ionization energy. But it is having lower. Why? Due to the half-filled electronic configuration, nitrogen has higher ionization energy. So I will explain it later in detail, but just in a brief, I will say this electronic configuration. See this electronic configuration. This electronic configuration I have already taught in the previous lecture. If you have not seen, you can go and check the lecture 5. You can see it is 2p3 and this one is 2p4. Now if I draw this 2p, for nitrogen we have 2p3. So one electron here, one electron here, and one electron here. Now same thing for oxygen. So one electron here, second electron here, third electron here, and fourth electron. Note down, I have drawn 3 electrons, all 3 are in up spin. Now when I put the fourth electron, that will share with this electron, and now this cannot be the up spin. So this electron will be down spin. Due to Pauli's rule, the electrons in the same shell cannot be of the same spin. Okay, so as I'm putting the fourth electron, I'll put it as a down spin. Now in this case, in case of nitrogen, we have 2p3 configuration. So this is half filled. This is called half filled because we can at max put 2 electrons, 2 electrons, and 2 electrons. We can put maximum 6 electrons in this 2p orbital, but we have put only 3 electrons. So this is half filled. Whereas in case of oxygen, it is 2p4. So here 2 electrons, here 1, and here 1. So total 4 electrons. So this half filled and full filled shells, they have surprisingly high stability because they are having higher exchange energy. I will explain this exchange energy in after some slides in this lecture. So because of this half filled configuration, it is having more exchange energy. So the exchange energy means this electron can go here, this electron can come here, or this electron can go here, this electron can come here. So all this kind of possible exchange can happen. So that's why this nitrogen is having higher exchange energy, and it is more stable. Because of that fact, if we try to remove one electron from this nitrogen, so this ionization energy will be much high compared to the oxygen's ionization energy. So from oxygen, if you want to simply remove one electron, we can simply remove this electron. But from nitrogen, if you want to remove electron, so that time the ionization energy will, the exchange energy will decrease. So these electrons can exchange their positions, and that's why they have better stability. But if you remove one electron, so that time their exchange energy will decrease. So that's why this nitrogen will not let it go. It will not let the electron go. Okay, because of that reason, the ionization energy of nitrogen first ionization energy of nitrogen is more compared to the first ionization energy of the oxygen. Okay, but now consider the second ionization energy. So we have already removed one electron. So I'll just erase this. Wait. So we have removed one electron. Just assume we have removed this electron from the nitrogen and we have removed this downspin electron from the oxygen. So in this case, now we see there are only 2 electrons and the exchange energy is also very less for nitrogen because it is not half filled. But now this O positive, that is actually half filled. There are only 3 electrons and in this half filled configuration, they have higher exchange energy. So if you consider the second ionization energy, if you want to try to, if you try to remove one more electron, so that time we have to spend lesser energy in case of N plus, but we have to spend much more energy in case of O plus because O plus got stable state, this stable half filled state. Now you are trying to disturb it. You are trying to take one electron again. That time this O plus will not let it go. It will not let the electron go. So that's why you have to put more and more energy. Okay, got it? Let's see some more cases. For example, if you see phosphorus and sulfur, so similar to the nitrogen and oxygen case, phosphorus is having 3p3 and sulfur is having 3p4. So that's why if you consider the first ionization energy, the phosphorus will have higher first ionization energy compared to the sulfur, right? But now it is becoming phosphorus positive and sulfur positive. Now it has 3p2, only 2p electrons, and sulfur positive is having 3p electrons. So now this S plus sulfur positive is now half filled. So it is much stable. So now if we try to remove one more electron from phosphorus positive and the sulfur positive, so that time we are removing electron from this 3p2 and 3p3. So this time this second ionization energy will be lesser in case of P plus, whereas it will be higher in case of sulfur positive. But this is not universal, okay? So this works in this concept of exchange energy and gaining stability through this exchange energy, that works well in case of lighter elements. So this exchange energy concept does not have effect in the heavier elements and they follow normal periodic trend. So if you go along the period from left to right, it will increase. The ionization energy will increase. That thing happens in case of this antimony, tellurium, bismuth, and polonium. If you see, this is having 5p3, 5p4, and bismuth and polonium, they are having 6p3 and 6p4. So from the half-filled nature, we expect this antimony will have higher ionization energy, first ionization energy, but that is not true. You can see antimony is having lower first ionization energy. Sorry for that. So antimony will have a lower first ionization energy compared to the tellurium. You see, it is having higher first ionization energy. Similarly, from the exchange rule or from the half-filled concept, we might expect that bismuth will having higher ionization energy compared to this polonium, but that is not true. So if we see, this will be actually first ionization energy, sorry. If we see the first ionization energy of this bismuth and polonium, we can see bismuth is having lower ionization energy, whereas polonium is having higher ionization energy. Now let's try to remember this trend. How we can remember this ionization energy trend. So if you take these 3 periods, period 2, 3, and 4, and you will see, so these are the lighter elements or the lighter atoms. So they actually, in these lighter atoms, the concept of half filled and exchange energy, that actually works well. That already we have seen in case of nitrogen and oxygen, right? For that, the ionization energy trend is like this. So it first increase, then it will decrease, then again it will increase, then again it will decrease, and again it will increase. So this is how I remember it based on 2-3-3 formula. So first I will increase till 2 elements, means lithium and beryllium. Then I will decrease 1, I'll come to boron, and then I will take 3 more elements, means boron, carbon, and nitrogen. That will increase. Then again I will come down in case of oxygen. I will come down, and then again I will increase 3, oxygen, fluorine, and neon. Similarly, in case of period 3, I'm sorry, I'm using a very primitive setup. Yeah. So again, in case of sodium and magnesium, so these two will increase. Then again, in case of aluminum, it will decrease. And then again, aluminum, silicon, phosphorus, it will increase. Again, from phosphorus to sulfur, it will decrease. And again, sulfur, chlorine, and argon, it will increase. So I remember this trend of these 3 periods as a 2-3-3 formula. And these ones, these elements, for example, beryllium and nitrogen, or magnesium and phosphorus, these peak elements, they are actually full-filled and half-filled. So that's why they are having higher stability, higher exchange energy. If you see the electronic configuration of beryllium, it is 2:2, that is full-filled. In case of nitrogen, it is 2p3, that is half-filled. So these full-filled and half-filled configuration, they have higher exchange energy, and that's why they are having higher ionization energy compared to their nearby atom, right-sided atom. But as I said, that this concept of exchange energy and half-filled concept, that works well in the lower atomic number elements, but in case of these higher atomic number elements, that do not work. And for the next period, this will be period 5. For the period 5, you can see it will just monotonously increase. The ionization energy will increase. Similarly, in case of period 6, it will increase and then it will decrease for 1 and then again it will increase. And this element is actually lead. So cesium, barium, thorium and lead, that will increase, and then in bismuth it will decrease and then again it will increase. So when I used to prepare for competitive exams, I used to remember these trends. First 3 periods will be 2-3-3 formula, next period will be monotonously increase, and the last next period will increase till lead, then decrease and then again increase. So as I have already mentioned, this half filled and full filled concept, you can see in case of boron it is 2p1, and p orbital can take at most 6 electrons. Now we have only 1. In case of carbon we have 2 electrons, and in case of nitrogen we have 3 electrons. So 3 is actually half filled. At most we can have 6 electrons, we have 3 electrons. So that is a half filled configuration that is having higher exchange energy, so that's why it is more stable. So this half filled and full filled concept we will learn in the later slides. Yeah, so this is the filling of electrons that I have already discussed in the previous lecture. So you can see you have learned this electronic configuration. So first electron goes in 1s, and that is 1s1 in case of hydrogen. Then the next electron, that also goes in 1s, and in case of helium we have 2 electrons, and those spins are opposite in nature. One is up spin, another one is down spin. Now the next electron goes in 2s and we get lithium. The next electron goes in again 2s and we get 1s2, 2s2, that gives beryllium. So here 1s2, 2 electrons are oppositely spinned. Here also both the electrons have opposite spin. Now the next electron goes in 2p, and if you put one more electron, that will go here, another 2p, and if you put one more electron, that will also go in another 2p. And after that, if you put one more electron, that means 2p4 in case of oxygen, that electron will go here and that will have down spin. In case of fluorine, we will have one more electron, and in case of neon we will have full filled configuration. So this is the electronic configuration, you can see. And if you put one more electrons after this 2p, that will go in 3s. The next electron will also go in 3s, it will paired up, and if you put one more electron, that will go in 3p in case of aluminum, and then we put one more electron in silicon, phosphorus, this 3p3, this will be again half filled configuration. Now we put more and more electrons, and in case of argon we get again full filled configuration. So this is how you can put electrons and you can determine the electronic configurations. So now we are going to understand the concept of exchange energy. So in case of lithium, we have 1s2 and 2s1, only one electron. In case of beryllium, we have 1s2, 2s2. Now this beryllium in 2s, now it has 2 electrons. So this is actually full filled. Now these electrons, or these full filled electrons, are actually called, they are having higher stability. Now I will explain it in case of nitrogen and oxygen. Let's see again. In case of boron, we have 1s2, 2s2 and 2p1. In case of carbon, we have 1s2, 2s2 and 2p2. So the next electron will go here. Now we will do the nitrogen. We have 1s2, 2s2 and 2p3. In case of nitrogen, we have 1s2, 2s2, 2p3. Now this 2p3, so all the px, py and pz orbitals, they are having 1 electrons. This is actually half filled configuration. So these electrons, which are half filled, can now actually change their position. What I will do, I'll just draw it like this. So this is the crude idea which I'm telling you to understand this exchange energy. Now in the 2p we have 3 electrons, right? So let's write it as 1, 2 and 3. Let's consider it as 1. This one is as 2, electron 2 and electron 3. So this can be in this order, or this can be like this, 2, 3, 1, or this 2 and 3 can exchange their positions, right? So it can be 3, 2, 1. So all these possibilities can happen. So these electrons can change their place. The thing is, these electrons are occupying the shells, that's why they can change their place. If it is a vacant shell, you should not calculate it. I mean, you should not consider it that this electron will go here in this position. Okay, so if in this case, in case of carbon, these 2 electrons can change their positions. Similarly, in case of nitrogen, all the 3 electrons can change their position. Now this gives higher exchange energy. That is called exchange energy. That electron can go from here to here, and this electron can go from here to here. So this is more in case of half filled configuration. But when we have 2p4, p1, p2 P3, and P4. Now you might say that still these three electrons can change their position, but actually not, because these are paired electrons. These electrons have their interactions. And though these two electrons can change their position, but the exchange energy actually decreases from the compared to the nitrogen. Now that exchange energy will increase again in case of neon. If you see the electronic configuration of neon, so that will be actually 2p1, 2p2, 2p3, then 2p4, 2p5, and 2p6. Now these three electrons which are having half spin, they can change their position, they can have exchange energy, and these three electrons which have down spin, they can change their position and they can have exchange energy. So this configuration, full field configuration, is actually having 2 times of exchange energy compared to this nitrogen, right? So this is having 2 times of exchange energy. But there is another thing that we have to consider is the pairing energy. So as the electrons are paired here, so we have to subtract some term which is called pairing energy. For example, if we write exchange energy like E, so for 3 electrons we have E3 exchange energy, okay? Now here it will be E3, this 3 electrons generates E3, the upspin 3 electrons, and another E3 for the downspin 3 electrons. So let's try to understand again. Here we have 3 upspin electrons that can change their position, and that will gain this E3 term, E3 energy, stability. And these electrons, these 3 electrons which are having lower spin, they can also exchange their positions, and that will have another E3 exchange energy. Apart from this, we have some pairing energy also, that actually we have to subtract, because there are 3 pairs. When we are trying to exchange these electrons, we are breaking that pair. So if we take out these electrons, I will take the laser pointer for this. Yeah, see. So this is a pair, right? And this is another pair. This one is another pair. So these electrons are close to each other. They have some kind of interaction. They have some kind of energy going on, energy exchange going on in between them. So when I'm trying to do exchange of this downspin electron with this downspin electron, so I'm trying to change the position of these two. So that time first I'm breaking this pair, then I'm breaking this pair, and then I'm changing the position. I'm making new pairs. So to break that pair, to break those previous paired electrons, we need to give some pairing energy. So that actually decreases the stability. So now here we have 3 pairs. So crudely we can say 3p. So these electrons are changing, exchanging the upspin electrons. That's why we are getting stability in terms of exchange energy, E3. These electrons, downspin electrons, are also exchanging in between them. That's why we are getting another stabilizing energy term, another E3. And we are breaking these pairs. So that's why we have to apply some energy. We have to expend some energy. So that's why this 3 pairing energy we have to subtract. So now this one is the stabilizing energy that is working for this full field configuration. In the half field configuration, it was only E3. There were no pairing. We were not breaking any pair, right? But in case of full field, we have paired electrons, and to exchange the electrons into the same spin electrons, so we have to give some pairing energy to break those pairs. So actually this E3 plus E3, that is much greater than this pairing energy. So that's why even if we subtract this pairing energy, this value is still higher than this E3 value. So this E3 plus E3 minus 3p, this value is much higher than this E3 value. So that's why this full field configuration is much more stable compared to the half field configuration. Okay, got it? Now let's see the trend of ionization energy along period. So this one is for S and P block elements. So if we go along period, we see that principal quantum number is, this one is along group. So we are going along group. We have already discussed about along period, sorry. So if we go along group for S and P block element, we see the principal quantum number is increasing. That means the number of shell or number of orbit is increasing, right? From beryllium to magnesium to calcium, the number of orbit is increasing. So the size of the atom also increases. So I'll try to draw again. If this is the attractive girl, and these are the orbitals where these lower electrons are roaming. So the principal quantum number is increasing as we go from top to down of the group. The size of the atom also increasing because we are putting more and more orbits. Now Z star, effective nuclear charge, is also increasing, which works in the opposite direction. Now we can neglect this contribution. Just to let you know, I am giving this information, but these red ones, whatever I have written in red, so those factors are minor factors. So the increase of Z star or effective nuclear charge is minor in this case, and the increase of radius is predominant. So as the radius is increasing, as these electrons are going far away from this nucleus, so it will be easier to remove those electrons. For example, if we need some energy to remove this electron, if we have another orbit, it will be much easier to remove these electrons because this electron is further from the nucleus and this electron is closer to the nucleus, right? So this electron has lesser attraction to the nucleus. That's why it will be easy to remove this electron. So hence, as we go from top to down of a group, the ionization energy decreases. So that was the case in case of S and P block elements. Now let's see in case of D block elements. So in case of D block elements, when we go along the group from top to bottom, the high effective nuclear charge due to D and F contraction. So the effective nuclear charge increases because of the D and F contraction. So the D and F electrons, they are actually diffused in nature. They have less sealing power. So that's why the further S and P electrons, those are having more attraction towards the nucleus. So the effective nuclear charge is much more to those electrons, furthermost electrons also. And also the penetrating power is, the s orbital is having the more penetrating power compared to P, compared to D, and compared to F, right? So s orbital is having the highest penetrating power. So ns orbital penetrates in -1d and in -2f orbital. Hence, to remove electron from ns orbital, much more energy is needed. Now let's try to understand what is this penetrating means. So I will just give you a crude idea. Now let's see. So we have different orbitals. Just think we have some more energy levels here. Now when we consider this electron, let's put one more orbital here, and let's consider that these are the d electrons we have here. Okay, if we have d electrons here, so these d electrons are actually diffused and they have lesser sealing power. So this attractive girl nucleus will attract this electron or this lover, right? So this lover will try to come close, and actually it will go close, and it will go beyond this n-1d or n-2f. It will go closer than these d electrons and f electrons. So that's why this contraction is also known as penetrating power. This s orbital can actually penetrate this d orbital and f orbitals, whatever present there, and it can go inside. Again, try to understand, when we have more number of d and f electrons, their shielding power is less, and that's why this nuclear's attraction is more in this ns electrons. So these ns electrons will feel more attraction towards this girl, and that will go inside, penetrating the d and f electrons. Clear? So as the effective nuclear charge increasing, as well as the penetrating power of S is much more, hence the ionization energy increases. So we have seen for S and P block elements along group, the ionization energy is decreasing, but in case of D block elements along the group, if we go from top to bottom, the ionization energy is increasing. So this is not exception, this is actually rule for these D block elements. If you go from top to bottom, the ionization energy will increase. Now let's see some comparison to make it clear. Okay, now if we take this group 1 elements, lithium, sodium, potassium, rubidium, and cesium, and we see the first ionization energy, so we can see it is decreasing. As we go top to down, it is decreasing, or we can say from down to top, it is increasing this way, right? In case of lithium, it was having 520 kJ per mole, whereas in case of cesium, it is coming down to 375 kJ per mole. Same thing we can see in this group 14, carbon, silicon, germanium, tin, and lead. Again, we can see the ionization energy is actually decreasing from top to bottom, or we can say from bottom to top, it is increasing. In case of carbon, the ionization energy was 1086 kJ per mole, whereas in case of lead, it is only 715 kJ per mole. But now let's see the D block elements. So in case of D block elements, if we see group 4, titanium, zirconium, and hafnium, we see as we go down the group, the ionization energy is actually increasing. In case of titanium, it was 658 kJ per mole, whereas in case of hafnium, it is 760 kJ per mole. Again, see group 5, vanadium, niobium, and tantalum. So you see, in case of vanadium, the ionization energy was 650 kJ per mole, whereas in case of tantalum, the ionization energy is 761 kJ per mole. So in case of S and P block elements, as we go down the group, the ionization energy decreases in case of S and P block elements. Whereas in case of D block elements, as we go down the group, the ionization energy increases. So I hope this is clear. So this is not an exception case. This is actually rule for the D block elements. Okay. Now these are some conversion factors that you need to remember to calculate any, to do any example or sum. For that purpose, I have noted down these conversion factors. So 1 eV per atom is equal to 96.5 kJ per mole, and 1 eV per atom is equal to 23.06 kilocalorie per mole. Now, how to convert this? You can convert this EV. This EV is actually charge into voltage, right? And the charge of electron we know 1.6 into 10⁻⁻19 coulomb. And if you consider that 1 volt, so we get joule per atom. So coulomb multiplied by volt is joule per atom. So we get 1.6 into 10⁻⁻19 joule per atom. Now this is per atom. So if you want to convert it per mole, you have to multiply it by Avogadro number. So if you multiply it by 6.022 into 10⁻23, you will get the value of EV in joule per mole. Now from this joule per mole, you can convert to it in the kilojoule per mole, and you will get this value. 1 EV per atom equals to 96.5 kilojoule per mole. Now this is the chart which I thought to show you. This chart shows first, second, third, fourth, and fifth and sixth ionization energy of these elements or atoms. in the case of hydrogen and helium, you can see hydrogen has only first ionization energy. That is obvious because it has only one electron, right? So it cannot give more electrons, right? In case of helium, it has first ionization energy and second ionization energy. That is also obvious because helium has only two electrons. So at max we can take out two electrons. Similarly, lithium has three ionization energies, I1, I2, I3. Beryllium has four, boron has five, and rest of the elements can have more ionization energies. We can take out more and more electrons, but yeah, at the cost of higher and higher energy. If you see in case of carbon, first ionization energy is 1086 kilojoule per mole, whereas second one 2350, third one is 4620, fourth one is 6220, and if you see the fifth and sixth, that is way high. You can see this one is 38,000 and this one is around 47,000 kilojoule per mole. Because as you remove more and more electrons, the element will become positively charged ion, and those ions will have much more Z effective or effective nuclear charge. They will have much more attraction towards the nucleus. So it will be much more difficult to remove more and more electrons from the ions. So you can note down these values if you need. And this periodic table shows the first ionization energy of these elements in eV per atom unit. Now we will briefly discuss about the ionization energy of molecules. So earlier till now we have seen the ionization energy of atoms. Now we are going to consider the ionization energy of molecules. So with the increase of electronegativity of the central atom, the ionization energy of molecules increases. For example, if we see the trend in the binary hydrides, so we can see here we have nitrogen as a central atom, then oxygen, and then fluorine. So as the central atom is becoming more and more electronegative, what is the electronegativity? That I will show in the later part of this slide or of this lecture. I will describe this electron affinity and electronegativity, all these things. Just for the timing, just remember, as we are increasing the electronegativity of this atom, the ionization energy increases because the central atom holds the electrons, bonded electrons, more tightly. Similarly, in the case of pH3, phosphorus is the central atom, here sulfur is the central atom, here chlorine you can consider as the central atom. And as we increase the electronegativity, the ionization energy of the molecule increases. Same trend you can see in case of these halo acids, fluorine, chlorine, bromine, and iodine. As fluorine is having, fluorine is the most electronegative element, so it is having higher ionization energy. The HF is having higher ionization energy. So it means in case of HF, if you see this is the HF, and in case of HI, if you see HI, so if you want to take out these bonded electrons from HF or HI, the ionization energy will be much higher in case of HF. So it will be much more difficult to remove the electron from this HF molecule. Now similarly, you can see these other examples. NF3 will be having higher ionization energy compared to NH3, and PF3 will having higher ionization energy compared to PH3. Yeah, this one I have to explain. See, NF3 is having higher ionization energy compared to NH3, but PF3 is also having higher compared to PH3, but the amount is not very significantly high as expected. Okay, so the ionization energy of NF3 is higher than NH3 by 268 kilojoule per mole, but the ionization of PF3 is higher than PH3 by only 121 kilojoule per mole. So this can be rationalized by considering the 2p to 3d back bonding, p pi d pi back bonding. Now in case of NF3, so this there is no vacant orbital in case of nitrogen, so that's why these fluorines are just pulling the electrons, right? Fluorines are pulling the electrons towards itself. Now in case of PF3, so phosphorus is having vacant 3d orbital, so that's why these electrons of the fluorine, it can actually go to the vacant 3d orbital of the phosphorus, and that can make a double bond. You can see here is a double bond. F plus means fluorine has given its electron to the phosphorus, and all these fluorines time to time can give their electrons to the phosphorus. So this is called p pi d pi back bonding. So fluorine is giving back electrons to the phosphorus. Now because of this reason, you can see there is a potential negative charge in case of phosphorus. So as it is a negatively charged, you can relatively easily take the electron out. Okay. In case of NF3, fluorines were actually holding these electrons. They were dragging these electrons. So as when you are trying to remove electrons from NH3, you have to put higher ionization energy. You have to give more energy. But now in case of PF3, fluorines, yeah, they are pulling the electrons because of the inductive effect. But at the same time, because of the resonance effect or p pi d pi back bonding, they are also giving back the electrons. Now this phosphorus or the central atom is having partially negative charge. This is called a delta negative charge. Delta sign is like this. So because of this partially negative charge, relatively easier it is to remove that electrons, to remove the electrons from PF3. Okay, but yeah, still the ionization energy of PF3 is higher than PH3 because in case of PH3, these fluorines are having inductive effect. They will hold the electrons tightly compared to PH3, right? So there will be lesser. If you see this, I'll do here PF3. And here I will make PH3. So just try to understand ionization energy of these molecules. Although hydrogen is more electronegative compared to phosphorus, but still you can think there is significant amount of electron density on this phosphorus. Now when you have fluorine, that fluorine actually drags this electron cloud towards itself more compared to the hydrogen, right? That fluorines are dragging the electrons. Now the electron density over this phosphorus will be less. It will be there, but it will be less. But it cannot completely reduce this electron density, right? Because fluorine is doing p by d by back bonding also. That's why it is also giving it back. Some electron density will come back. So comparatively, we have lesser electron density on this phosphorus. So as the electron density is lesser, so this phosphorus will hold these electrons tightly, right? That's why you have to give some ionization energy to take out those electrons. Now that ionization energy will be higher compared to this pH3. Okay. As it is having lesser electron density, it will hold the electrons much more tightly. And because that, if you want to remove electron from pH3 molecules, that ionization energy will be higher, 121 kilojoule per mole higher compared to the ionization energy of this pH3, right? So no doubt that pH3 will have higher ionization energy compared to pH3. This one is clear. Let's try to understand it again. This one is pH3. Hydrogens are pulling the electron a little bit, but still there is significant amount of electron density in the phosphorus. Now when we have pH3, fluorines are pulling those electron cloud towards itself. Now phosphorus is having less electron density. Now when it has lesser electron density, then this phosphorus will have much more attraction towards its electron cloud, right? So it will tightly hold those electrons. That's why you have to put more energy to take out electron from this pH3. But in the other case, these fluorines, they are actually giving the electron back by p by d by back bonding. 2p from 2p of fluorine to 3d of phosphorus. So now because of this p by d by back bonding, some electron density is going from fluorine to phosphorus, and that is actually a little bit increasing the phosphorus's electron density. So that's why the ionization energy, which could be much more, that is not very bigger number compared to the pH3. Okay. For example, if I give some arbitrary numbers, let's take, for example, this pH3's ionization energy is 100 unit. Okay, 100 unit. Now in case of PF3, if we consider that this PF3, these fluorines do not involve in the back bonding. Okay, if the fluorines do not involve in the back bonding, that time the ionization energy should be around 500. Just arbitrary numbers. Okay. Now as the fluorines are giving back the electron density, so phosphorus is gaining some electron density. So it is somewhat easier to take out the electrons. So now the ionization energy comes down around 300 or 250, you can say. So actually, if there was no p by d by back bonding, the ionization energy would have been much bigger value. Okay, but as there is p by d by back bonding, the ionization energy is relatively small, but still it is large enough and larger than the ionization energy of pH3. Fine, is it clear? If you still have any confusion, please go back 5 to 10 minutes and then see the video again. And still, if you are not able to understand, you can comment down below. I will make a separate video on this. So what are the key factors or keynotes regarding this ionization energy? So we have observed that ionization energy is upright property. I will take the laser pointer. So ionization energy is upright property. And do not get confused with the term ionization potential. Okay. So ionization potential is an intensive property measured by volt, whereas ionization energy is an extensive property measured by EV per atom or kilojoule per mole. So ionization energy is slightly different than the ionization potential. Inert gases having highest ionization energy along period occupy the peak positions in the graph, and alkali metals are having lowest ionization energy along a period. From left to right along a period, ionization energy increases for S and P block elements, whereas for D and F block elements, the variation is very less. There is very slight increase. And if you see from top to bottom along a period, ionization energy decreases for S and P block elements, whereas from top to bottom along a period in D and F block elements, ionization energy increases. So this is due to the less shielding effect of D and F electrons, known as D or F contraction or scandite and lanthanide contraction, and higher penetrating power of S orbitals, which I have already explained these things. So this increase in ionization energy along period is not an exception, rather a rule for D block elements. Okay, so these many things you have to remember for the periodic trend in ionization energy. So next we are going to discuss about the periodic trend of electron affinity. So this one is also an upright property. That means the electron affinity increases in the upside from bottom to top in the group and from left to right along the period. So first let's try to understand what is the meaning of electron affinity. For that we will take example of this. Let's suppose this guy. So this guy likes this woman. Now he is thinking of proposing this woman. So he went with a bouquet of flower and he proposed. Now it's up to this woman that whether she will accept this flower or not. If the women like him back, then she will accept it, she will say yes. But if she doesn't like him, then she will say no. So it's actually the decision of the women, right? Similar thing happens in the atomic world, that when you are trying to put an extra electron to an atom, at that time the atom, maybe the atom is accepting that maybe that atom is accepting that electron, or it may be reluctant to take that electron, right? That's why let's take the definition. Let's see the definition now. So electron affinity is the amount of energy released when an electron is added to the valence shell of the isolated gaseous species. It may be atom, ion, or molecule. So you are trying to add an extra electron in the valence shell of the isolated gaseous species. Now, if the atom is willing to take that electron, then the energy will be released. And if the atom is reluctant to take that electron, then you have to give some energy. You have to put some energy. So this one was the older definition, and recently it has been changed, and it is said that energy required to detach an electron from the singly charged negative ion. So the energy for the process of x plus E is equal to x minus. So the same thing, as you are adding an electron to the atom, or you are detaching an electron from the singly charged negative ion. So already you have added the electron to the atom, now you are detaching that extra electron. So it is just two different ways to look at the same incident. Is it clear? So you are trying to put an extra electron in the atom. Now, depending upon the atom's electronic configuration, it might take the electron, and then if it easily takes, it will release the energy. And if it doesn't want to take the electron, then you have to provide extra energy. Now let's take some examples. So some atoms readily attract electrons, and the electron affinity has a negative value, meaning that energy is released as I was talking. So in this case, the girl said yes to that person because the girls like him back. That's why you can see, if you put an extra electron to the chlorine, the delta H of this process is negative. So it is exothermic, minus 349 kJ per mole. So the chlorine atom easily takes electron. Most atoms, however, do not accept additional electron readily, and the electron affinity is a positive value, indicating that energy must be used to add the electrons. For example, nitrogen. So we have already seen that nitrogen has half-filled configuration. So if you want to put one electron, it is not energetically favorable. So the nitrogen atom will not try to take this electron. So if you have to force it, you have to put extra energy to make it N minus. So that's why the enthalpy of the process is positive, plus 20.3 kJ per mole. Now things to remember, that positive value of electron affinity indicates endothermic process, which is not favorable. That means you have to invest energy, you have to put more energy. And negative value of electron affinity indicates exothermic process, which is favorable, readily acceptable. Means chlorine is readily taking the electron. Similarly, fluorine is readily taking the electron. So if the electron affinity is negative, the process is favorable. Now let's see the periodic trend of this electron affinity. So as we go from left to right along a period, the electron affinity increases. And as we go from top to bottom along a group, the electron affinity decreases. So what we can say, along group, if we go bottom to up, the electron affinity increases. So it is increasing from left to right and bottom to up. So actually it is increasing in this diagonal way. That's why I call it upright property, or UR property. Now let's see the 3D plot, 3D bar plot for this electron affinity values. You can see, as we come from left to right, the electron affinity increases. And as we go from top to down, the electron affinity decreases, right? So what are the reasons behind it? So we'll try to understand. For this, I will take this pen. So principal quantum number is fixed along period. When we go lithium, beryllium, boron, carbon, so that time the principal quantum number is fixed, or the number of orbit is fixed, shell number is fixed. Effective nuclear charge increases. So we have already seen, as we go from left to right, the effective nuclear charge increases and size gradually decreases. So same thing we have already seen during the atomic radius, periodic trend of atomic radius, atomic volume, all these things. So as we go from left to right, so we put more and more protons, means the girl is more and more attractive. So that's why these boys, these electrons, which are in the outermost shell, they feel more and more attraction towards this girl. So that's why they shrink, right? The size is also decreasing, and the effective nuclear charge is also increasing because we have more number of protons in the nucleus. Now, when we put more and more electrons, when we go from left to right, so electron-electron repulsion also increases, but you can ignore this fact. That's why I have marked it in red. This contribution is very minor. Another contribution that decides what will be the effect. Okay, so this point is just for your understanding and learning. You can ignore this point for considering the electron affinity trend. So thus, the electrostatic attraction of nucleus towards incoming electron increases along the period, and electron affinity increases. That means when we are trying to put another electron from here to this valence shell, so as we are going left to right along a period, we can see this electrostatic interaction of nucleus to this valence shell's electrons are increasing. So if we put one more electron, it will easily come and the nucleus will attract it with more electrostatic interaction, right? So that's why it will be a favorable process. So as we increase the number of protons, the electrostatic attraction increases and electron affinity also increases. If we place another additional electron, that will easily come and sit in the valence shell. So that's why along a period, the electron affinity increases. You can see here from the graph, here you can see lithium, beryllium, boron, carbon, those things we will discuss. Now let's see along the group. What is the trend along group? So along group, what are the factors are there? Size of the atom increases. So as we go from top to bottom, we have more and more shells or orbits. So that's why the size of the atom increases. Now effective nuclear charge slightly increases, which acts in the opposite direction. But this point is minor, so we can neglect this point. So this is written in the red. This is a minor factor. Now incoming electrons are placed in a higher energy level far from the nucleus. Let's try to understand what it is written here. So when we have, let's suppose, an element which has only 2 shells, and when we go from top to bottom, let's suppose we have another atom which has, so I am drawing it half circle. This will be actually full circle, okay? My full circles are not good, that's why I'm just drawing half circle. Oh, my half circles are also not good. Anyway, so try to understand. When we have this element which has only 2 shells, as we go along the group and we have another next atom which has 3 shells, next atom which has 4 shells. So when we are trying to place an external electron, we are actually placing the electron here in the second shell, right? But in case of this, when we are trying to place an additional electron, we are placing the electron in the 4th shell. So this nucleus is much more closer in this case. The nucleus to the incoming electron distance is lesser in this case, whereas in the right hand side, the nucleus to this distance is much more. So as the distance increases, the electrostatic attraction decreases. So here the distance is less, so the attraction is more. So you can in terms of girl, you can figure out that if the boy is close to the girl, if they meet regularly, or they are very nearby, they live nearby, then there is a high chance that there will be more attraction. But if the girl is very far away and the boy is in another city, so in that case it will be difficult. The attraction will be less, right? They will meet very less. It will not be frequent. So the incoming electrons are placed in a higher energy level far from the nucleus in case of these elements where we have more and more shells. Thus, the electrostatic attraction of the nucleus towards incoming electron decreases along the group, and electron affinity also decreases. So as we go from top to down to the group, the electron affinity decreases. So you can see from here, chlorine is here, then bromine is less, iodine is much more less. So electron affinity decreases along the group. But there are some exceptions. So 3p elements, they actually have higher electron affinity compared to 2p elements. But according to the periodic law or periodic trend, actually it should be the opposite. You see here, the electron affinity is actually decreasing, right? From top to bottom of the group. So this fluorine, when we are going fluorine to chlorine, the chlorine's electronegativity should be lesser according to this periodic trend. But actually, this chlorine's electronegativity is more than fluorine. Or in other language, you can say 3p elements have higher electron affinity compared to 2p elements. Now let's see the pairs. So we have fluorine and chlorine, and this is the electron affinity value. So chlorine has higher electron affinity, and in the pair of oxygen and sulfur, sulfur has higher electron affinity. In the pair of nitrogen and phosphorus, phosphorus has higher electron affinity, and in the pair of boron and aluminum, aluminum has higher electron affinity. But the electronegativity trend is actually completely opposite. Now why so? What is the reason behind it? So to understand that, we have to consider these 3 points. So first one is 2p atoms have smaller size and greater electrostatic attraction. So the 2p atoms, they have smaller size. So smaller size means greater electrostatic attraction towards the incoming electron. But the extra added electron creates electron-electron repulsion. So although it has higher electrostatic attraction, that's why the electronegativity is more in case of 2p elements. But the extra added electron, if we add one extra electron, that creates electron-electron repulsion in that valence shell. Now the repulsion is large in second period elements, but the repulsive force is not so large in the third period element. Now in the third period element, in the 3p has bigger size compared to 2p, right? So when we are adding electron in the 2p, that time electron-electron repulsion is very high. But if we are adding electron in the 3p, that time it can manage, it is not that much high. The next point is possibility of delocalization of increased electron density in vacant 3d orbital reduces the repulsion for third period elements. Now in case of third period elements, they have a vacant 3d orbital. So the incoming electron, which is increasing the electron density, so the atom can pass that electron density to the vacant 3d orbital. And in that way, it can reduce the electron-electron repulsion, right? So that's why these 3p elements, they have higher electron affinity. Whereas 2p elements, they have higher electron negativity. What is electron negativity? We are going to learn after this electron affinity, okay? So just remember, these 3p elements, they have higher electron affinity because the electron-electron repulsion is less. because the electron can be delocalized in the vacant 3d orbital. And these 2p elements, they have lower electron affinity compared to the 3p because of the increased electron-electron repulsion. Okay. Now we will see in case of d block elements. So sometimes electron affinity do not show apparent trend. For example, electron affinity of manganese, which is half filled, and zinc, which is full filled, is 0. So this is the electron affinity data for d block elements. Now if you see, so we said along the period, if we go from left to right, the electron affinity increases, right? So from here to here, the electron affinity actually should increase. And we can see in the case of titanium, palladium, and chromium, the electron affinity is indeed increasing. But in case of this manganese, the electron affinity comes to 0. And from here to here, again the electron affinity is increasing. But again in case of zinc, the electron affinity is 0. Now this happens because in case of manganese, I'll show you the 3D cell. So in case of manganese, the 3D is actually half filled. So in case of manganese, it is 3d5. One electron here, another electron here, another electron here, here, and here. So I have already taught you that when it is in half-filled situation, that time the exchange energy is very high. Exchange energy contributes in the stability of the system or stability of the atom, right? So in case of manganese, it is 3d5 configuration, electronic configuration. So these 5 electrons are having much high exchange energy. So that's why it is very stable structure. And this manganese element or atom, they don't want additional electron. If the additional electron comes, it will come and sit here and it will do the pairing. So this manganese do not want that. That's why this half-filled configuration is having 0 electron affinity. Similarly, in the case of zinc, zinc is actually 3d10. So there are 5 more electrons here, 7, 8, 9, and 10. Here also you see we have these 5 electrons of same spin, and we have these 5 electrons of same spin having down spin. So now these 5 electrons can be stabilized due to the exchange energy. Okay, due to exchange of their position, they can give extra stability to this atom. So that's why zinc also do not want to get additional electron. So that's why the electron affinity is 0. Now the next factor is because of lanthanide contraction, the post lanthanides show unusually high electron affinities. Now lanthanide contraction I have already explained in the lecture 5. So as these F electrons have less shielding effect, so the atom size actually contracts, it shrinks. So because of that, the atom size is very small, and the nucleus to valential distance, the radius r or atomic radius, that is very less. So that's why the nucleus is having higher electrostatic interaction to the incoming electrons, right? I'll simply draw it for you. So this is the nucleus, and there are multiple shells. Now consider this, that there are F electrons here in this layer. Okay, just consider F electrons are here. Now F electron has very less shielding power. So what, and it is diffuse in nature, less shielding power. So what happens? The next orbit, which is after this F, whatever will be the next orbit, so that electrons, they experience high attraction force towards this nucleus. So this orbit actually shrinks. It comes closer, and it comes here. So as it is shrinking, you can see the distance is decreasing between the nucleus and this valence shell, where is the electron density is maximum. So this distance, which is denoted as r, this distance is decreasing now. So this nucleus can now have higher electrostatic interaction. So if you want to place another additional electron, if this F electrons were not there, you had to place it here. But now as you have F electrons, D electrons, because their shielding effect is less, this orbit has shrunk here. Now you are placing this electron actually here, so much closer to the nucleus. So that's why they have unusually high electron affinities. These post lanthanides have unusually high electron affinities. For example, gold has a very high electron affinity, which is 223 kilojoule per mole. So among the metals, gold has the highest electron affinity. Now for your reference, you can check this data. Here I have mentioned the electron affinities. You can see the electron affinity values here. You can see greater than 0 means it doesn't want to take electron. These are having full filled shell. That's why the electron affinity is greater than 0. They don't want to take electrons. Similarly, nitrogen also greater than 0. And especially these inert gases also, they have also full filled shell. They also don't want to take electrons. And the electron affinity is greater than 0. Whereas if you see this fluorine, chlorine, bromine, iodine, they have negative, very high negative electron affinity. So they readily accepts that electron, the incoming electron. So let's see some key points, whatever we have learned in this lecture regarding periodic trend of electron affinity. So we found out that this is a upright property. So it increases from left to right. If you go along period, it will increase, and if you go bottom to up along a group, it will increase. Do not get confused with the term electron affinity with electronegativity. So electron affinity is a discrete atom's property. So electron affinity is actually an inherent property of the element or the atom, whereas electronegativity is the property of a molecule, so bound with another atom. So one atom will have single electron affinity value, but it can have multiple electronegativity value depending on its environment, depending on its with which atom it is bound. Okay. Metals like to lose valence electrons to form cations to have a fully stable octet. They mostly don't like to take electrons. So that's why for metals, the electron affinity value is very less, or maybe sometimes greater than 0. For alkali metals, NS1 electronic configuration, the accommodation occurs in NS level and gives NS2 configuration. Whereas for alkaline earth metals, they already have stable full-field electronic configuration. Thus, the process is favored more in group 1 compared to group 2. Because that group 2 elements, they have already NS2 configuration, full-field configuration. So they are not favorable, they do not favor, they don't want to take the additional electrons. Whereas the group 1 elements having NS1, they can take the electron and they can achieve NS2 state. Nonmetals like to gain electrons to form anions to have a fully stable octet. They release energy, that means it's an exothermic process, to gain electrons to form an anion. Thus, electron affinity of nonmetals is mostly negative. That we have already seen in case of fluorine, chlorine, bromine, right? Those are having negative electron affinity values. Elements with electronic configurations of NS2, full field diamagnetic atom with no unpaired electron, NS2np3, that is half field, and NS2np6, those are the inert gases, have positive electron affinities because they are unusually stable. They are very much stable, these full field and half field configurations. That's why they have positive electron affinities value. They don't want to take additional electrons. Okay. Next, we are going to discuss about the periodic trend of electronegativity. So this is also an upright property. That means along a period, if you go from left to right, the electronegativity value will increase, and along group, if you go from bottom to up, the electronegativity will increase. So first, try to understand what is electronegativity, right? Now you guys have already seen, I guess, this rope pulling game. So there are two teams, and both the teams will try to pull the rope in their side. So if this team can pull the rope in their side, and these members comes this side, so this team wins the game, right? Similarly, if this team can pull the rope in their side, so this team wins. So this rope pulling game is the ideal situation that happens in a bond. So in a bond, two atoms are there, but they are continuously pulling the electrons. I will take a pen. See, assume this team is actually team A, okay, and this team is actually team B. Now in between we have a rope, just call it a bond. Now this bond is consisted of electrons, right? Two electrons make a bond. So these atoms, they will try to pull those electrons towards itself. Similarly, this atom B, that will also try to pull these electrons in their side. So this is exactly how we play this rope pulling game. So this atom is also pulling these electrons in their side. This atom also wants to pull the electrons in their side. Now, whoever will be the stronger, if let's suppose B is stronger, so if B can pull these electrons in their side, so we will say the electronegativity of B is higher or greater than the electronegativity of A. Okay. Let's see the definition now. So it is defined as the electron pulling capacity, that electrons in a bond, of an atom towards its nucleus in a covalently bonded molecule. So this AB, which has a covalent bond in between them, they are trying to pull the electrons, and the electron pulling capacity is defined as the electronegativity. Now key points, so there should be a covalent bond to define the electronegativity of any atom, and electronegativity is not an inherent property, so it depends on its surroundings. So if you change the atom B to atom C or atom D or any other atom, the electronegativity of all the atoms will change. Okay. Now this periodic table shows the electronegativity value of the elements, of all the atoms. Now from this data we can see, if we go from left to right, let's take this lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. If we go from left to right, the electronegativity value increases. Again, you see in this group wise, if we go from top to down, the electronegativity value decreases. So if you go from down to top, the electronegativity value will increase. So these are the electronegativity values of all the atoms. And this is a 3D bar plot from which you can clearly see that electronegativity is increasing along the period. And if you see here, it is decreasing along the group. Now let's see the reasons. What are the reasons behind it? So let's first see the electronegativity trend along period. So along period, what are the factors there? Principal quantum number is fixed. So the number of shells are fixed. Effective nuclear charge increases. I have already shown multiple times that as we go from left to right, the number of proton increases. That's why the effective nuclear charge also increases, and size gradually decreases. So we have same principal quantum number, we are filling electrons there, and the number of proton is also increasing. As the number of proton is increasing, the effective nuclear charge is increasing, and size is also gradually decreasing. And as we have more and more electrons, the electron-electron repulsion also increases, but this is a minor factor. We can ignore this. So considering all these factors, we can say that electrostatic attraction of nucleus towards bonding electron increases along the period. So the electronegativity also increases. So I will draw it here. You see, this is the nucleus of atom A. Oh, sorry. And this is the nucleus of atom B. So here the principal quantum number is fixed. So the number of shell is fixed. It will have same number of shells, but you see the size is smaller. As we go along the period, the size becomes smaller. So if you form a bond between some another atom, let's suppose atom A. Now, if this one is forming a bond with atom A, and this one is forming a bond with the atom A. Now, if the electrons are here, somewhere in between the bonds, you can see the electrons of the bonds will be much closer to this nucleus compared to the electrons of these bonds. Okay, for example, if you see these electrons here and these electrons somewhere here, so these electrons are actually much closer to this nucleus because it has high effective nuclear charge and small size. So if the size is small, that time the electrostatic attraction will be more, and that will attract the bonded electrons, that will attract towards itself. So that's why the electronegativity will also increase. That you can see from this atomic number versus electronegativity plot. As you go from lithium to fluorine, lithium, beryllium, boron, carbon, nitrogen, and fluorine, you can see the electronegativity is gradually increasing, or sharply. You can see electronegativity is sharply increasing here, right? So similarly, if you go along period, as the size shrinks, the electronegativity increases. Now let's see along group. What is the effect that is playing role along group? So if you go from top to down along the group, the size of the atom increases. Now size of the atom increases means the electrons, bonding electrons, will be much farther from the nucleus, right? For example, let's see this atom, and let's take another atom. Now as you are going from top to bottom, the size of the atom increases, the number of orbits also increases. Now if you make a bond between another atom A and here another atom A, so these bonded electrons are actually much further in this case, whereas these bonded electrons will be much closer to this atom. So this atom having smaller size, it has more electronegativity. Now in this case, in this atom, it is down to this atom. So in a group, we are going from top to down. So the number of orbits is increasing, number of orbits are increasing. As a result, the size of the atom is also increasing, and these bonding electrons are placed far from the nucleus. So this is the nucleus, and these bonding electrons are placed far away. So that's why the electronegativity decreases along a group. Now here is one more point, that effective nuclear charge slightly increases, which acts in the opposite direction, and it's a minor effect. Now if you see this element, fluorine, then chlorine, then it might be the bromine. So these elements show that as you go from top to bottom along the group, the electronegativity decreases. But there are some exceptions, and the exception lies in the D series. So 3D to 4D electronegativity falls slightly, but 4D to 5D electronegativity increases due to lanthanide contraction. So along the group, the electronegativity actually should decrease, which is happening from 3D to 4D. The electronegativity is slightly decreasing, but from 4D to 5D, the electronegativity is actually increasing because of the lanthanide contraction. So because of the lanthanide contraction, what happens? The F electrons and D electrons, they are having lesser shielding power. So the nucleus, and that is attracting more to the valence electrons, and because of that, the size also contracts. And as the size becomes small, now the nucleus of the atom is closer to the bonded electron, and that's why it can pull the bonding electrons towards itself, and because of that reason, the electronegativity will be higher. Now we will try to remember the electronegativity order of the first 12 elements. So this is very helpful actually, and I always remember this in many competitive exams or during practicals. Many times you need to remember that which element is having higher electronegativity. For example, if I draw pH3, you need to take a few seconds to realize that which one, either the phosphorus or hydrogen, which one is having higher electronegativity, which one is having plus charge and which one is having minus charge, right? Similarly, if I draw methane, CH4, it will take you some time to realize or to remember which one will be positively charged and which one will be negatively charged. Or in case of borosilicates, that is also you have to remember, or you may need few seconds to remember which atom will be positively charged, which atom will be negatively charged, and that you can decide based on the electronegativity order. So the element which is having higher electronegativity, that will form minus, negatively charged. For example, if there is a bond between oxygen and chlorine, so O will be minus and chlorine will be plus charge. Because the electronegativity of oxygen is higher, so it will take the electron and it will become O minus, whereas chlorine, which has lesser electronegativity compared to the oxygen, so that will become plus. For that reason, it will be handy to remember the electronegativity order of first these 12 elements. And I always remember these first 12 elements. There might be some more metals in between in these spaces, here or somewhere here or somewhere here, somewhere here. But those metals you may not need to know those things, but these 12 elements we need to remember. Yeah, so one more thing, that there might be some more metals in between here, but for our practical purposes, for remembering these 12 elements, we need to remember. Or even if you want to remove this first word, you can remove. So electronegativity order of these 12 elements. Now how to remember? So you have gone to a Xerox shop, and in the Xerox shop you have to make photocopy of some important documents, and then you saw that your friend Firoza Usman's brother is there, and he is secretly copying some photos of girls. So how you can remember? You can remember Firoza Usman's clever naughty brother is secretly copying hot pics both sides. So you went to the Xerox shop and you saw there that Firoza Usman's brother is there. He's also copying something, and he's very clever as well as naughty, and that brother is secretly copying hot pics both sides. So he's photocopying some actress models and their photos with bikinis. So you have to remember Firoza Usman's clever naughty brother is secretly copying hot pics both sides. From this Firoza, you can remember F stands for fluorine, this one. From this Osman, O stands for oxygen. From this clever, Cl, then nitrogen will come, and from the brother, bromine will come, and from this E's, I will come, iodine. Now in this, secretly this sulfur, this first S is denoting the sulfur. From the copying, carbon, and what is he copying? He's copying hot pics. So from the hot, H stands for hydrogen, P stands for phosphorus, both B stands for boron, and in this side, this Si stands for silicon. So you can remember Firoza Osman's clever naughty brother is secretly copying hot pics both sides. Or if you know the meaning of Fokla, I remember like this also. Fokla naughty brother is secretly copying hot pics both sides. So in Bengali, Fokla means someone who doesn't have teeth. So he has lost many teeth. That's why we call it Fokla. So from the Fokla, you can remember these first three atoms, fluorine, oxygen, and chlorine. And then naughty brother is secretly copying hot pics both sides. That is same as of the above. So this is the easier way in which you can qualitatively remember that which atom is having higher electronegativity compared to the other atoms. So this is qualitatively you can remember. You don't have to remember these values, so quantitatively it is not needed, but it is necessary to remember it qualitatively, that which atom will come first. Now let's talk about Pauling's electronegativity. So the electronegativity periodic table, which we saw earlier, that is actually based on Pauling's electronegativity. So it originates from the concept of valence bond theory, VBT. In a covalent bond AB, the ionic forms also contribute. The contribution depends on the electronegativity difference between A and B. So these two atoms, which are forming a covalent bond, so inside their covalent bond, they also have some ionic nature. Now, because of the covalent ionic resonance, the actual bond energy is always greater than the hypothetical 100% covalent bond. So as I mentioned, if there is a bond between two atoms A and B, so the bond is having some portion of covalent bond and some portion of ionic bond. So that is called covalent ionic resonance. So some part is coming from the covalent bond, some part is coming from the ionic contribution. So that's why, because of this ionic resonance, because of the presence of this ionic nature, the actual bond energy, which is EAB, that is always greater than the hypothetical 100% covalent bond. So this difference gives the measure of covalent ionic resonance energy. So what happens? The actual bond, which is having higher strength, if you take that and then subtract the hypothetical 100% covalent bond between A and B, the amount whatever you will get, that represents the covalent ionic resonance energy. So how you can write? You can write this covalent ionic resonance energy, delta, is equal to actual bond energy minus energy of the corresponding 100% covalent bond. So this delta AB represents this covalent ionic resonance energy. That is actually EAB, the actual energy, minus EAB covalent, which represents 100% covalent bond. So this EAB covalent can be written as this geometric mean. So this is the geometric mean of these two. To understand this, first we have this molecule A2 and we have this molecule B2. Okay. Now, if you break these two bonds and if you break this bond and if you break this bond and then if you join this A and B, so this energy of this AB will be actually equals to this value, square root of energy of AA multiplied by energy of BB. Okay. So we can write this value in term of this energy of 100% covalent bond between AB. So if you put that, we get delta AB is equals to EAB minus under root of EAA into EBB. Now Pauling suggested this 100% ionic character in AB bond is actually proportional to the difference between their electronegativity, that is proportional to chi A minus chi B, and that is also proportional to square root of covalent ionic resonance energy or delta AB. So from here we get that chi A minus chi B. This chi is the symbol of electronegativity. So electronegativity of atom A minus electronegativity of atom B is actually square root of delta AB. That means if we take square root of this covalent ionic resonance energy, we get the electronegativity difference between those two atoms. Now this chi A minus chi B, whichever is greater, you can take that. If electronegativity of B is greater, you can take chi B minus chi A. Okay. So if we put the value of this delta, which is this value, we get chi A minus chi B is equals to this equation. So here delta is in eV, electron volt per molecule. So from there, we observe that chi A minus chi B is proportional to under root covalent ionic resonance energy of delta AB. Okay. So chi A minus chi B is equal to under root delta AB. And here delta was in eV per molecule. Now 1 eV per molecule is equals to 96.5 kilojoule per mole. So we can convert this value from eV per molecule to kilojoule per mole. We just divide it by 96.5 and eventually we will get 0.102 square root of delta AB. So here this delta value is in kilojoule per mole. So this delta is the covalent ionic resonance energy. And from there, if we take this value in the left hand side and we square it, then we get delta AB is equals to 96.5 into chi A minus chi B whole square. So this is the one equation that you have to remember, this one. And also this one, chi A minus chi B is equals to 0.102 square root of delta. Here delta is in kilojoule. And also you have to remember this one, here delta in eV per molecule. Simply if you just put 0.102 before this term, you will get delta in kilojoule per mole. And similarly, you can convert this eV per molecule to kilocalorie per mole using this factor. So if you just divide it by 23.06, you will get chi A minus chi B is equals to 0.208 square root of delta. So here delta is in kilocalorie per mole. So these three things, these three formulas you can remember. And from here, if we just take this factor in the left hand side and then square both the sides, we will get delta AB is equals to 23.06 chi A minus chi B whole square. So these formulas you have to remember, and I will erase all these things. You can take a screenshot of this. You can pause the video and take a screenshot. Now we will discuss about different type of electronegativity. Earlier we observed Pauling's electronegativity. Now we will discuss about Mulliken's orbital electronegativity, which is represented as chi m. Now Mulliken said that electronegativity of an atom is orbital dependent, and electronegativity of an atom is related to both ionization energy and electron affinity. So Mulliken suggested that chi m of atom A is equals to half of the summation of IEA, means ionization energy of A, and electron affinity of A. So this is in eV per atom. So you can again convert this eV per atom to kilojoule per mole. You have to just divide it by the factor 96.5 and you will get chi m, or the Mulliken's orbital electronegativity, is equals to 0.0052 IE ionization energy of A plus electron affinity of A. So here this ionization energy and electron affinity, those are in kilojoule per mole. Similarly, you can convert this formula in kilocalorie per mole by dividing by this factor 23.06. If you divide it, you will get chi m is equals to 0.0217 ionization energy of A plus electron affinity of A. So here ionization energy and electron affinity, they are in kilocalorie per mole unit. Again, I will remove all those inks. You can pause the video and take a screenshot. Now let's see the relation between Pauling's electronegativity and Mulliken's electronegativity. So the relation is given as chi p, means the Pauling's electronegativity is equals to 0.168 times of this ionization energy plus electron affinity of the atom and minus 1.23. So if we subtract this 1.23 from this ionization energy and electron affinity value, and then if we multiply it with 0.168, we get Pauling's electronegativity. Now this can be converted into Mulliken's electronegativity. This IE plus EA, and we know half of IE plus EA is equals to chi m. So you can just convert it to chi m, and ultimately we'll get 0.336 chi m minus 0.616, which will give 0.336 km minus 0.2. So this is the relation between Pauling's electronegativity and Mulliken's electronegativity. And even some scientists proposed that chi p and chi m should be related like this. Chi p is equals to 1.35 times of square root of chi m, and then you subtract the value 1.37. So any of the values, both the formulas you can use to relate the Pauling's electronegativity with Mulliken's electronegativity. Now let's see some other important facts. So electronegativity is also orbital dependent, and the sequence for the normal orbitals is actually ns greater than np greater than nd greater than nf. So ns is having, so s orbital is having more electronegativity compared to the other orbitals. That because this s orbital lies closer to the nucleus. Now let's see the sequence for sp hybridized orbitals. For the hybridized orbitals, the sp orbital is having higher electronegativity compared to sp2 and compared to sp3. Now let's see some examples. For example, if you consider carbon atom, so in case of only p orbital, the electronegativity value is 1.74, whereas when it is sp3 hybridized, the value is 2.52. When it is sp2 hybridized, it is 2.8, and when it is sp hybridized, the value goes to 3.34. So as we can see, as the s character increases, the electronegativity also increases. So if you see here, s character is 0, here it is 25%, here it is 33%, and here s character is 50%. So as the s character increases, the electronegativity of the element or atom also increases. Similarly, in the case of nitrogen, we can see in the pure p orbital, the electronegativity value is 2.52, whereas in the sp3 hybridized form, the electronegativity value is 3.74, in the sp2 hybridized form, it is 4.18, and in sp hybridized form, it is 5.14. So along with that, some additional information that we know Mulliken's electronegativity is defined as chi m, and chi m is equals to 0.5 multiplied by ionization energy of the atom and electron plus electron affinity of the atom. Now if you just change this plus to the minus sign, so that will give the absolute hardness of atom. So that gives absolute hardness, and it is represented as this symbol eta. So eta absolute is given as 0.5 multiplied by ionization energy of A minus electron affinity of A. Now let's see some keynotes regarding the electronegativity. So we have observed that electronegativity is actually upright property. That means if you go along period, it increases from the left to right, and if you go along group, it increases from the bottom to top. So that's why it is upright property. Okay, and do not get confused with the term electron affinity. So electron affinity I have already discussed before. So electron affinity is hugely different than electronegativity. Okay, so electron affinity is inherent property of an atom, and it is independent of the surroundings, whereas electronegativity is the property of a molecule bound with another atom and not an inherent property. So let's take an atom A. Okay, so if you make a bond between A and B and make another bond between A and C and another bond between A and D, so in all those cases the electronegativity of A will be different. Okay, because its environment is different. It is bounding, it is making a bond with different atoms. Okay, and in Mulliken's electronegativity, we take the first ionization energy and first electron affinity values. The electronegativity is also orbital and hybridization dependent, that we have just seen in the earlier slide. And electronegativity depends on the charge of atom as well. So with the increase of positive charge, the electronegativity increases, whereas it decreases with the increase of negative charge. So this happens because if you increase the positive charge, so the atom will be more and more positive. That means in the atom, it has less number of electrons and it has more number of protons. When it has more number of protons, the electrostatic attraction will be more. The size of the atom will become less. Now, when the size of the atom is less, the nucleus will become more powerful, and that will draw the bonding electrons towards itself. So it will try to pull the bonding electrons more and more. So that's why the electronegativity decreases when we increase the positive charge. Whereas when we decrease the positive charge or increase the negative charge, so that time we are increasing, when we are increasing the negative charge, that time the atom is getting bigger in size. So as the atom is getting bigger and bigger in size, so the distance of bonding electrons to the nucleus is increasing. So that's why the electronegativity value is also decreasing. Okay. Now let's see the periodic trend of metallic character. So metallic character is down left property. I'll take the pen again. This is a down left property. So let's see the periodic table again. And in the periodic table, you see this portion is very crucial. This portion. So this portion is actually dividing this periodic table into two halves. So this right hand side, these are called non-metals, whereas this left hand side, these atoms and elements, they are called metals. So here in this periodic table, these sky ones are metals, and these green ones are metalloids, and these yellow ones are non-metals. These middle elements, these elements which are separating these metals to non-metals, so they are having some property common to metals and some properties common to non-metals. So that's why these are called metalloids, which is in between metal and non-metals. So if I will just say one more thing, that metalloids, these are the metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium. So people remember it as a stair step. So you get one step, again here one step. So as a stair step, we need to remember it. And in this test step, I remember it as 1, 2, 2, 2 formula. That means when we are making this test step, first we have one element, boron. Then in the next step, we take two elements, silicon and germanium. And in the next step, we take another two elements, arsenic and antimony. And again in the next step, we take tellurium and polonium. So these 1, 2, 2, 2, I remember for the metalloids. Now, how do we define the metallic character? So the metallic character of an atom is estimated as the ability of losing electron and gaining positive charge. So if you have one element, maybe let's take magnesium or sodium, so these elements, they will try to lose the electrons. If they are more prone in losing the electrons and gaining the positive charge, that time we will say that they have higher metallic character. Whereas if you take this this right hand side element, these elements, they do not want to lose the electrons, whereas they want to gain the electrons. And gaining electrons, they will gain negative charge. So that's why these are called non-metals. Now if you see the periodic table, so the metallic character increases in the down left property. This metallic character is the down left property. So along a period, if you go from left to right, the metallic character actually decreases. In the other word, if you go from right to left along period, the metallic character increases. And from top to bottom, if you go along the group from top to bottom, the metallic character increases. Now why so? We are going to see. Now let's first see along period. What are the factors that are affecting along period? So along period, principal quantum number is fixed. That means the number of orbits are fixed. The number of shells are fixed. Effective nuclear charge increases. Yeah, we have already seen as we are putting more and more protons in the nucleus. So the effective nuclear charge, the attraction of that attractive girl towards the boys, that is increasing, right? Now size gradually decreases. This also we have already seen. And the other factor is electron-electron repulsion also increases, but this is a minor factor. We are not going to consider this in this case. So for this, the electrostatic attraction of nucleus towards valence electron increases along the period, and the possibility of losing electrons decreases. Hence the metallic character decreases. So that means when we are going from left to right, let's take this from left to right along a period. So what are the things happening? The effective nuclear charge is increasing and the size is gradually decreasing. So now as the size is decreasing, the nucleus can attract more the electrons, the valence electrons, right? So now if the nucleus is attracting more and more to the valence electrons, now it will be difficult to take out electrons, and the atom will not try to lose electrons. So if it doesn't lose electrons, then the metallic character decreases. Okay. Now let's see along group. What are the factors that working along group? So if we go from top to bottom along a group, we can see the size of the atom increases. We have already seen that when we go from top to down, the number of orbit increases. As a result, the size of the atom also increases. Now I will show. Let's suppose in case of lithium, so this is the nucleus, and this is the first orbit, and this is the second orbit. Whereas if you take the sodium, in case of sodium, this will be the first orbit, this will be the second orbit, this will be the third orbit. Okay. So as we are going from top to bottom, the size of the atom increases, and the outermost valence electrons are placed far away from the nucleus and easier to take out. So the outermost electrons are here in the second shell, right? Whereas in case of sodium, the outermost electron is in the third shell. So it is very easy because it is now the distance is more from the nucleus to electron. So that as the distance is more, now it is relatively easy to take out this electron from here to outside. So if we take out this electron, means it will be easier to remove the electrons. So that's why the metallic character increases along the group. So as we go from top to down along a group, the metallic character increases. Now one more factor we will see, that as the metallic character is defined as the tendency to lose electrons. So that's why these metals, which we call metals, these metals can easily lose electrons. And by losing electrons, the number of electron becomes less and the number of proton becomes more. For example, let's take sodium. In case of sodium, so first we have 11 protons and 11 electrons. So as we remove one electron, so that time we still have 11 protons, but now we have only 10 electrons. So this forms a unipositive charge. So this is called a cation. So sodium forms a cation because it is a metal. And generally these metals tend to form cation by losing electrons. Whereas in the right hand side of the periodic table we have non-metals. They actually tend to form anions. They try to take electrons because they have higher electroaffinity and electronegativity. That's why they tend to take the electrons, and by taking electrons, the number of electrons compared to the protons get increased and it becomes negatively charged and they form anions. So let's see the keynotes in the periodic trend of metallic character. So this is a down left property we have already discussed. That is a down left property. And from left to right along a period, metallic character decreases. As we go from left to right along a period, the metallic character will decrease. And from top to down along a group, the metallic character increases. And non-metallic character goes exactly opposite to the metallic character. So from left to right along a period, as the metallic character decreases, the non-metallic character increases. Whereas from top to down along a group, as the metallic character increases, from top to down along a group, the non-metallic character decreases. So if someone asks you about non-metallic character, you just simply have to reverse the metallic character trait. Okay. Now we will see the periodic trend of cohesive energy. So by the term cohesive energy, we are referring the periodic trend of melting point and boiling point. Okay. So this is actually a curvy property. Now let's see. So first we have to know that what is a cohesive energy. What is the term means? So you can see there are two different molecules. So the interaction between two different molecules, here blue one and the green one, that is known as adhesion or adhesive energy or adhesive force. Whereas the interaction between two similar type of molecules or atoms, that is known as cohesion. For example, if uh, if you have a group of boys, okay, so if you have a group of boys, so all are boys, so that defines cohesion. And if you have mixture of boy and girl, so that tells adhesion. So cohesive energy or cohesion is related to similar type of molecules or atoms, whereas adhesion is related to different type of molecules or atoms. Okay. Now when there are more than one molecules, they experience intermolecular forces. As we put more than one atoms or one molecules, they will experience some intermolecular force. Either they will attract or they will repulse each other. Now cohesion is an attraction between molecules or atoms of the same substance. So as I said, it's a all boys class or all boys property. And adhesion is an attraction between molecules of different chemical substances. For example, as I said, if you put boys and girls together, some boys will talk to the girls, and that is actually adhesion, example of adhesion. Now let's see the definition of cohesive energy. The cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other, or the amount of energy that is responsible for holding the atoms or molecules together. So here I will try to draw. Let's suppose you have an atom A. Now these atoms are bound to each other, okay? These atoms are bound to each other by these bonds. And you might think that these bonds are in all four directions, okay? Now if you want to take out one atom from this, you have to supply some amount of energy. And supplying energy, you can break these bonds, this one or this one. So you have to supply energy and you have to break all these bonds, then only you can take out this one atom, right? So the energy required to separate this atom from rest of its atoms, that is known as cohesive energy. Or in other words, you can say the energy that is responsible for holding the atoms. So these atoms, this atom is sitting here, so there is some amount of energy that is making it responsible to sit in that location, okay? So that also in both terms you can define cohesive energy. Now this is the periodic table which is showing the periodic trend of melting point. And if you see, if you go from left to right, so first the melting point is increasing. So the circle, as big the circle, if the circle is bigger, that tells the melting point is more. And if the circle is small, that tells the melting point is very low and small and it easily melts. So as you can see, as we go from left to right, first the melting point increases, the circle becomes more and more big. And then as we go to extreme right, we can see the circle becomes more and more small. So first it increases, then it decreases, okay? Now same thing you can observe from this 3D bar plot of melting point. You can see this, first it is increasing and getting maxima and then it is decreasing. So if you follow this line, first it is increasing and then it is decreasing. Similarly, we can see the periodic table containing the information of boiling point of the elements. Now if you see the boiling point, that also refers to the same trend. As we go from left to right, first it is increasing and then if you go more right, that time it is decreasing. The spots have become more and more small. That means the boiling point is decreasing. Again, we will see the 3D plot. And same thing we can see as we are going from left to right, first the curve is increasing and then the curve is decreasing, okay? Now why it is happening? So we have to understand the factors. What are the factors that are responsible for this type of behavior? So we will see first the trend of cohesive energy along period. Cohesive energy maximizes at group 14, then falls to the minima. So this is the group 14 elements. You can see if you go along period, for example, beryllium, boron, carbon, nitrogen, so the group 14 elements are having higher cohesive energies. And then again it is falling down. For d block elements, yeah, so this one is for the S and P orbital, sp elements. Whereas for the d block elements, it maximizes at group 5 and 6 and then falls. So I'll go back, I'll show you again. So see this boiling point data. From here you can see these d block elements are increasing first, cohesive energy, then decreasing, right? Similarly, if you see this S and P block elements, if you consider this sp together, then you will get to see first it is increasing and then it is decreasing. So the maxima is at group 14, means this carbon series. This carbon group, it will show maximum cohesive energy. Whereas in case of D, D block element, it shows maximum near group 5 and group 6, this region, somewhere this region. Now what is the reason behind this increased cohesive energy? Okay, that we have to find out. So the availability of number of unpaired electrons determines the extent of cohesive energy. With the increase of number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now, if you see the electronic configuration, you will see that beryllium is actually 2s2, so completely filled. So I will write here the electronic configurations. Now this one is 2s2, 2p1, and for carbon it will be actually 2s2, 2p2, but so if you see this 2s2, 2p2 will look like this. So first we have this one 2s2 and then 2p2, one electron here, and this p orbital is vacant. But what happens during bond formation, hybridization occurs, and this s and p, these orbitals get merged. So this was before hybridization, 2s and 2p, and after hybridization it becomes 4 orbitals together, and in all 4 orbitals they have only 1 electron. So this is called sp3 hybridization, and carbon forms this sp3 hybridization. Now in sp3 hybridization all orbitals have only 1 electron. So now all these 4 orbitals, they can participate in bonding. So this s, 2s and 2p, 3 orbitals of this 2p, they come together and then they make 4 then sp3 hybridized orbital. These sp3 hybridized orbitals can make 4 bonds. So that is the maximum number. In case of boron, even if you do sp hybridization, that will form only sp2. So only 3 electrons can be there. And if you go to nitrogen, there is one more electron, and that will be here. Even if it is sp3 hybridized, that has 5 electrons in total. So 1 electron pair and 3 unpaired electrons. As nitrogen has 3 unpaired electrons, so nitrogen can form at max 3 bonds, even after hybridization. Whereas carbon had 4 unpaired electrons, right? See, carbon has these 4 unpaired electrons. That's why carbon can form 4 bonds. So when carbon is in a carbon atoms are there all over, one carbon atom binds to 4 different carbon atoms. Similarly, all other atoms, for example, boron, that can bind to at max 3 atoms. Nitrogen can bind at max 3 atoms. So this binding increases in case of these group 14 elements. Group 14 because they have 4 unpaired electrons. So if you see again, the availability of number of unpaired electrons determines the extent of cohesive energy. If the number of unpaired electrons are more, the number of bonding will be more. Bonding within same type of atoms. So that's why the extent of cohesive energy will be more. You have to apply more amount of energy to take out that atom, right? Now with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. That is what I just explained. Now Ns and Np can accommodate maximum 4 unpaired electrons through sp3 hybridization that I have shown here after sp3 hybridization. So this one is the hybridized orbital, sp3 hybridization. Okay, I'll write it as H, hybridized orbitals, which is attained in group 14. And for d block elements, d electrons can also participate in bonding. As d electrons can also participate in bonding, that's why the d block elements, they have more number of electrons to make this bondings. Okay, so that's why the cohesive energy is also much greater. Now let's see what is the trend along group. So along group, number of available unpaired electrons remains same. So if you go from top to bottom of a group, the shell is same, valence electrons are same. So the number of available unpaired electrons are also same, right? Now for S and P elements, size of the atom increases. So for S and P block elements, if we go from top to down, the size of the atom increases. It becomes bigger because we are increasing the number of shell or orbits. The increased size reduces the number of bonds per unit area. So as the atoms become bigger and bigger, the number of bonds per unit area decreases. So if you have this, just see, if you have this carbon atom, let's suppose, so it can bind with this atom, it can bind with this atom, and it can bind with this atom, it can bind with another atom. Now see, within this much area there are so many bonds, so you can just multiply it. All these atoms are bound with 4 other elements. Now if you see silicon, or let's say tin, the atom size is bigger. Now that is bound to another bigger atom, that is bound to another bigger atom, now another bigger atom, and another bigger atom. Similarly, these atoms are also bound in all 4 directions, but here the circle is much bigger compared to this, right? So we have same number of unpaired electrons, we have same number of bonds, but as size is small, here we have more number of bonds per unit area, whereas as the atom size is bigger, here we have less number of bonds per unit area. So hence, the cohesive energy decreases in S and P block elements as we go from top to bottom because the size of the atom increases. Now, for D block elements, size change is significantly less due to the D and F contraction, which I have already explained in the previous lecture. So because these D and F electrons are diffused, they have less sealing power, and that's why the nucleus have more attraction towards the outermost valence electrons. So that's why the size change is significantly less. As we put more and more protons, it can attract the outermost electrons, and size is almost similar. So density of atoms increases. So the density of the atom also gets increased, and these heavier elements experience higher cohesive energy. So if you see here, as we go from top to bottom of a group in S and P block element, we can see the cohesive energy actually decreasing. For carbon, it is maximum, then silicon, germanium, tin, lead, the cohesive energy amount is decreasing. Whereas if you see in case of D block element, so in D block element, this curve is for the 3D element, 3D elements. Now if you go down, this one will be for 4D elements, and this one is for 5D elements. So this one is chromium, molybdenum, and tungsten. So this one chromium, then if you go down molybdenum, and if you go down tungsten. So along the group we are going down, but these heavy, as the atoms are becoming more heavy due to D and F contraction, the cohesive energy is increasing. So here you have to remember that cohesive energy for S and P block and D block along group runs in the opposite direction. Okay. Here you can see the atomic number versus melting point graph. This one, and on the right hand side, the same graph you can see. So the scale is different. It is in Kelvin scale, and this one is degree centigrade scale. So from here we can see that carbon is having the highest melting point. And here in these plots, I'm showing you the atomic number versus boiling point data. So here boiling point is given in Kelvin scale, and these ones are the data. You can see, if you need for your reference, you can take a look of this periodic table. So let's discuss about the key points. So we have observed that this trend in cohesive energy is actually a curvy property. So first it increases, then becomes maximum at group 14 in case of S and P elements, and in group 5 or 6 in case of D block elements, and then it comes down. So the cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other. The availability of number of unpaired electrons determines the extent of cohesive energy, and with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now along period, cohesive energy maximizes at group 14, then falls to the minima. And for D block elements, it maximizes at group 5 and 6, and then it falls. Inert gases having only weaker van der Waals force acting as the intermolecular interaction have the lowest cohesive energies. And along group, cohesive energy decreases in S and P block elements if you go from top to down, whereas it increases in the case of D block elements due to D and F contraction. Okay. Now let's summarize all these trends. So whatever till now we have observed. So we have observed the trend of atomic radius, metallic character, ionization energy, electron affinity, electronegativity, atomic volume, and cohesive energy. And these are the short notations that you can remember, and it will be very easy for you to remember if you remember these short notations. So for atomic radius and metallic character, this is actually down left property. So the arrow is pointing at the down and left side. Whereas for the ionization energy, electron affinity, and electronegativity, the property or the trends are actually upright property. So the arrow will be in the upright corner. And for atomic volume, so this will be a curve which is going down and then increasing. And for cohesive energy, this will be a curve which is first going up and then decreasing. So these are the short notations that will be extremely helpful for you to remember these periodic trends. And this is the summary. And this is also, you can take a note, or you can pause the video and take a screenshot of this. This will also be extremely helpful, where I have specifically written what will be the trend in S and P block elements as well as D block elements. So all the exceptions are also written here. Next, we will quickly discuss about the extreme of these periodic properties, highest and lowest ones. So atomic radius, for francium, the atomic radius is highest. For helium, it is lowest. In case of atomic volume, francium has highest atomic volume, and boron has the lowest atomic volume. Ionization energy, helium has the highest ionization energy, whereas cesium metal, which has the lowest ionization energy. If you consider the electron affinity, chlorine has the highest electron affinity, and francium metal has the lowest electron affinity. Whereas in case of electronegativity, fluorine has the highest electronegativity, and cesium has the lowest electronegativity. If you consider the metallic character, francium is having the most metallic character, and fluorine is having the lowest metallic character or the highest non-metallic character. And if you see the number of isotopes, tin is having the most number of isotopes. It has almost 10 isotopes. And if you see electric quadruple moment, lutetium is having the highest electric quadruple moment. That means this atom is highly deformed. This nucleus is highly deformed. Now we will discuss about another important feature, that is the diagonal relationship. So the diagonal relationship signifies the similarities in properties of the elements of the second period with the respective diagonally opposite third period element. So if you see the second period element lithium, beryllium, boron and carbon, and if you see the third period element sodium, magnesium, aluminum and silicon, so you will observe that the properties of lithium and magnesium, this pair, is kind of similar, whereas the properties of beryllium and aluminum, that is also similar, and the properties of boron is also very close to the properties of silicon. Now why this happens? So to understand this, the thing is, most of the periodic trends that increases from left to right, that actually decreases from top to down along the group. So if a trend is there that is increasing this way, that will also decrease this way. Or if you go this way also, the trend decrease this way, whereas increase this way. So that is how it is. These diagonal elements are actually having almost same properties. Now I will try to justify it by giving some arbitrary calculations. For example, let's take this beryllium and aluminum, or boron and silicon. Let's take this boron and silicon, okay? And let's consider this atomic radius and metallic character. So for example, boron, let's consider the atomic radius and metallic character is denoted by x, and we know that atomic radius decreases along the period. So if we go from here to here, the atomic radius will decrease, right? So this atomic radius and metallic character I denote by x, it will decrease. Let's suppose it will decrease by 1 unit. So here in case of carbon, it will be actually x minus 1. And again, suppose in case of going down a group from boron to aluminum, this atomic radius and metallic character increases by 1 unit. So from boron to aluminum, it will come down and it will become x plus 1, because we are defining that from top to down it gets increased by 1 unit. Okay. Now if you go from aluminum to silicon, again the atomic radius and metallic character should go down, or should decrease by 1 unit, because we have already defined that it will decrease by 1 unit from left to right, and it will increase by 1 unit from top to down. So if we go from aluminum to silicon, it will again decrease by 1 unit, and it will be x plus 1 minus 1. So ultimately we will find the value x. Same thing we can do from carbon to silicon, and if you go carbon to silicon, so in case of carbon, the values of atomic radius and metallic character were x minus 1, and from going top to down, we are actually increasing the value by plus 1 unit. So again it will be x minus 1 plus 1, so it will come as x. Now if we compare the values of boron and silicon, we see it comes nearly same, x, both are x. So that's why if we see the diagonal relationship, if we go diagonally in the periodic table, we find out that most of the properties are very close to each other. And yeah, this works in the lower atomic weight, low atomic number molecules. Okay. So this we have seen atomic radius and metallic character, which decreases along the period from left to right and increases along the group from top to bottom, right? Now let's just clear it. And let's see the trend of ionization energy, electron affinity and electronegativity. Okay. So these things, what happens if we consider it as to be, if it is a y, and we consider that it increases by plus 1 unit. From left to right, it increases by plus 1 unit, and from top to down, it decreases by 1 unit. Okay. Now we will take this pair, beryllium, magnesium, aluminum and boron. We will take this beryllium and aluminum. Okay. Now let's consider for beryllium, our electron affinity, electronegativity and ionization energy values are y. Now when we go from beryllium to boron, so actually these values will increase by plus 1 unit. So in case of boron, it will be y plus 1. And when we go from top to down, from beryllium to magnesium, these values will be decreased by 1 unit. So it will be y minus 1. Now again, if we go from magnesium to aluminum, we are going along a period. So it should increase by plus 1 unit. So if we increase it by plus 1 unit from magnesium, that means y minus 1 plus 1, and we will get y. Similarly, if we come from boron to aluminum, in boron, these units were, these ionization energy, electron affinity and electronegativity were as y plus 1 unit. Now if we go from top to down, we have to decrease 1 unit. Okay. So we will subtract 1 unit, and it will again come as y. So you can see beryllium is also having y unit, and aluminum is also having 1 unit. That's why there is a diagonal relationship between this beryllium and aluminum. I hope this method will be easier to understand. So this is a qualitative method. So this is not totally correct. Okay, the values will not be exactly same, but it will be somewhere closer. Now let's see. So all the periodic properties, for example, radius, electron affinity, electronegativity, ionization energy, polarizing power, remain more or less same for the diagonal elements of 2p and 3p. In the higher periods, the diagonal relationship cannot be seen due to the presence of d and f electrons. It results so because the group trend of some properties in the transition elements is of opposite nature compared to that in the representative elements. Representative elements mean S block and P block elements. Okay, but the trends along the periods remain almost the same for both d block and representative elements. So if we go to the higher elements, higher atoms, that time this diagonal relationship does not work, because what happens here, we were considering that if we go from left to right, it will increase by +1, and if you go from top to down, it will decrease by -1, right? So this is valid in case of 2p and 3p. But after that, when we have d and f electrons, that time this trend is not valid, because there are some properties in the d block elements that shows opposite trend. Okay, I have already discussed in this lecture. You can go back and check. So there are some trends that do not follow the order of representative elements, means S and P block elements. So maybe from along group from top to down, in case of S and P it is increasing, but in case of D it is decreasing, or the vice versa. But along the period it remains same. So along the period the properties are having same trend, but along the group the properties may have different trend. So that's why this diagonal relationship is not valid in the higher elements. Now you can see some of the parameters that are given for these pairs: lithium and magnesium, beryllium and aluminium, and boron and silicon. I repeat again, the values will not be exactly same. Okay, the values will be somewhat different, but there will be similarity. It will not be exactly same. Okay. Now you can pause the video and you can look it. My throat is actually hurting. It's a very long lecture, and my throat is paining. I will not go into the details of these similarities in the pair of lithium and magnesium. If you are interested, you can pause the video and you can take a note, or you can read this. So these are for those who wants to learn more. So you can have these informations. Similarities in the pair of lithium and magnesium. Similarly, you can learn about the similarities in the pair of beryllium and aluminium. So if you are interested, you can pause the video and you can read this. I'm not going to discuss in detail. I might discuss these things in some other videos, in some other chapter. And here are some similarities in the pair of boron and silicon. So if you are interested, you can pause the video, you can take a screenshot, and then you can go through this data. Yeah. So there are multiple properties that are similar between these pairs, or the elements which are showing diagonal relationships: lithium, magnesium, beryllium, aluminium, and boron, silicon. So I will conclude my lecture here, and most of all these things, some things I have collected from net, some things I have collected from other teachers or professors' lectures, and many things I have collected from this book. This book is actually written by Professor Ashim K. Das from Vishwavarti University, West Bengal, India. Means when I was in Vishwavarti, I was doing my bachelor's, so that time I have also taken his classes, and his classes were very informative. We have learned a lot of things from here, and he has 7 volumes, if I am not mistaken. He has 7 different volumes, so you can check which part is containing which chapters. You can take a look at those volumes. These books are very, very informative. Hey genius, welcome back to the 7th lecture of the series Periodic Table and Periodic Trends. So in the previous lecture, means lecture 6, we have discussed about periodic trends in atomic radius, atomic volume, ionization energy, electron affinity, electron negativity, metallic character, and cohesive energy. So all these trends and the reasons behind these trends I have nicely explained in the lecture 6. So that is a long 4 hours lecture. So I'll encourage you that you please watch that, and that will clear all your concepts regarding these periodic trends. And at the end, I have also shown some tricks and notes to remember these trends. So if you have not seen, please go and watch that video first. This lecture is going to be a fun-based lecture. Here I'm just going to show you some Guinness World Records, and I will encourage you that if it is possible, you can try to break them so that world record can be yours. Then I will show you some memes regarding periodic table and periodic table apps that can be useful for learning. So without wasting any time, let's start. First, I will tell you some Guinness World Records regarding this periodic table. So this one is known as the oldest periodic table of elements wall chart. This periodic table, which I have already shown you during the discussion of Mendeleev's periodic table. So the oldest periodic table of the elements wall chart dates from 1885 and was found at St. Andrews University, St. Andrews, UK in 2014. The chart was made just 16 years after the Russian chemist Dmitry Mendeleev published the first periodic table in 1869. So this is the oldest periodic table. So this girl is the fastest to arrange all the elements of the periodic table. So the fastest time to arrange all elements of the periodic table is 2 minutes 27 seconds, and was achieved by Natalia Nazam in Lahore, Pakistan. So on 15th November 2020. So this is the date which, when I prepared this PPT, that time I checked these values or these Guinness World Records. So I'm not aware that this has been changed or not. So you can go and check what is the current world record for fastest to arrange all the elements. And I will encourage you, you can also try to break these records. So Natalia decided to break this record for her academic achievement. She was 10-year-old at that time. So she was only 10 years old when she got this achievement. So next, this boy was the fastest to recite periodic table. So as class 8 cadet of the Rashtriya Military School, Bangalore, 13-year-old Ujjwal Sharma is the fastest to recite the periodic table without reading. So just sequentially named all the 118 elements of the periodic table in just 33 seconds, and the earlier record was 35.23 seconds. So if you are confident that you can recite this periodic table below 33 seconds, having a lower time, then you can go for it. So this person, or this boy, Swastik Garg, wrote all the element symbols for the periodic table in 83.38 seconds, and he is the fastest to write element symbols for the complete periodic table. So he wrote all these 118 elements in 83.38 seconds. Let's discuss about world's smallest periodic table. So in 2010, the University of Nottingham received a Guinness World Record for creating the world's smallest periodic table, lovingly etched onto one of the chemist Martin Polyakov's own hairs. So we all know Professor Martin Polyakov. He's also in YouTube, so you can check some of his videos. And it measured just 90 micron by 46 micron. So that was the dimension of the periodic table. Now researchers at the university have beaten their own record using electron beam lithography to engrave a periodic table that is even tinier. So first time they made a periodic table with the dimension 90 micron by 46 micron. Now they have beaten their own records. And the table was presented on a silicon chip along with portraits of Dmitry Mendeleev and Yuri Gagarin. Each portrait is around 30 micron by 30 micron, and the periodic table is just 14 micron by 7 micron, less than 1/40th area of the previous record. So earlier, the periodic table, what they have made, that was 90 micron by 46 micron, and now the current record is 14 micron by 7 micron. Now we will see some memes regarding the periodic table. Here you can see periodic table of wine. This is for the wine lovers, for sarcasm. So if you are going to propose someone scientifically, you can write this kind of I love you. And this is the periodic table of internet memes. And some more memes. So if you want to say someone cute indirectly, you can say this, that are you made of copper and tellurium, because you are cute. And this one is my favorite, that a hug without you is just toxic. So yeah, this one is, you can see if you remove the U from the hug, it will become mercury. That's nice. Now I'm going to show you some periodic table apps that can be useful for learning. So in your free time, you can download these apps and you can go through these apps, so you can learn a lot of information from those.
So if you go to the Google Store or Apple Store, then you can search periodic table. So I had already searched before, so that's why it is appearing in my recommendations. Now you will get a lot of apps. Some are showing the periodic table, some will show some periodic table related quiz. So you can download some of these apps, and in your free time you can play with those, and along playing you will also learn. So I had already downloaded few apps before. For example, I had already downloaded this app, so I'll open this. So as we open this, we see this interface where we can see the entire periodic table, and here you can touch in any atom. For example, I will take this lead. So if you touch on any element, it will show the details of that element. For example, this small thing you can see, that means the previous atom is thallium, atomic number 81, then lead is in between, and the next atom or next element is bismuth 83, atomic number is 83. Then you will get some overview, as names, year of discovery, cache number. So this cache number, this thing is actually important when you are going to buy this element. That time you will need this cache number. And then if you go down, you can see the number of electrons, number of protons, and number of neutrons in this element. And if you touch here, you can see the electronic configuration, how these electrons are arranging here in this atom. Now if you go further down, you can see some additional informations: atomic number, atomic weight, density, melting point, boiling point, phase, valency, period and group number, which block element it is, as well as you will get emission spectrum. And here is the electronic configuration, oxygen states, and then atomic radius, covalent radius, van der Waals radius, all these informations you will get. And towards the end, you will get its crystal structure also. For example, I have selected lead, so lead is FCC crystal. So you can see the FCC crystal of lead here. And again, some more informations you can obtain. So you can take a look at these apps. There are so many apps. You can take a look of few of them. Generally, we download games from this Play Store or App Store, right? But instead of downloading game, if you download this periodic table, then you can learn something new. Now in the corner, you can see some more tables. Solidity table, electron configuration, all these things. These things can also be helpful. And here you can see some indicators.
Now let's see another app. So in this app, it is kind of periodic table quiz. So they will either give you the atomic number or the symbol, and you have to find out its position. So let's see this app.
I will start it. So here you can select different options. I will do this find the elements. Now here in the find the element, you can also select different options. For example, just I'll take this group 1 elements. So it will suggest the element and you have to tell that where this element is located, and there is a timer that is going on here at the top right corner. So sodium, we know atomic number is 11, so it will go here. Then lithium, we know atomic number is 3. Cesium, it will go 55. Potassium, it will go after sodium, so I will put here. And francium, we know that francium is at the end of this group 1 elements, so it will go here. And rubidium, it will be at 37. And hydrogen, we know hydrogen is the first element in the periodic table, so I'll put in this one. So you can see this timing, and you can also improve your game in the next time. I don't want to start it again. I'll stop it. You can also do this name to symbol. There is also different options. For example, I will choose this halogen group. Bromine. Now bromine, we know bromine will be Br, so I'll tap in this Br. Tennessine will be TS. Astatine, it will be AT. So here is the AT. Fluorine, we know fluorine will be only F. Iodine is I. And chlorine is Cl. So all these small games you can play when you are free, and then while playing you can learn this periodic table as well.
Yeah, so I will end this lecture here, and this much I have just covered for the periodic table and periodic trends. And this last video, this lecture 7, is just for fun. I'm not going to teach anything new here. So for learning purpose, you can refer to these first 6 videos. If you have missed any video, you can go and watch.
Hey genius, so here I am concluding the series periodic table and periodic trends. I have made a total of 7 lectures. I'll recommend you please go and watch those lectures. I hope I have made all the concepts clear. But still, if you are not able to understand anything, you can comment down below, and whenever I will get some free time, I will respond to the comments, or I will make another video to clear all your doubts. And these videos take a lot of time to make, so at least 1 to 2 months I give per chapter. So I'll request you, please share it as much as possible. Share it with all of your friends. And if you like my content, and if you want to get more this kind of chemistry contents or other scientific contents, please subscribe this channel. That means a lot to me. Thank you for your time. Have a good day. Bye bye.